It's a great honor for me to introduce this Sierr update to 2023 on the artificial intelligence in the AI. I would like to remind you that the main language of this event is in English, with respect with the guest and the speaker of today. But before to start, I would like to switch in Italian because we like to introduce our authorities that today are here. So voglio ringraziare Giulia Scaravelli e Fiorenza Bariani in rappresentanza del Centro Nazionale Trapianti e del registro PMA. Quindi lascio la parola prima a voi due per lasciare giusto due saluti iniziali e anche dimostrazione di questa collaborazione costante e costruttiva che abbiamo. Prego.
Buongiorno a tutti, un piacere essere qui. Abbiamo fatto tanta strada insieme. Io ricordo uno dei primi convegni 2004 del registro, che ancora non era formalmente esecutivo perché il decreto, come voi vi ricordate, è del 2005, però iniziò una stretta collaborazione con la società degli embriologi, che all'epoca erano un po' arrabbiati in generale perché venivano considerati ancora troppo poco e con la loro società volevano fare di più, volevano avere nuovi spazi. Penso che dopo tutti questi anni voi possiate dire che li avete conquistati, vi sono dovuti, avete fatto tanta strada e abbiamo fatto tutti quanti insieme tanta strada. Quando si dice che nelle tecniche di fecondazione in vitro ormai i risultati sono quelli che sono, non ci sono miglioramenti, se voi guardate al lato laboratorio io direi proprio che questo non è vero, perché ci sono dei grandissimi risultati, un grandissimo miglioramento, basta pensare soltanto a tutto quello che ha comportato l'implementazione di tutte le tecniche di crioconservazione. Oggi il titolo di oggi mi piace particolarmente perché io, che sono ormai del Neanderthal, sentire parlare di intelligenza artificiale mi emoziona. L'ho già sentito a un convegno a Napoli una ventina di giorni fa. Questo è il futuro sicuramente, è il futuro però che viene governato dalle nostre intelligenze, dalle nostre competenze, dalle nostre conoscenze. È un mondo in cui io metterò il naso appena appena perché sono in una fase di conclusione e spero di concludere con la raccolta dati su ciclo singolo, l'iter del registro nazionale PMA. Se riusciremo tutti insieme a fare questa bellissima raccolta dati ciclo per ciclo, il registro sarà immortale e io avrò compiuto la mia missione. Ognuno ha una piccola missione professionale, io spero che sia questa e spero anche di concluderla. Oggi ci sono buoni motivi e buoni elementi per pensare questo. Sicuramente con la Sierr, appunto, sono anni in cui abbiamo sempre lavorato insieme e mi piace essere qui oggi e augurarvi una buonissima giornata e una proficua. Sentirò per quel che posso questa mattina se ci sono relazioni proprio in questo campo dell'intelligenza artificiale. Sono molto curiosa e sarò molto attenta nel sentirle. Passo la parola a Fiorenza, che si occupa di voi ancora più attivamente di me.
Grazie Giulia, ovviamente anche per me è sempre un grande piacere venire qui a trovare gli amici della Sierr. La società degli embriologi è stata la prima società con cui il mondo della PMA si è trovato a collaborare con noi, un po' perché quelli che sono i requisiti di cui noi ci occupiamo impattano moltissimo, soprattutto sugli aspetti di laboratorio più che sugli aspetti clinici, e nel tempo abbiamo costruito un rapporto che è andato crescendo e credo sia stato per tutti un rapporto di scambio. E in quest'ottica voi sapete che abbiamo fatto fin dall'inizio, quando ancora c'era Rosanna Ciriminna presidente, un manuale per la corretta interpretazione dei requisiti delle normative, che poi è stato rivisto e adesso è in una fase di ulteriore revisione proprio per adattarlo a quelli che sono stati i cambiamenti e anche all'arrivo del nuovo regolamento europeo che probabilmente arriverà l'anno prossimo e modificherà in parte quelle che sono le attuali direttive europee. Quindi insomma c'è questo lavoro in campo che stiamo facendo tutti insieme con la collaborazione di un po' di persone del CNT e di un po' di volontari colleghi vostri, e io spero che entro Natale ci sia sotto l'albero questo regalo per tutti voi, e quindi di poterlo presentare come nuovo strumento di collaborazione e di lavoro per l'anno prossimo. E con questo io vi auguro buon lavoro in questo bellissimo convegno, sempre spinto verso il futuro, verso le nuove possibilità, e davvero congratulazioni e una buona giornata.
Grazie mille. Grazie, e darei la parola a questo punto all'ente previdenziale e all'ordine dei biologi, che da poco è diventato non più ordine nazionale ma un'organizzazione a carattere regionale, quindi abbiamo i due presidenti qui. Prego, dottoressa Stallone.
Grazie. Io darei la parola alla presidente Arduini, perché ne ho eletta e devo dire mi fa molto piacere avere una persona di valore, una donna con cui facciamo sinergia. Quindi a te la parola.
Allora, buongiorno a tutti, è chiuso? Buongiorno a tutti. Io prima di tutto volevo ringraziare il dottor Valerio Pisaturo per l'invito, per l'organizzazione di questo convegno, che si vede avere un altro profilo scientifico. Devo necessariamente ringraziare la presidente dell'ENPAB, Tiziana Stallone, perché è la nostra guida in questa nuova nascita di un ordine territoriale. Noi ci siamo costituiti a dicembre appunto dell'ultimo anno come primo ordine regionale del Lazio-Abruzzo. Attualmente c'è una federazione che quindi veglia su 11 ordini territoriali e siamo il primo ordine in assoluto, quindi per me è un'enorme emozione essere qui oggi con voi a trattare soprattutto di una tematica talmente in evoluzione quale quella dell'embriologia. Mi emoziona la tematica per un motivo soltanto, perché io sono un biotecnologo medico, diventato anche medico, che lavora in una struttura quale quella della Cattolica, e sono esposta quindi costantemente alle limitazioni che l'embriologia ha in Italia per diversi aspetti, ma dall'altra parte sono esposta anche all'oncologia in cui lavoro, in cui la necessità di biologi specializzati in questo settore si fa sempre più sentire per la necessità di intervenire in determinati contesti di malattia e quindi di disfunzione ormonale e anche di trattamento, in cui noi garantiamo così, con l'aiuto vostro, con l'aiuto dell'embriologia, un futuro a delle persone che tutti i giorni ovviamente sopportano un trattamento che molto spesso inibisce ovviamente lo sviluppo e la maternità. Quindi che cosa dire? Una cosa importante, come ordine, e spero tanto in collaborazione sotto la guida anche dell'ente di previdenza, noi vogliamo rappresentare l'embriologia in tutti i suoi settori, dalla ricerca alla diagnostica, e cercare di fare in modo di capire qual è il ruolo del biologo e come questo si interfaccia perfettamente con quello di altre professioni sanitarie, con il medico e con altre strutture. Questo in Italia deve essere ancora ben compreso, e soprattutto bisogna portarlo all'attenzione del governo e delle istituzioni, perché il professionista biologo ha il diritto e il dovere di presenziare in questi settori nei laboratori, a maggiore anche competenza di quella che può essere il medico, si deve interfacciare con questo professionista e determinare un lavoro eccellente che impatta ovviamente sulla riproduzione e su, se vogliamo in senso lato, sul nostro futuro, sul futuro della nostra generazione. Quindi il valore di questo convegno ha un valore scientifico, tecnico, ma soprattutto umano. In maniera intelligente e professionale dobbiamo portare all'attenzione l'estremo valore dei biologi qui in Italia, che non devono più fuggire e andare in altre regioni, in altre soprattutto paesi. Ahimè, abbiamo la Spagna che in questo senso è portabandiera di un grande sviluppo nell'embriologia. Noi quello sviluppo che hanno loro lo dobbiamo coscientemente, e ripeto sempre la parola coscientemente, portare in Italia e favorire un grande sviluppo. Io ringrazio tutti, vi auguro un buonissimo convegno e ne sono certa perché, ripeto, incontri del genere danno spessore e valore alla tematica di cui trattiamo e spero di incontrarvi presto, spero di poter collaborare e di portare insomma sempre più biologi all'attenzione di questo meraviglioso mondo in completa evoluzione. Grazie ancora.
Io ringrazio prima di tutto Daniela perché le parole sono sentite e reali e noi biologi dobbiamo avere la garanzia che ci sono due istituzioni che davvero collaborano in sinergia, la Federazione Nazionale, l'Ordine Territoriale e la Cassa di Previdenza per il sostegno del valore della nostra professione. Il ringraziamento è al Presidente Valerio Pisaturo, con cui mi sono confrontata tante volte, ma non solo con lui, con Laura Rienzi, con Lucia De Santis, eccola lì. E perché? Perché l'ho detto più volte, con orgoglio, io sono stata una delle prime iscritte alla Sierr, ho visto la nascita della Sierr, perché nel passato di biologa, ricercatrice con il dottorato di ricerca mi occupavo proprio di procreazione medicalmente assistita, quindi i vostri nomi per me sono musica, come il nome del dottor Borini che so che è qui in sala, eccolo, professor Borini, con cui per me ero, come dire, ero una giovane ricercatrice e per me era un onore, no? Lavorare in questo campo. Ero una microscopista elettronica, quindi lavoravo sulla crioconservazione degli ovociti e così via. Allora, quello che mi colpisce di questo evento è il tema, sicuramente, perché i biologi hanno bisogno di strumenti e bisogna guardare oltre, avere intercettato l'importanza dell'intelligenza artificiale a sostegno della biologia della riproduzione è un'innovazione. Io al momento non ho visto nessun argomento su questo tema. Tra l'altro noi scriviamo liberi professionisti e la forza del nostro lavoro dipende dagli strumenti e gli strumenti che vengono messi a disposizione, quella che è il frutto e l'impatto sulla società dipende dalla cultura e la solidità delle società scientifiche, perché non bisogna combattere, e l'abbiamo visto, no? Un po' tutti dalla persona che ha fatto nascere Facebook, adesso non mi viene il nome, dalla regia di Apple, c'è anche un po' una critica, no? Di quella che è la nascita dell'intelligenza artificiale. Io credo che davvero possa essere di grande utilità. Il secondo aspetto, e lo dico come presidente di cassa, è il valore sociale che voi avete su quello che è l'impatto demografico in primis del nostro paese. La settimana scorsa con il sistema previdenziale italiano, quindi con le 20 casse di previdenza, eravamo a Bruxelles e nel Parlamento europeo si parlava proprio dell'impatto della demografia sulla stabilità del sistema pensionistico. E allora sicuramente c'è la stabilità, ma non è una stabilità utilitaristica, perché si rende possibile, anche grazie al lavoro, la crescita del paese, la piena soddisfazione delle persone, perché un indice importante della stabilità di un paese è anche l'indice del benessere, e quindi aiutando a realizzare quelle che le persone realmente vogliono, voi fate del bene bene al nostro paese. Quindi ancora complimenti per l'evento, noi ci impegneremo ancora di più come EMPAB a garantire, e da qui appunto la collaborazione con molti di voi, la formazione sul campo di tanti biologi sul tema della riproduzione medicalmente assistita, perché crediamo nel vostro lavoro. Quindi grazie davvero.
Grazie mille a voi, grazie di tutto. Grazie. I think we will start. So before to start, I would like to thank all the scientific societies that are partner of this event today. Jay, SIAMS, CBIOC, SIGU, that give us a really great collaboration. And let me introduce Danilo Cimadomo, our scientific coordinator, to discuss for the topic of today. Thank you.
Okay. So also AI will make my name wrong. I mean, it's pretty, so it works. So I'm happy like a kid, I must say. I'm happy that you all are here. And then finally we can make this live. So in these few slides, I will give you some numbers and an introduction of the program we go through together. So this is here updating numbers. 250 is the number of attendees that we are. And thanks for, I mean, you all to be here, and to some of them, people that are actually here travel a lot, many kilometers. We have people actually coming from Canada, from Australia, from anywhere in the world, and it's my pleasure and my honor to have you all here. Indeed, there are 13 countries represented from these 250 people. 18 are the sponsors that I'm, very happy to and honored to thank, because this event is due to them, thanks to them. 4 are the supporting Italian institutions. We have them now that very nicely introduced the meeting. 6 are the supporting Italian scientific societies, and we open the meeting for free to all the attendees and members of these societies. And we also have 1 supporting international society, that is the AI for Fertility Society. So the first session of the program will be opened by Stefano Diciotti, and it will be an opening lecture about AI in everyday life. And the whole first session will be held by professors at university, so there will be the academy represented here. They will lead us through how AI is actually changing the world, and Professor Maurizio Zuccotti will introduce this session. There will be Professor Lucia Sacchi from the University of Pavia. They will give us some terminology, the glossary, the relevance of AI. Professor Nicola Toschi from the University of Tor Vergata will talk about AI in healthcare and research. And lastly, Tommaso Pippucci, a professor in Bologna, will talk about AI in bioinformatics and genetics. So as you can see, there will be a focus from everyday life down to genetics. This session will be discussed by representing people from the three societies: Jay, the president, Professor Luciana Dini, Perino from SIGO, Dr. Perigo from SIGO, and Dr. Zuccarello from SIGU, so the Italian Society of Human Genetics. The second session will be hosted by Lello Scarica. And in this case, we will dig into IVF. So how AI, what are the needs for us in IVF? First talk by a friend of Sierr, Dr. Alberto Vaiarelli. They will talk about AI for reproductive counseling. Is it needed? Dr. Pallotti from Sapienza, AI in the management of male factor infertility, and then Luca Pagliardini from San Raffaele Hospital, AI in the lab, why? And this session will be discussed by representing professionals, again, from important societies in our field, Dr. Borini from CIFES, Dr. Garolla, Professor Garolla from SIAMS, and Padoan from CBIOC. And then in the afternoon, after the lunch break, different companies from the field, so the real players in AI in IVF, will lead us through their tools, the tools they are already commercializing, through the data that they are producing, and we will have the possibility to discuss with them the evidence that have been already published in this field. And then a closing lecture, Easter egg if you like, from Matteo Ferrante and Tommaso Boccato, who are two PhD students that will give us an idea of how novel paradigm from AI are actually adopted for chatting, painting, and how we are virtualizing also human creativity. And finally, this is perhaps the most important part of the event. We pressed you a lot to stay here up to the end. The keywords are food, drinks, music, and networking, because we want you to interact with the speakers and with the societies. You can find us on all the social networks, Radio Sierr. If you didn't hear to Radio Sierr yet, it's a podcast that I highly suggest you to go and have a look. And if you want to comment, use the hashtag SierrUpdate2023. So that's it from me, and I will now leave the podium to Professor Klinger, that will introduce our first speaker.
Good morning to everyone. It's a real pleasure to see you all here, and that you're a lot. It's really nice to have seen the presentation from Danilo, because it has come out the importance even of the research, basic research part, and the academic that I represent also in the society in Sierra. So it's a real pleasure to have seen how many universities are here present in this morning. So not to waste time and go straight in our day work, it's a real pleasure to introduce you Professor Diciotti from University of Bologna. He is a professor in Ingegneria Medica, medical engineering. And he will take us today in the everyday intelligence, artificial intelligence. So thank you.
Thank you. Thank you, sir. Thank you so much for this invitation. It's an honor for me to talk about AI in everyday life. Absolutely. You know that AI is an invisible hand on daily life. This is really important for me to transfer this point. And you can imagine that AI is something the big tech giants are focused on, and that is not important for normal people. But this is not true, because AI is present from morning until night without being aware of using it. You know about AI, ChatGPT, you know very well, because it is really powerful. Okay, it's a new entry in AI, but I will not talk about ChatGPT, because in another talk, other speakers will talk about ChatGPT. But I asked ChatGPT for help. ChatGPT, please help me in this in a good outline of this presentation. And so ChatGPT answered a very good outline for this presentation. So first of all, introduce the basic concept of AI, and then you can list a number of applications in AI for everyday use. And then we have a lot of other applications, AI in healthcare, in business, and so on. But I was not so completely happy about this answer, because I wanted a more precise list of applications in everyday life. So I asked another question, more precise question, and ChatGPT, after 20 seconds of thinking, replied a very precise list of applications of everyday life, starting with application with smartphones, social media, online shopping. And so, taking all these suggestions in consideration, I prepared this presentation. So, following the suggestions of ChatGPT, I would like just to give you a very brief introduction, very brief introduction to AI, just some terminology, because you know that in newspaper, every day you read about AI, machine learning, deep learning, and the question is, are all these terms synonyms or not? And the answer is no, they are not synonyms. Machine learning is a subset of techniques of AI. So with machine learning, we intend the algorithms that use statistical learning to enable machine to improve with experience. Improve with experience are keywords. Improve with experience. We will see later also why they are so important. And what is deep learning? With deep learning, we are considering a subset of machine learning techniques. Okay, so a subset of machine learning. And with this kind of techniques, we use mainly artificial neural networks, very deep, very complex, to learn from large amounts of data. Okay, the keywords here are learn and data. Okay, very, very, very important. So we will talk basically about machine learning, because in AI, effectively, the machine learning techniques are nowadays the more powerful. Okay, so for this reason, you find sometimes the term machine learning also in newspaper. And we can define machine learning as the science and also art of programming computers so they can learn from data. Again, learn from data. So if you want to summarize what machine learning is, I can say that it is really important to use a very powerful algorithm, but also to use a very large amount of data, and not only a large amount, but a high quality data. So a very good machine learning application is a trade-off, a compromise between algorithms and data. Okay, not only algorithms, because you may think that AI is only related to computing, to algorithms, computer algorithms. Yes, but no. The data are absolutely important for obtaining a very good performance in a machine learning system. And in the following, I will follow a learning by example paradigm, which is common in machine learning. Many machine learning applications use this paradigm. And for example, if you want to train a system for distinguish picture of dogs from pictures of cats, what do you need? You need not just one picture, but you need many pictures of cats, many pictures of dogs. So learning by example without describing how you are able to distinguish a dog from a cat, but only showing examples. Okay, so we will use this kind of paradigm also to understand what AI can do in our daily life. So if we start from morning until night, I usually when I wake up in the morning, I don't know if it is a good thing to do, but I open my phone with Face ID. I don't know if it's really good. And so here behind the scenes, there is an AI algorithm, because with the smartphone, basically find more than 30,000 of points in my face, and uses these points to understand if my face is really my face to open the phone. So behind the scene, there is a machine learning algorithm. It's a pattern recognition algorithm. Then if you use social media, I don't use social media, I have to say, but if you use social media, behind the scenes, there are many machine learning algorithms, because when your social media suggests friends or filter fake news, preventing also cyberbullying, and also personalizing your feeds, all these activities are basically the output of machine learning systems. More than one machine learning system is in action where you are scrolling your social media account. And also when you send or receive emails, there are many machine learning algorithms without being aware of it. Okay, so for example, when you receive email, your anti-spam filter to remove undesired emails is made of a machine learning system. The antivirus software, again, is a machine learning system nowadays, but also when you send or you reply to an email and you use a spell checker, the spell checker nowadays is made of artificial intelligence. It's basically machine learning. And now there exists also applications, apps, for suggesting the reply. They are able to draft the reply of an email, and obviously you can edit and improving, but they may be really useful also for the future. Okay, in home, where where we can find machine learning algorithms with these so-called smart home devices, for example, using smart thermostats. I have a smart thermostat. I have to say that, yeah, it's really weird for me because it learns how the temperature that I use in the morning or in the evening. So it learns from data. These are really keywords, learning from data. And you understand that now we are living in the data society, the society of data. We have a lot of data. And this is one reason, explaining why AI nowadays is emerging, because we are living in a society of data. When you use Google, the Google search, behind the scenes, there are many machine learning algorithms. The autocomplete feature, you see here, you type something and Google try to predict what you are typing. This is a machine learning algorithm where there is the prediction. Basically, usually there is a machine learning behind the scenes. When you find something on Google, the Google searching algorithm uses a machine learning algorithm again. And also advertisement, okay, personalized advertisement are based on your data, okay, your data, and a machine learning system uses your data for personalizing advertisement. Okay, other applications, when you use a digital voice assistant, for example, in your home, it uses the recognition of your voice, and like the recognition of your face, this is machine learning algorithm again. And it can suggest directions and can learn from your data, so can monitor your working hours, screen time. I don't know if it is really good things, but anyway, it can learn from your data. So you understand what the importance of your data. Okay, it's really important. How you give your access to your data. Okay, something related to banking operations. Machine learning can read a written signature and so check if the signature is your real signature or not, and check also any purchase, for example, in a shop. When you use your credit card, there is a machine learning system that tries to find if this transaction is really yours or not, or is a fraud. Okay, so you don't see anything, but AI is under the scene. And obviously shopping recommendations, they are all based on machine learning. Again, they are recommendations based on your data. So when you buy something, the retailer machine learning algorithm predict what you would like to buy more. So you understand that when you give data, they are used for predict, for suggesting something useful for you, that may be useful for you. And it is also used, the sentiment analysis applied to your feedback. So if you write a feedback about the product, also your feedback is analyzed to predict another product that you may be interested in. And obviously, this is similar also for streaming services like shopping recommendations, similar when you use Netflix or Disney Plus or other similar. Again, your data are used for suggesting new films, new music. Okay, so the idea is the same, data and learning from data, data and learning from data. Okay, oh, this is a new application. In this app, based on machine learning system, it allows you to suggest some recipes based on the ingredients you have in your refrigerator. I think that may be useful for me, for example, that I'm not so creative with cooking. So this could be really useful for the future. Okay, now we have some machine learning applications with an impact on the society. For example, traffic monitoring. You see here, I think that is incredible, this application, because it's in real time. So you can identify cars and trucks in real time. this is a real-time application, okay, not offline application, in real time. So it's incredible, this application, and we can apply this technology also for other goals. For example, you know that there are problems sometimes to find the parking, okay? With the same technology, using a camera over a parking, you can find in real time the parking spaces free, okay? Without using any sensors. You understand that using a sensor, it may be a problem because it may require maintenance, batteries. So here we don't use any sensor. And another application, detect changes in asphalt for road maintenance. And yeah, I think that this is a problem, especially in more Italian cities. If you see this application, I think that you will be very happy. This application for road maintenance was a pilot study in Memphis, Tennessee. Pay attention, a camera mounted on buses in real time detect potholes and send the information to a central server. And after 48 hours, 2 days, the roads are repaired. I think that this could be the best AI application for Italian cities. Memphis, Tennessee. Memphis, Tennessee. Yes, Memphis, Tennessee. This is, I think, really useful. Really useful. Okay. So using a bus and a camera mounted on a bus, a camera, a low-cost camera. So I think that very, very interesting application. And these are applications very similar because the idea is the same. Analyzing real-time videos is about self-driving cars. You know what they're doing. They are obviously avoiding other cars, people, and other obstacles. And I think that this video is impressive, probably too much impressive. I think because, yeah, now you see that the car is moving very slowly because there are some obstacles, but now the video is becoming impressive, probably too much. So I don't know, you understand that this application is debated because there may be also problems. Yes, I'm sorry, it's too much impressive. Let's switch up. Okay, this other application is interesting for teleconferences. You understand that in a teleconference, there is no eye contact because the camera is not close to maybe not close to the monitor. And so this is a real-time application. You see on the right side, the processed video for improving the eye contact with camera. It's incredible. It's in real time. I think that's really incredible. This is new. A few months ago was presented. It's really incredible. Okay. Okay, and as a last application, there is a lot of work about the generation of synthetic data, synthetic images, and other kind of data, and using generative adversarial networks and other stuff, AI stuff. And I need your help. Here we have two pictures. Which one is real? So if you want to play with me, please raise your hand if you think that the real one is on the left side. Left side. Yes, the mail. Is real. Okay. Okay, thank you. And which one think that the real one is the female? Okay, about 50-50. And the real one was the female. It's incredible. Again, which one? Left, on the left side? Which one on the left side? Which one on the right side? Oh, right side, yes, good. Okay, humans are already needed, okay, because I'm sorry? No, yeah. Yeah, human learning, yes, better than machine learning. You know, the problems in, for example, deep fake, you understand that we may be not able to distinguish what is real from what is fake. But we have a lot of useful applications. For example, in medical imaging, you can create synthetic data sets with reduced problem in privacy. You can share synthetic data sets. You can improve the data set size. So we have a lot of possible good application of this technology. Okay, so it will be hard to imagine any of our daily routines without the help of AI, but I think that we need a sort of regulation, because you understand that it is really exploding. So I think that we need regulation. And the European Commission is proposing a first ever legal framework on AI. And in this proposal, provides AI developers, deployers, and users clear requirements and obligations regarding specific uses of AI. I think that is very important. And in this work that is work in progress, we have 4 different risk levels. So we have an unacceptable risk, for example, in tools, voice assistance tools that encourages children dangerous behavior. So this is unacceptable and it will be prohibited. With high risk AI tools, for example, AI application in robot assisted surgery, there will be a list of regulations, a list of things to do. So you can apply these high risk tools. You can use that, but you have to follow a list of recommendations. Then we have limited risk tools. So for example, ChatGPT, you have to inform the human that he's talking to a machine, not a human. So inform the user. And so we have some transparency required. Whereas when we are using AI tools with low minimal risk, for example, video games or spam filters, no obligations. So I think that this will be really useful in the future. And the future is next year, the second half of next year, this regulation could become applicable. Okay, so thank you so much for playing with me. And if you have any question, obviously I'm here for you. Thank you.
I'm supposed to introduce the next session, but if there are questions for our colleague, please. Yes. Are there questions, curiosities? Yes, of course.
Is there a way to protect us against the high risks, also for our boys?
Protect us. I think that this regulation will protect us. I think that this is what we need, a European Commission regulation. Following this regulation, we will be protected, we hope so.
Any more questions? I saw some hands raised before, no? Okay, so thanks a lot, and we can move to the next session. So the next session is titled How Artificial Intelligence is Changing the World. And before we start, I'd like to thank the organizers for this timely and very necessary meeting. For those of us like myself who are biologists, we have grown up with biotechnology that was a science of its own. But we now know that it's completely interconnected with informatics. As a matter of fact, most of my work now in the biotechnology field is done together with bioengineers or mathematicians or colleagues from physics. And this meeting comes to a moment when the biotechnology and the informatics revolutions are really posing some of the most, I think, important challenges to our species. One of my preferred Italian writers, Italo Calvino, once wrote in his book American Lessons, which I suggest to all students. He wrote that for a good story to last for a long time, you need to have in the story both the good and the bad. Okay, so you need to have soothing moments and scaring moments. Otherwise, that story won't last long. Okay, and I agree. This is true whether you write a story or you tell a story or you are participating to a story. So you need the good and the bad. If there is no bad, that's not gonna last. Probably because people don't like when a story is just good. Okay, and I think that artificial intelligence is really a topic that falls into this precise storytelling. So it has goods and it has a lot of bads. And I took some, I wrote here some titles of very recent articles in different newspapers, like this one by Naomi Klein, who is a bit older than many of the young people here, probably know who Naomi Klein is. She wrote in the 90s the famous book, No Logo. And she's now one of the most important journalists that write in the New York Times or the Guardian about technology and science. And she wrote this article a couple of days ago in the Guardian. The title is Artificial Intelligence Machines Aren't Hallucinating, but their makers are. So it's all about bringing up the bad side, the scary side of the whole story. And we just heard from Professor Garolla the question, but is there a possibility that these technologies are bad for us? So it's something that runs in our mind. And many other titles like, I'm switching for a few seconds to Italian, but I'll be very quick because I couldn't bother to translate them. So this is in Italian. Il garante per la privacy blocca ChatGPT. ChatGPT, il lato oscuro dell'algoritmo è la forza lavoro. Lavoro e pensiero umani, il vero scontro sull'intelligenza artificiale, l'imparzialità fittizia di uno strumento di dominio. And the last one, sorry, l'idea più pericolosa dei padri dell'artificial intelligence è che non ci sia via di scampo. This comes after Geoffrey Hinton, one of the pioneers of the artificial intelligence, has just quit from, you've heard from the news, from Google, saying that we should stop or at least reflect on the experience we are doing. So I need to go back to my notes. Here they are. So it's a topic that has the scary parts, and I hope, I'm sure, the good ones, which will come out probably from this meeting as well. I think that the organizers have gathered here some of the best researchers in artificial intelligence, and I'm sure we will learn from them what artificial intelligence is, and we will update it on the most advanced experiments. Also today we'll have here a panorama of the most important enterprises, and they will tell us about the tools that they have developed, and the tools that might help us in our work, whether it is basic research or in research into the clinic. So it's going to be a day of knowledge, and I'm telling this particularly to the young students. We know that we have many of our master students here. So it's a day of knowledge, and to this regard, I would suggest, particularly to the students, this book, which has been written by a very good historian. His name is Yuval Noah Harari. He's an historian. He wrote, it's in Italian, but it's 21 lessons for the 21st century. And it's all about how biotechnology and also informatics is changing our world. And there is a sentence right at the beginning, and I'm finished my introduction, which I'd like to read you, which underlines the importance of such a kind of meetings. In a world flooded with irrelevant information, clarity is power. In theory, anyone can participate in the debate on the future of humanity, but it is very difficult to maintain a clear vision. We often don't even notice that a debate is underway or what the important issues are. Billions of us can hardly afford the luxury of delving into these questions, as we are pressed by quite other urgencies: work, taking care of children, or assisting elderly parents. Unfortunately, history does not make discounts. If the future of humanity is decided in your absence, as you are too busy feeding and clothing your children, you and they will suffer the consequences. Of course, it's quite unfair, but who said history is fair? So after having set these thrilling moments, I think we can start into the meeting with our first speaker, who's Lucia Sacchi from the University of Pavia. I'm from the University of Pavia. Lucia is a colleague and a friend. Before I said most of my work is done together with engineers, and Lucia is one of them. And we both have been taught by our mentor in informatics, who's Professor Riccardo Bellazzi, who's also the professor of Lucia. So Lucia, please.
Thank you, Mark.
The title of your talk is An Introduction to AI, History, Terminology, and Relevance. Please, Lucia.
Thank you, Maurizio, and thank you all for inviting me here today, and also on behalf of my group of the Biomedical Informatics Lab at the University of Pavia that has a long-lasting collaboration with Maurizio's group, who has been really a pioneer of the application of these techniques to biology and to developmental biology. So in this talk, I will try to give you an overview of AI with also some definitions and terminologies. I will go back also to some of the definitions that Stefano gave you in the last presentations, and some examples. So let's start from a bit of history of AI. AI as a discipline was born in 1956 when a group of very well-known scientists at the time got together in a workshop to, let's say, discuss on the way to make machines, we will call now computers, solve problems that were up to then only reserved to humans. and by solving those problems also improve themselves, so learn from these problems. Since then, AI has been growing a lot, and it went through several phases. Phases where AI had held a lot of promises in terms of results, and also phases that are known as the AI winters that were occurred basically during the 70s and the 80s, where these promises seemed to be unattended. After that, anyway, AI started to grow again, both from due to the technological advances and also to the availability of more data, until what it is known as the deep learning revolution that started around 2010 and has now brought us to the tools that are so famous also in everyday life, such as ChatGPT or Bard, that is the, let's say, competitor of ChatGPT that now is also becoming well known. Let's start from a definition of AI. As a definition, I have selected this one, that is the one that is included in the AI Act that Stefano was mentioning before. And in the AI Act, we find the definition of AI system. So an AI system is a system that is able to infer or to learn how to achieve a set of final objectives and to produce some outputs in the form of predictions or recommendations or decisions. And these outputs can be reached using a variety of methods, because as we already heard, AI is a broad discipline that includes several methodologies. And in this slide, as you see, this is the same slide, the same picture that you also found in Stefano's slide. You will, if you look on the web, you will find this picture in many different websites. And as I said, AI is a very broad discipline that includes for sure the well-known techniques of machine learning. That is a subset of techniques that is the one that is probably the most advanced at the moment, where we find a set of algorithms that, as Stefano stressed out very well in his presentation, where we train computers to learn from data. Deep learning algorithms are within machine learning techniques, those techniques that work by trying to reproduce the mechanisms that work in our brain, in the networks of neurons of our brains. And in fact, the machine learning algorithms that are at the basis of deep learning are called neural networks. Of course, the applications of AI and machine learning have been growing a lot also in healthcare. As you see here, this is a very, let's say, quick search I did last week on PubMed. And you see that in the past 5 years, the number of papers dealing with machine learning applications in healthcare has been increasing exponentially. This increase is due basically to 3 main aspects that can also be related to other fields, not only to healthcare. But anyway, the first one is the possibility that now we have to electronically collect a large amount of data from several sources that include both, let's say, data coming from routine practice, but also data coming from images, large repositories of images, large repositories of texts, and so on. Then on the other hand, we need and we have now the technological capabilities of storing first and then analyzing such data. And how do we do that? With a set of novel and algorithms that can work in an efficient and accurate way on such data. Okay, so these three aspects has led to the growth, the large exploitation of these techniques in healthcare research, at least. So going back to machine learning, because this is, let's say, the field of AI that is currently being the most applied to healthcare and biomedical data. Here you have some definitions, but basically what we already said is that machine learning are AI techniques where we train a machine on the basis of data or experience. So data are also known as experience. So a computer is said to learn from experience with respect to a set of tasks, because of course we still need an objective for this learning, if its performance at performing a specific task improve with experience. So they learn with experience, they learn from data. Within machine learning, we can find basically three paradigms that are called supervised learning, unsupervised learning, or reinforcement learning. We will focus on the first two in this presentation. Because they are also the most widespread in the AI applications in healthcare up to now. So, as I said, machine learning is that field of AI where computers learn from data. So what are these data? Data, we can think of data as represented with a metrics. So somehow we will be able to reconduct the data that we collect to something like this. We collect observations on a set of examples that could be, for example, patients. And on these examples, we measure some observations, some variables, okay, age, sex, and even things much more complex. In supervised machine learning, we also have another, and this, sorry, I forgot to say that these variables we collect on the data are usually called features or attributes. In supervised machine learning, we have also a special kind of feature that is called the target or the class. That is a variable that characterizes the output of our data. For example, going back to the example Stefano was introducing, cat or dog. The class our examples belong to, ill or maybe has the disease, doesn't have the disease, okay? So the main idea in supervised machine learning is to use these data that are called training data that have the class label to learn a function that usually is a mathematical function and depends on the type of problem and a method that we are applying, that is able to map our features to the output data and the target. Okay. So what do we do? Once we learn this model from data, we can use this model to classify an unknown sample, so a sample that we don't know the class, and find the so-called prediction. So the predicted class from our new sample based on the machine learning model we have learned on training data. Okay. In unsupervised machine learning techniques, instead, we are always starting from data, but these data that are always structured as before, but we don't have the attribute related to the class. We don't know, or we don't use, when we apply such techniques, the information on the output. So this algorithm work on the main idea to discover hidden patterns in the data without considering their classification, but considering, for example, similarities or patterns in data. So the objective is to group together samples in clusters or groups where the examples within one group are similar to each other, and we try to maximize instead the difference between different clusters. Okay, so these are the two main paradigms of machine learning. Now, in these last 3 minutes, I will show you two applications that of two works that we did together with Maurizio. My group did together with Maurizio's group. One applied supervised machine learning, and the other one instead unsupervised. So the first work was related to the classification of images coming from developmentally competent and incompetent oocytes through a supervised machine learning technique. So here the input data, as you see, are images of these oocytes. Images are, let's say, as I said, need to be converted. Data related to images need to be converted in that data matrix that you saw earlier. We apply a machine learning algorithm supervised that is called logistic regression. And through this algorithm, we are able to classify these images with a very little error. You see here the error that we do are here represented in red. And the algorithm is able to well separate the two groups of images between the competent and not competent oocytes automatically with a good accuracy. So it means that we don't make a lot of errors. The second application was an application on folliculogenesis, always starting from imaging data, in this case proteomics data, mass spectrometry imaging data. And the objectives was to characterize the relevant proteins in the evolution of folliculogenesis. Also here we used let's say advanced unsupervised machine learning techniques coupled with visualization techniques that were able, as you see, to group together these proteins in clusters. I will call them clusters or communities that corresponded to significant follicular types without the information on the phase where these images were collected. So this was an application, an interesting application, in my opinion, of unsupervised learning that, as you see, allows us to create and build such visualization networks where nodes are clustered together on the basis of similarity. And what it turned out is that in this case, similar and relevant proteins for a specific phase of folliculogenesis were really clustering together. So with this example, I conclude, and I thank you very much for listening to me, and that's it.
Thanks, Lucia, and I'm calling to the podium Professor Luciana Dini, who's our discussant. Professor Dini is the president of the Gruppo Embriologico Italiano. Is also a friend and a colleague. Luciana, do you know?
So, first of all, thanks to the organizing to let me to be here. And I have the honor to be the president of society that is very old because it is more than 70 years that is relating with the problems of embryology. Of course, not the embryology of human reproduction, but the study of the basic mechanism that are underlying any type of development. So that was the beginning of our knowledge, and it's very important. So now we have to face with a lot of different technologies and a lot of different applications that will help us in our studies. What I would like to give to the audience as a point of question, just to think about it, that it was quite clear from the timesheet of the story of the artificial intelligence is that in parallel, at the same period, it was starting the idea of nanoscience. So when it was thinking to create a computer to work, to analyze the data, on another room, there were people that were deciding how to take molecules and to create a different structure for these molecules to obtain different possibility and application. So the informatics is lining also on the basis of nanotechnology, and they are working together underground, because it seems they are two different fields, but are very, very connected. So I agree perfectly with the discussion of the morning, the introduction, in which we as biologists, we need the improvement of technological tools, because improving technological tools, especially those are at the nano-size level, we can better go deeper in the not real, because we don't know the level that we have to go deep of the problem, and we need someone much more faster than our brain to analyze and to help in our conclusion. So this is my comment, and I have to wait, I think, a question perhaps.
Yes, it would be nice if there is some time for a few questions from the audience, curiosities that have come to your mind. To me, as an embryologist, I keep telling to my students that from now to my pension, I want to work. And for this, I need perhaps more than artificial intelligence, even more. So certainly I need artificial intelligence, is to be able to connect all the different hierarchical levels that make up a human being. Okay. Until now, we have been used to disaggregate our individual. Yeah. If you think the way we are learning biology, it's divided into disciplines. Okay. But now I think it's time for these disciplines, for molecular biology and tissue biology, what's called histology, and organ biology to come together. And but to do this, probably our capabilities are not enough. So we need some instruments that allows us to bring them together, because something that we know since, something that we know since the beginning of the past century, and both me and Professor Dini teach to our students is that the living being is connected. I mean, it's just a matter of being useful for us to cut it into pieces, okay? But it's a whole together with the environment. So we move to a sort of simplistic model from the molecular biology, the histology. These are all simplistic models of the human being. And we move to a more complex model. And for complexity, we need some other instrument. Like in the past, we needed the microscopes. Now we need some other instruments. And I think these instruments come from your field, Lucia, if you want to comment on this or both of you.
Go ahead.
Just to add something, this is absolutely in my line of thinking. What is very important is to renew the idea of a biologist. That is very important. So perhaps we should rethink our academic course of studies. And biology is too big to still exist as a course of biological science. Should be divided in more specific area. And the very important point is that to have the best results with machine learning or whatever is to have the perfect collection of data. Because if we made the mistake in give data to the system of artificial intelligence, we should create something of incorrect and can create problem. I think this is a important link to create between two words that have to learn to speak together and to understand.
Yes, that's exactly the comment I would have made, because as I see it from the other side, you know, I work on these techniques, but without the cooperation of scientists coming from different research areas, the application of these methodologies is not optimal. To really have something that can support, because as I see it, working on applied AI to healthcare and biological sciences, these techniques should be as a support, as a real help to perform activities that, given the amount of data, the complexity of such data, it is impossible to carry out manually. But this should be a support. And this support will be optimal, so the results will be will really improve the knowledge only if data are discussed together, results are discussed together. We are able to propose results that you can interpret, understand, and trust. So this is my view of how AI could be of support to healthcare and in general, as an instrument, but nothing without the collaboration with the experts of the field.
I wanna, unless there are other questions, I wanna close this part of the session just by citing Ernst Mayr, who was one of the greatest evolutionary biologists. He said that putting together the different hierarchical levels, so the molecular with the cellular with the tissue level, it doesn't make just the sum of them. It makes something new, and that's new. So that word new is something that we still don't know. It's something that we call life, but it's something we still don't know. And so there is an open field to be discovered. And it's there for, of course, for me, I hope, and but particularly for the young people. And the engineers can really help us towards that, the realization of this unity. Okay, so we can move on to the next. Thanks, Luciana and Lucia. Thank you very much. We can move on to the next speaker, who's Professor Toschi from the University of Rome Tor Vergata. Ciao, Nicola. He's talking about artificial intelligence in healthcare and research. And our discussant, if he wants to join me, or maybe later, is Professor Antonino Perino, who's the president of the Società Italiana di Ginecologia e Ostetricia.
Okay,
thanks.
Thank you very much for the introduction. Thanks to the organizer for having me here. It's a pleasure to actually give you, it's going to have to be a, a shallow but hopefully broad overview of one of the things that I actually do every day, which is applying or designing AI paradigms for biomedical research. And so I want to start by asking a question, I guess, what is the point, right? Why is AI percolating so much into biomedical research? I mean, AI is great, we're all excited about it, but so why should we apply it to medicine, to biology, to biological data? And there may be many answers to this question, but one of the main drivers that's happening right now in the market, in the research field and in the fields in between, is the holy grail of medical care today, which is basically what some people will call precision medicine. Some people call it P4 medicine. So precision, participation, prediction, and personalization. Now there's even people who have come up with P5 medicine. So what does that actually mean? It's basically a paradigm shift. So right now, medicine, in my opinion, I'm a physicist, by the way, so feel free to contradict me, works in a reactive manner. It's a reactive paradigm. Something happens, we try to react, right? And we try to cure. And the other point is that we still have, in many branches of medicine, most of them, a so-called one-size-fits-all approach. So you get a diagnosis, you get a therapy. Yes, the therapy may be a little bit tailored to you, maybe to your weight, to your height. In oncology, a little bit more, maybe you'll do some genetic testing to see if a tumor will react to a certain chemotherapeutic substance or not, but no more than that, right? And so the paradigm shift here is to move away from reacting to actually detecting perturbations in health in healthy people before they actually turn into disease, and to crafting specialized and specific patient profiles that are idiosyncratic to that particular patient, so specific for every patient. Every one of us is different. Every one of us will react differently to a therapy, to a pathogen, to anything like that. And put these two things together to actually, preserve disease from happening, or if we can't do that, tailor therapeutic intervention to every single person, right? I mean, you all know that, I'll just give you an example that comes to my mind, Alzheimer's disease. Alzheimer's disease doesn't exist, right? In my opinion, or in many people's opinion, it's a spectrum, right? Or dementia. Why do some people react to some treatments and some people don't? Obviously, there's something different in these patients because the therapy is the same. We give the same drugs to everyone. Sometimes they work, sometimes they don't work. And this is true for a number of diseases, right? So we must be different. And the answer is in the data, right? What has been missing so far is the fact that we cannot observe, or we could not observe, these differences. And these differences may be encoded in what, and I don't need to explain this term to you, this audience, what we call biomarkers, right? Things that can quantify the state of a patient. These biomarkers can be multi-scale, multi-domain. You can go from molecular to, novel things like metabolomics, but all the way to systemic, biomarkers, even neuropsychological scales, medical imaging, and so on and so forth. And this data is actually now in the last 5 years really starting to be accumulated. So, learning from data and the AI winter, now we have both the computational power and we're starting to have the multicentric worldwide data to actually perform P4 medicine or test P4 medicine paradigms in a bunch of fields, right? Just to give you an idea of the interest, there is, of course, a precision medicine initiative, which is sponsored by the NIH. There is an equal or similar initiative towards precision medicine by the EU. And countries and institutions and funding bodies are pouring billions, actually, of dollars or of euros into this paradigm. So it's not just me that thinks that this is important. What is this paradigm that I'm talking about in a bit more detail? So the way that precision medicine is conceived right now hinges a lot on integrating this multi-scale, multi-domain, multi-everything data. I doubt that there could be a physician that could look at a whole patient's genome, at their medical images, at their complete medical history, at 100 hours of conversation with the patient, and recommend a personalized treatment. So now that part of integration is exactly why people are looking at AI. We're starting to have data. We're starting to understand that everyone's different. Now we need to integrate that data to make those predictions. And so P4 medicine is sort of an integration between, of course, big data analytics, what people call systems medicine. There's not a lot of time to go into it, but these are actually more mechanistic models that inject sort of a priori knowledge about how something works, something like meaning the human body. And of course, what we call the digital revolution, right? This is just a buzzword, but it means the ability to collect all these data in an organized manner. Somebody said that, the quality of the data is extremely important, and that is true, of course. And then the idea of P4 medicine is to put this into a whole sort of life cycle where at some point you have data which is both big but also deep. Big means, a lot of modalities. Deep might mean, like I said, the whole genome or thousands of radiological images or whatever. And then you go all the way to the clinical application, and the AI is somewhere in here, right? And the AI can do a lot. It can. And this was already mentioned, so thank you very much for explaining this. It can do a lot. Just to bring this more in a clinical context, let's say a supervised paradigm could be used, for example, for... yes, I'm fine, thank you. Actually, maybe I'm not fine, but I'm okay. I just have a cold. Thank you. Thank you very much. So in a supervised paradigm, that means you're training with data and labels, right? So you might have a big population of patients which already have diagnosis. You train your algorithm, whatever the algorithm is, whatever the features are. A new patient comes into your hospital, or into your practice, into your clinic, which has never been seen by the algorithm. And the algorithm uses the knowledge that it has apprehended from the data to tell you, okay, this patient has category B or diagnosis B, and it also quantify its own performance, right? Whereas, for example, in unsupervised learning, you might have a cohort that's really heterogeneous, but you don't know where the heterogeneities are. You're doing a clinical trial, 33% of patients respond, 25 don't respond, 10 don't show up to follow up. That's something else. But you might apply some sort of unsupervised learning algorithm to actually extract these categories based on the multidimensional data in the hope that the trajectories of these patients will be much more homogeneous, and also the reaction and the effect of therapies, for example. And reinforcement learning was mentioned. It's a little bit more exotic, but it's very, very big right now. It's one of the workhorses of what Google is doing, and it's also much more similar to the way humans learn. It's basically, let me put it in a very plain way. If there's any technicians in the audience, please forgive me, but it's just learning by doing, right? There will be an agent that's moving somewhere in in a setting like the world, like we do when we're kids. And if you do something right, you get a reward. If you do something wrong, you get punished, and you learn, and you keep going and going and going. And that's how these algorithms, or this training paradigm for algorithms, is structured. And it's very, very powerful, especially to solve more complex problems. So that was just an introduction, and now I just want to give you some examples. None of these examples are from necessarily from my work, but if you're interested, of course, you can look it up. Diagnostics, so mostly supervised learning. I always like to bring this up because this was the very first time that a neural network, in this particular example, a convolutional neural network, which is something which is very good at processing images, beat the performance of a team of doctors. This convolutional neural network here analyzed skin lesions and was able to make a very, very stratified, very fine-grained diagnosis about, malignant, benignant subtypes, and so on and so forth, better than a group of dermatologists. And this was a landmark. In 2017, you may think it's only 6 years ago, but in AI, 6 years are basically an eternity, right? This was a landmark paper, and by now it's an FDA-approved algorithm, and doctors have it on their smartphone, and so on and so forth. And it was also interesting because he used what is called a transfer learning approach. So I don't want to go into it, but I think it's interesting because transfer learning means take a huge model that has been trained by a huge corporation or a huge institution that has huge computers, maybe on data that is not exactly your data. For example, here they used a model that was Inception, which is a model which is trained to classify natural images of beaches, people, the world, basically, right? But it's still sort of understood that allows a bigger model to understand how these images are built, what the main features are, colors, shapes, and so on and so forth. And then you do what's called a fine tuning to your own data. So you have to train much less. You don't have to own super computers, but you exploit the knowledge from a big pre-trained model to actually tailor it to your needs. And this was exactly what these people did. So I thought that was interesting to mention, to get, like I said, dermatologist grade or superior to dermatologist grade performance. And there are many examples of this. This is just another one. These people were able to predict cardiovascular disease just from looking at retinal images. They're actually predicted a lot of other stuff, like gender, like whether one is diabetic or not, one is a smoker or not, and things like that. So the information is there in the biomedical data, much more than the naked eye can see, even if the naked eye has a lot of experience. And this is the strength of these algorithms, extracting relevant information and combining relevant information that we cannot see with the naked eye. Of course, drug discovery is a big field in the biomedical applications of AI. We desperately need new drugs for a bunch of diseases. And I don't want to, let you go without having mentioned AlphaFold. You might have heard of it. It's one of Google's great achievements. AlphaGo was an algorithm that that would learn how to play the game Go, right? But then the similar architectures were applied to predicting protein folding, which is something I'm sure you're all familiar about, right? The function of a protein depends on its tertiary, quaternary, basically on its spatial structure. And if you know that spatial structure, you have druggable targets, right? You can find targets for drugs. Now, this algorithm in 2020 had already predicted structures for all the proteins that could be expressed by the human genome, right? Without X-ray crystallography, without NMR, without any experiment. And sure enough, in 2013, actually, the first drug discovery of a small molecule inhibitor was done by using one of the structures that nobody had ever experimentally determined, but it were predicted by AlphaFold. So that is big. And this is just the green is the real structure, and the blue is the predicted structure, just to show you that it actually works, right? Another thing that's done a lot is drug repurposing, which, as you know, means taking a drug which is approved for something and trying it out for something else. Atomwise is a company that does a lot of that. The models are a bit different because they combine also physical knowledge about the molecular interactions in the proteins. So you could call it something like a physically informed neural network. To actually check whether these drugs could be applied to other targets. And for example, they repurposed an FDA drug that was actually, I forgot what it was for, but it was not for Ebola, and they used it successfully to treat Ebola straight out of a computer, right? And they also designed drugs for Ewing sarcoma, for inhibiting certain enzymes in the brain, and so on and so forth. All in silico. In silico means in simulation, right? Straight there from the synthesis of the molecule to the clinical trial. So you can imagine how much this can accelerate, and how many new things that you wouldn't have thought of you can discover if you can test, every protein possible without even synthesizing it, right? Precision medicine is what I was talking about before. The strength of AI here is to actually pool, like I said, multi-domain data. This is a bit old, but I still like to mention it because it was a nice project in my opinion. The Watson is IBM's supercomputing structure. And so they have this oncology program where they put together very different types of AI algorithms. Like, for example, natural language processing, which means that this program can read freely written reports by doctors, integrate them with images, and also it has a rule-based system, which means that some doctors have said, this you cannot do, this you can do. So it's an integration of expert domain knowledge from doctors and data-driven stuff to actually formulate treatment plans and options for oncological patients, and which has been successful for a number of cancers, from lung cancer to colorectal cancer and so on and so forth. So bringing together different types of AI tools to process completely different types of data into something that is homologous and can be used to make a prediction and a recommendation. Then, of course, in our current legal framework, it's up to the medical doctor whether to accept this recommendation or not, because they still have legal responsibility, but this can be very helpful in seeing things that can be overseen by someone else. This has been done with many, many diseases. So because I work a lot in neuroscience, I thought I'd mention Alzheimer's disease. I've already said this. Imagine you get old and your memory starts to decline, mild cognitive impairment, but then there's a time where either you keep going like this or you will veer into dementia, right? Any type of dementia. And if you could predict what's going to happen to you in advance, it could be great for you, for your caregiver, but it would be a huge socioeconomic advantage, right? So a lot of people are working on this. And these people, for example, by combining multimodal data, actually manage to make the prediction better, again, than any human, any practicing expert in neuroradiologist or radiologist. And again, this is not only a research interest, it has a huge impact on clinical trials, on planning, socioeconomic or welfare measures, and so on and so forth, right? And also, you may all know that in neurodegenerative disease, basically 40% of the diagnoses are completely wrong, and you only know when you open up the brain post-mortem, whereas the algorithm actually corresponded very well with autopsy results, which is a big deal. I don't want to, I think I have zero time, so let me just go quickly. AI in prosthetics, of course, has been used. AI is used a lot to control prosthetic limbs. Here, the algorithm is taking signals from just two nerves and matching the movement intention of the person coming from the brain with a 97% accuracy. So that's pretty advanced. Digital pathology I like a lot because it saves a lot of time. I don't know if there are any pathologists here, but you know that analyzing a slice and counting biomarkers and so on and so forth is horrible. And you also, most of the time, you'll get it wrong, because if you want to get it right, you'd have to spend 12 hours on each patient, right? And so image processing techniques will actually are in place to do this for you, even at a distance, which has a telemedicine implication. Wearable sensors. You know, I'm wearing an Aura ring right now. This thing here is monitoring my sleep, my blood oxygen and things like that. It's uploading it to the cloud. If I give permission, somebody could use it for analyzing data. And they are wearable sensors also for more complex things like biofluids and stuff like that. So this is also a great way to collect real world data, RWD, which helps in making epidemiological predictions. Yeah, I'll just go fast. You can use models to generate imaging with contrast from imaging without contrast. So you don't expose the patient to radioactivity, you don't expose the patient to additional risk, and the quality is basically undistinguishable from contrasted images. You can use AI to predict patient flows, to predict how long a patient will stay in the hospital, so you can plan accordingly and reduce wait lists. And this is also a topic that I like a lot, AI and mental health. There have been a lot of applications, and this is, I think, my last slide, or my second last, which have used chatbots or interactive AI systems on your phone to actually talk to you, learn from you. And as you know, your phone knows everything about you, right? It knows what you're doing, where you are, what the weather is at the moment. So the phone might say, oh, you know, it's a nice day today. You seem a little bit down. Why don't you go and take a walk? You know, and it can go all the way. I actually work on a project that did this. It can go all the way to saying, well, at this point, I recommend that you see a specialist, right? If this is not working. So that's very nice. And just to conclude, of course, this is all fantastic, but there are a lot of challenges, like the previous speakers were saying. Ethical considerations, privacy, and safety are a consideration. You may have heard about this. Very well-known names, the father of deep learning, Elon Musk, people like that, have written an open letter to the community asking for a stop in training these huge models like ChatGPT that might not very long from now exhibit what people call artificial general intelligence, meaning basically human intelligence or superhuman intelligence. You know, they want people to stop so that we have time to put the regulatory frameworks in place, like Stefano was saying, right? My personal opinion is that even if they stopped this, it wouldn't work anyway. Remember when if you're old enough, remember when the internet came out, you know, this is always going to be rear view mirror regulation. You can stop for 6 months or a year, but the field is so fast that unfortunately the regulatory agencies, in my opinion, are never really going to catch up with it. But, you know, this can be discussed. It's definitely an important caveat to keep in mind. So thank you very much for your attention. I'm sorry I went a bit over time. Take your questions.
I call to the stage Professor Perino, and I give him the microphone.
Okay, thank you. First of all, I was to thank for your kind invitation, organizer, and I want to precise that I am not the president of Italian Society. I am here in behalf of the president, and for me it's a pleasure to stay here with you. And it's interesting that in the morning devoted to the artificial intelligence application in our, I made a lot of paperwork for get my ideas about that. And I think Professor Toschi was very interesting presentation because he made a comprehensive panoramic of all of the actual situation. Speaking about artificial intelligence, I think to system in my car. When I start to drive, after 10 to 15 minutes, artificial intelligence of the car say me, it's time to get a coffee. And it's a good way to start. Yes. But in any case, so we have seen that there is no doubt that artificial intelligence application in our field, in medical field, is very promising, very interesting. No doubt that with artificial intelligence we will make more precise diagnosis, more precise treatment, and so more we get more good result for our patient. Of course, we speak now about artificial intelligence application in the field of reproductive medicine, and this is interesting because we have seen that it's how it's possible collecting big data to have possibility to improve our skill, our ability to find the very good embryo for making a very good transfer and to have the very good result. But I would like also to speak about some pitfalls, some problems in this field. And I think that now these methods are in the very early stages of development. And so we are in the moment in which it's not very easy to make a balance between opportunities and risk connected to. And I think about, like a gynecologist, we think about the problem of liability. Liability is a big problem today, making also becoming more complicated maybe in the future, because in this arena, in this scenario of our field, I speak with, of course, for IVF, medical, there are entering new players in this scenario, in this arena, like tech companies, like programmers, like data managers. And so if there is a problem, if there is an error or mistake or wrong reaction, what it will rise, surely, problem of who is in charge, who is responsible, and how to share responsibility. This is, I think, is a very important problem, and I think that the scientific society have to make a lot of work.
Can I make a comment on this? Well, this is a problem I think for many other fields. My brother-in-law just wrote a novel, so some publicity advert about who's responsible for a car accident when you drive a self-driving car. Yeah, that's something that hasn't been solved yet. So is the driver, the car company, or the programmer? So the engineer. So it's really a problem that crosses through different fields.
Yeah. In the future, we will have this problem. And the other problem, of course, the privacy and security of data of these patients, of our patients. I think that this is a very important area of concern. And of course, this problem need to be carefully addressed in the future. So, and finally, of course, there is a problem of cost. That of course we are not. This is not the place for discuss about that. But I think that is another important point to discuss about. So finally, you at the beginning you remember the Italo Calvino with Lezioni Americane, and it's 40 years ago, maybe more. And the running title is 6 Proposal for Next Millennium. But I want to remember also other writer, English writer, very famous, Aldous Huxley. 91 years ago, he wrote The Brave New World. I think that now we are, the Brave New World is just starting.
Well,
thank you.
Also Philip Dick.
Okay, thank you.
Sure. Do you want to comment on this, Nicola?
Yes, sure. I mean, I work in a medical context, both here and in the States, and the question that you pose is extremely relevant. In fact, anytime you propose an algorithm or a decision support system to a clinician, the question of legal responsibility, but not only legal, but also, you know, moral or professional deontological responsibility comes up. There are a lot of steps that are being taken these days already to make sure that, well, I'm actually sort of moving to the second question, which is easier, to make sure that the data is protected according to GDPR and encryption. So this is a very strongly felt concern in the field of AI applied to medicine. Everybody knows that it will never be used if it's not GDPR or compliance. But yeah, like I was saying in my last slide, the regulatory part and the responsibility part is something that almost branches out into philosophy, almost, right? And so there will be, I think we need a new generation of regulators, of people that actually create a discipline of AI. Well, it already starting to AI ethics, AI laws, AI responsibilities, and like I was saying in my, I think in my talk, just like when the internet first appeared, right? And people were doing no matter what, and there was no laws about it. There is a risk that we are exactly at the same point, except that now we have a million times the computational power, so a million times the speed of development. So yes, it is an open problem, and I'm actually very curious to know how it will end up being dealt with, if at all.
Are there a couple of quick curiosities, questions? Yes, who? Laura, please.
Thank you. I mean, it's really incredible. Huh? My mind is going very far. I see a completely new way to see medicine, physics, and biology. To have three of you here, it's really exciting. So what should we suggest to the next generation? Next generation of lawyers, next generation of doctors, next generation of biologists. We need to give some advice to them, to the young students. Should they do a master in artificial intelligence, in data science? Should we encourage our young students to do something new, to be ready for this new generation of jobs and work and life and reality?
I have a quick comment about that. My question would be, even before that, like, who is going to teach this to them, to your new student? So, you know, yeah.
I think it should be done collectively, okay, like we are doing today. That's a way of teaching, because the first step to do when you have a big problem like this, which has all the ingredients, it has goods and bads, so it's something that people will like a lot. And also has the power, because it comes at the right time in history. So the first step is going through discussions like we are doing now. So what the Sierr has done, I think, is of capital importance. Really, it's not just because I'm a member of Sierr and I've been invited, but it is because. As Nicola said, who's going to teach? There can be only one person, because it is a multi-points problem. So we have to gather together with many different figures that tell their opinion, because we are all involved. We are all using this stuff. So, I mean, we are all in. And it's just a matter of understanding what it is, knowledge, and then take the best decisions for the society. Too many? Yeah, but that's what happened always. When the first car substituted the horses, when the first, how you call it, la locomotiva, the first train.
I don't know who is at that time. I know, for example, that
we were not there.
I know.
Thanks a lot.
I know for sure that, for example, in the Nouvelle Cuisine, the teacher were not the old chef, but all new chef that were thinking in a new way. So I think it's very difficult. That is the most important, the most difficult problem for the AI, because all the people like me are, of course, biased, too much biased. We are not, it is not important that we are using this telephone. And so I think it is completely different. That I agree with Laura is the most difficult things and part.
Oh, sure. It isn't easy, but I think this is the first step. At least we are here discussing it. Yeah, I agree with you, Andrea. Yeah, it's not easy. We move. Yeah, thanks a lot. Our next speaker is Professor Pippucci from IRCCS, Azienda Ospedaliera Universitaria di Bologna, and he's going to talk about artificial intelligence in bioinformatics and genetics. That's the microphone, yeah, please.
So yeah, even it needed artificial intelligence to understand that I was talking into the microphone and automatically switch on. Okay, thank you very much. I am very glad to be here, and have to give a disclosure. I usually talk behind a desk or a pulpit, and having all this open space in front of me is really great. I could even dance. Second disclosure, I won't do it. I won't do it. So I'm very glad to previous speakers because they did a very nice introduction to the theory, which I am not very strong in. So I will go directly to give you some instances of things put in practice. And this is Pac-Man because I was very fond of it. Then I left computers aside for a bit in my life. I'm a biologist by training, which marks a difference between me and all the other speakers. It's more in what I want to say. Then I realized that I couldn't do my job properly without computers, and so I started to look at genetics on a bioinformatics perspective. So what I will say today is about what I know of machine learning, deep learning in clinical genetics and genomics, and I share with you. And then I will give you some hints in bioinformatics and genomic data analysis using these algorithms. With a look at variant detection and classification, which is most part of my job. And I will start with this because this is something that has become reality very fast in the last years, and it is about the use of algorithms doing facial recognition in the clinic. Which means that this device, using normal smartphones, is intended to help physicians, medical geneticists, to make diagnosis, recognizing the hallmarks of syndromes, looking at the faces of the patients. And I start with this because it is probably something that you can really understand its utility, its broad of scope and use, but also because it is based on something that is really shared by other applications in the field. You have already seen this morning applications widely using images not to make their job. And this is exactly what this does. And this is some summary of the mechanisms that are used by the algorithm, which is a convolutional neural network that has been mentioned already before for, as I said, other different but similar applications. And what you obtain at the end is essentially a similarity score to what we have fed the algorithm with. So images of patients that we know have a certain syndrome and the patients that we have in front of us at the moment of the examination. And what the authors claimed about this this tool, which has been published, you see, just some years ago, the publication came out in 2019, is that they obtained a ranking of the diagnosis the physicians agreed with in the top 10 of the list, and 90% of the situations where they used it over hundreds genetic syndromes. Now you know that genetics and genomics is not only a matter of clinical diagnosis, but it has also to do with sequence. And the title of this slide is Genome, both the book hard to read, which is a quote from Eric Lander, a pioneer of the completion of the human genome sequencing in the early 2000s. Because the problem that we have to do with is we have 4 letters replicated for billions of times, and we have to understand a lot of how the information is encoded and how the information is used by the cells and the organism. And what we know is that essentially many of this information is essentially impossible to be used by and understood by human eyes. So, this is important because, on the contrary, this kind of task cannot be performed or is impractical to be performed just with human intelligence, while the physician work that I showed earlier is possible to be done with the usual medical toolkit. So what happens is that the deep learning revolution, which has been started in the last 10 years, goes along with the transformation of genomics in a big data field, and the applications of the artificial intelligence in genomics have raised in the last years because of the impossibility of handling such a huge amount of data looking at the sequences with pencil and pen. So what we do on a daily basis in our laboratories is to get the sequences and align them to a reference human genome, and to try to understand if what you see in red, in blue, or in green is something that is worth of pursuing. So it's something worth of our attention. Are these variants which are clinically important? Are these real, or are these are fake variants because of technical errors? All these kind of questions has to be they have to be posed for billions of nucleotides and for millions of variants in each human genome. And so you understand that picking up the right and useful information from noise here is a very huge task. I just noted a special challenge for mosaicism is because what we are, I mean, the big thing is that we always pile up a lot of sequences over the reference genome, and the fewer are the bases that support the variants, so as in osmoticism, the more difficult is to understand if their presence is real or not. And another point is to predict the functional, the clinical utility of information, which is hard to predict, especially information that is outside the protein coding sequences of the genome, which have been widely studied in the in human biology and genetics, and medical genetics, especially for the scope of our interest, because today we have an availability of many human genomes, which are been sequenced very fastly and very cheaply today, and this information has is not supported by a similar level of awareness about the actual importance or clinical definition of their role. So this is an example moving from a still image recognition, where the problem of identifying variants, which is here, so this is a variant or not, has been addressed by using a neural network. And the idea of the authors is interesting, because what they did is to say, looking through eyes which are not human eyes, but are eyes of an algorithm. So they made the algorithm look at the images exactly as any genomicist, any clinical genomicist in the lab does today. So he looks here and say, oh, the caller called this variant. Is this nice? Is this real? It looks reliable. And they made the algorithm doing this for them. And what they say is that the neural network does it with 99% accuracy for all these small variants, using the same features that actually we always use to make this kind of evaluations with our human intelligence. Another couple of examples are about the classification of functional and eventually clinical interest of variants. And this is an example exploiting not only the human sequence, but also the sequences of primates on the basis of an assumption that many human primate variants can be used for their support of the evaluation of the human of a human sequence, because of the evolutionary similarity between the species. And actually, this obtained as another example of deep learning network an accuracy of about 80%, trying to discriminate variants in patients and controls in autism spectrum disorders. And this is another example addressing the big challenge of classification in coding, non-coding variants as variants happening outside the coding sequence. And these are two nice examples, because actually this is a summary we made of these different tools in a recent review. But the important thing is that both these algorithms are able to be fed with a lot of sequence context much more than what we are able to feed the usual algorithm. So this is the promising point of becoming more accurate in this respect. Finally, I just take 2 minutes to talk about something we have done in this respect, and this is one of our points in our research interest, which is exploiting exome data. So, as you know, maybe exome data are different than genome data because they are just looking at the exons, so they are sparse data that are actually only sequencing the coding part of the genome, and it's quite difficult to understand if there are copy number variants in these regions. So this is important because copy number variants are a source of clinical information, and for this reason, many tools have been developed for copy number variance calling in exome data. But as you can understand, I can assure you there is a deletion here, which is also quite big, but it's not probably trivial to understand by eye that there is no CMV here, but there is a CMV in heterozygous state in this sample, which is a deletion. So we reasoned that it could be nice to see if machine learning could help in understanding this issue, which has been addressed previously by many statistical modeling tools, and actually we wondered if there was a way to learn from data this kind of task, and actually we came up with the idea that we have an instance in our genome of a chromosome which is in 1 versus 2 copies, and this is the X chromosome. And so we modeled the training of an algorithm using support vector machine, looking at male X chromosomes and female X chromosomes to model deletions, and then we merged these data sets to model the applications. And what happened is that what we propose is that this kind of an approach can outperform accuracy of existing tools, especially in the fact that while statistical approaches are very good in doing this, but they are very biased towards either deletions or duplications, this kind of an approach is more able to generalize and is able to understand the presence of deletions and duplication with a similar accuracy. So we propose this to be more generalized and so clinical, of possible wider clinical use. And this is a work that has been done in collaboration with Romina Daurizio, who works at the CNR in Pisa. I have just some final remarks, starting with saying that the applications in clinical genomics are already here based on principles that are used in other areas of artificial intelligence, and they might be used in tasks that are impractical to perform by human intelligence or error prone with statistical approaches, and they have followed the transformation of genomics in a big data domain. I have given 2 examples with calling and classification, and of course, these approaches are increasingly permeating the field, as in other fields that we have seen also in all the other speeches in the morning. And this is the end of my talk. So I thank you very much for your attention.
Thanks. Thanks, Tommaso. And I call Professor Zuccarello, Daniela. Here I go. We have just 2 or 3 minutes, unfortunately, because we are running late.
Yes.
I'm running late. and if you want to comment on.
Yes, thank you for the invitation. I'm here on behalf of President of Italian Society of Human Genetics, whose greetings I bring to you. So thank you for the invitation again. Tommaso, very interesting talk as always.
Thank you too kind.
And I think that is very interesting that there are now some software based on AI to try to make a substitution in our clinics, because probably the medical geneticist is not really useful now, because you have a software in your smartphone and you just take a picture of the patient and the software say, yeah, it's the Silver-Russell syndrome, so it's done. So what is the role of clinical geneticists? We have the machine learning, we have the software, so but I don't think that it will be very easy to get rid of us. I mean, also because
you're tough people.
Yeah, in my experience, thank you, Lara. I think that in my experience, the phase-to-gene software, that is very interesting software, is still learning. Yeah, it's science years, but it's get right about 20% of the times, such as a second-year medical geneticist trainee. So yeah, it's useful just to make the first selection, but of course, I don't know what you think, but maybe the medical geneticists still need this process.
No, I don't want to give the impression that I want to do without my beloved clinical colleagues. I think I'm always remind of an eminent colleague back in around 2010, 2011, when the NGS technology came out, and this was the same kind of concern. No, the computer will do anything, which is actually the opposite of what is happening, because what we see is that by genomic variability always plays tricks, and what I don't know if I'm correct, because my experts, colleagues who preceded me in their talks might contradict me, but I think that what these algorithms don't want is that you are unpredictable. The genome is always unpredictable. Phenotypes are very often unpredictable, and I think that we have to do great attention to the use of these tools, because they will become very useful, but also they will need our, I think our, really us to follow the technologies and their developments. Also, I take just a minute to say that I agree with the need of actually increase the knowledge of this kind of topics in our education. And the other thing that is important, very important, I think, is ethics, because it's something that is probably overlooked, as the hard science in the education of biologists and medical doctors, and this is becoming something very important, I think.
Last question from we have 1 minute.
Running very late.
Yeah,
because I've been already told.
I hope it's not my fault.
Yeah, we need a coffee.
So we no, it's not a fault. We can keep talking with them in front of the coffee.
I will be around for the coffee. So if you want to catch me,
coffee time, and we'll be back in 15 minutes. Okay. Thanks.
Hello, everyone. It's a pleasure for me to introduce you next session. We start because we are late, and what an amazing session before. Now we have a very comprehensive view of what AI can do in medical fields. And now I'm curious of how our speakers will introduce the AI matter about IVF. We have a lot of things to do. I ask the speakers to stay in time, 15 minutes, please, for every speech and 5 minutes for questions, because we are, as human beings, we still have the needs of eating something and not eating only data like machine learning. So I would like to introduce my friends and colleague, Alberto Vaiarelli, Medical Scientific Coordinator of General Life Rome, Clinica Valle Giulia. He will speak about AI for reproductive counseling. Is it needed? Thank you, Alberto.
So good morning. Thank you, Lello, for this kind introduction, and thank you very much for this invitation, and congratulations for this amazing meeting. So the first disclosure, I'm a gynecologist, and so sorry. After the first presentation, after the first section, is not easy to speak about artificial intelligence in our clinical setting, but I don't have any kind of conflict of interest for this presentation. I want to be honest, because when I started to study medical school, my dream was to become like a Gandalf. It's just to manage my patients and in order to select which is the best treatment or the best therapy for our patients. But now maybe I need to change my goal, I need to change my dream, because the application of the artificial intelligence or the application in general for the new technologies, of course, we can help we can help all the physicians to manage our patients. So today we know that we are moving from traditional medicine to precision medicine, and of course the artificial intelligence can be the first step, okay, to allow the prediction medicine. And of course, the artificial intelligence can help me to try to support the decision, try to standardize the treatment, and of course, try to make an automatization for some specific protocol. I think, I think today, we need to keep in mind that we are in the new era of assisted reproductive technologies. We try to individualize the treatment. We try to individualize the ovarian stimulation, the luteal phase support. We stimulate patients in different way. So many evidence is growing regarding the tailoring of our patients. And of course, the new era of the assisted reproductive technologies can be considered a fertile ground for artificial intelligence. This is the reason why we can distinguish different area of interest, of course, in the IVF lab, but also in terms of clinical decision, in terms of outcome prediction, robotic surgery, and also for the cost effectiveness assessment. I think if I am a clinician, and so the title of my presentation is how I believe the artificial intelligence helped me during the counseling. And the counseling in a reproductive setting is not easy, because we need to try to discuss with the patients, and we need to try to individualize which is the efficacy, or what does mean efficacy. And efficacy means how many baby can I obtain after the treatment, but also I need to explain what does mean efficiency. And so I think the destination is a very important point, but also the journey is important. And I think this aspect is crucial for my counseling. The question is, how can I use the artificial intelligence to manage all this information? I think that in the lab, in IVF lab, we can hypothesize the putative advantage thanks to the artificial intelligence in terms of sperm selection, oocyte selection, and embryo selection. But the question is still open regarding which are the putative benefits that can I use in my clinical setting with artificial intelligence. Of course, the prediction of ovarian response is a very crucial step when I want to discuss with my couples regarding the realistic chance to obtain a baby. And the prediction of ovarian response is not only important in terms of hyper response, but also important in terms of hypo response. I need to maximize the ovarian response in every single stimulation. Another important point for me is to try to optimize a good number of the mature eggs. And so the prediction, of course, of the percentage of metaphase 2, I think this is another crucial point. But of course, another important aspect when I manage the counseling is important. Try to avoid the risk. Risk, for example, is when I have a premature progesterone rise during the stimulation, or if I want to predict the oocyte and the embryo competence. So all these aspects, I think, are very important in terms to predict the outcome for our patients. But also the artificial intelligence from my side can help me to try to reduce the time, to try to reduce the risk. And what does mean? Try to improve the efficiency of my treatment. And the last but not the least, try to reduce the workload, because of course we spend a lot of time with our patients, and so we need to save time to invest maybe this time for study or for intellectual activity. And then the reproductive surgery represent, I think, another aspect. What about the outcome prediction? So theoretically, this is an hypothetical illustration on what we can expect from artificial intelligence. I have a patient in front of me. I can complete some empty box, the age of patients, the sperm quality, some specific characteristic, and then I can have an algorithm to help me to predict the possibility for this couple to get in pregnancy. I think this aspect could be very useful also for the natural conception, because we can have patients also with subfertile patients during the first consultation. But theoretically, this is the idea, to try to have new information, or to try to support the counseling for our patients. During the counseling, we invest many times. We make a big effort in order to individualize the aspect that can impact the outcome. And the first point is the number of the oocyte. And so, in patients candidate for IVF treatment, of course, the number of the oocyte is a crucial point. And this is true also in patients with low prognosis patients. This is important because try to individualize the patients with a low chance is an important point in order to try to make a very honest counseling, try to make a correct information for our patients. And here you can see that the number of the oocyte, the number of the embryo transfer for each single couples increase the cumulative chance for our patients. But the problem is not only the quantitative, but also the quality. Of course, this is we know very well this information, but what I do in my clinical setting is to try to explain, and sometimes it's not easy. And so the point is that we need to categorize the patients. I think in our clinical setting, it's not easy to categorize the patients, but I need to try to do that, because otherwise I am not able to individualize a specific treatment for each single group of the patients. This is just an example regarding the categorization of the patients, defined low prognosis patients according with the age and according with the ovarian reserve. The problem is that I manage day by day patients with advanced maternal age and with a few eggs. And what we know today is the eggs, the number of the age, the eggs are the most important predictive factors for our chance. This is the reason why I need to change my approach with my patients, because maybe in patients with poor prognosis patients, I needed to try to discuss which is the cumulative live rate after multiple cycles, not only after one cycle. And this is difficult when we speak with our patient to try to make a correct formula to assess the measure of our success. This is the reason why today we are trying to move the concept from one stimulation to multiple stimulation in order to try to reach a relative high cumulative labor rate also in patients with very poor prognosis patients. What we do every day is to try to to understand the biological age of the patient. What does mean biological age? Means to try to understand which is the ovarian reserve. And the only tools that we have today is the antral follicle count and the MAH. And this aspect is something I think is important. I want to show you just the first realistic attempts to try to define the biological age of the patients. This is an Italian startup. The name is of age, with two simple input: the age of patients and the antral follicle count. We can have one simple number. So this number is easy to manage for doctors not specialized in reproductive medicine, in order to make a correct picture of these patients in terms of which is the biological age of my patients. But I want to show you the number of the data that support this algorithm. But I think that this can be the first step. The second point is that this is what we do, is to try to individualize the treatment for each single patient in order to have one competent embryo to transfer. This is just a very simple example. We know that, of course, we can have a huge variability, a biological variability, but for our patients it's important to understand maybe one stimulation is not enough to reach one competent embryo, because, of course, the competence of my embryo decreases. But this works apparently only when I have normal sperm, when I have no other disease, other medical problem. And the question is, can artificial intelligence help me to drive the counseling in specific patients population, for example, with severe male factors, or when I have abnormal karyotype? Because I need to try to explain to my patients my philosophy. I need to try to explain that sometimes I need not one cycle, but more cycle to reach adequate success. This is another example. The name is ART calculator. The goal of this calculator was to predict the estimate number of the metaphase 2 in order to obtain one competent embryo. This is the algorithm, and this is the paper for the validation of the algorithm. The validation was performed in 3 different centers. One was in Rome, another was in Ankara, and another was in Brazil. Here you can see the number of the patients support the validation of their IRT. And the goal was to try to make us, in a very simple way, a correct information of not only for the doctors, but also for the patients. Here you can see an example. You can write, so this is a video. Okay, you can write the name here. You can write the sperm source, ejaculate, or testicular biopsy, for example. And then we can have an algorithm to predict how many eggs I need in order to obtain at least one competent embryo. This is just, of course, a preliminary algorithm. We need the external validation, but I think this concept should be useful for our clinical point. Not only for clinician, but also for the patients, and also in terms of fertility preservation. For example, I need to reach a correct number of the eggs for our patients. Maybe in the future, thanks to expansion of genetic assessment, I will put in other important indicators in order to reach an ideal number of the oocyte. And I think this is an important goal for us, thanks to the artificial intelligence, to have many data, to try to combine all these data in order to have some simple support in order to take our clinical decision. I will go very fast in this second part of my presentation, but the idea is that many papers has been published regarding the putative advance of the artificial intelligence, not only during the first consultation, but just in order to explain to my patients that I can standardize the treatment, and of course in terms to improve the safety. And the safety, what does mean? Try to reduce the OHSS, for example, or try to reduce the hyper response. This is just an example in terms to decide which is the right time for trigger, or when we need to plan a monitoring during the stimulation. And it seems that thanks to the artificial intelligence, we can improve the number of the oocyte. We can improve the number of the 2P, and this is just an example. So all these papers are very positive regarding this approach. I think we need to external validation, but I think this concept is very useful also for us. Just an example, some other algorithm support that we can select the right time and the right position for the embryo transfer, thanks to many input in order to help the physician during the embryo transfer. As I said before, I think we need external validation. This is a big bias. Unfortunately, here you can see just an example that in the majority of the paper published regarding the artificial intelligence, the number of the records is there is a very huge difference. And also look the number of the characteristic inside the algorithm. So we need to work in this way, because still the age represents the most important predictor factors for our goal. What about the workload? Sorry, Lello, just I want to spend another minute. This is the paper was published the last month in JAMA. And apparently the artificial intelligence chatbot assistant might provide a response to patients in terms of quality and empathy compared with the patient, with the physician is very similar. That means that it's better to write in the chat box, and we will have a better response in terms of quality and emphasis. I think this application is very important because the antral follicle count for us is very important in order to predict the viral response, but we do manually this approach. Maybe in the future, we will try to make this step with artificial intelligence, because we need to overcome the intra-observational variability. And this is just an example. Okay, we do the scan. There is an algorithm to save all the quantification of the ovary and the follicles using the 3D ultrasound, and this is the detection rate is very high. Look, is around 90% in regarding the very small follicles. I think this is an important point. Maybe in the future we have a system to have a tablet at home with the ultrasound at home, and the patients in-house can make the ultrasound for the monitoring. This is just an example that maybe in the future also the management of the patients will change, because I can stay in my office and I can receive all the picture coming from the ultrasound in-house. And apparently this system can have a good concordance. What about the estradiol? No problem. I can take the saliva at home and I can have the hormones. And so this is maybe the way to reduce the workload for the monitoring. The last, just the robotic surgery. In the reproductive surgery, apparently we can have a space for the robotic surgery, but unfortunately there is no any data, and so we still need the gynecologist to make the embryo transfer at the pickup. So this is, I think, the most important slides. The application of the artificial intelligence in our clinical setting, I think, is important, but the problem is the nature of the data. Okay, because of course we need to redesigning the electronic medical record. We need to spend time, and sometimes I am a doctor. I don't spend a lot of time to write in a right way all the information. But if we can do this, maybe in the future we will have a good data, and this is, I think, the criteria to create a good algorithm. We need to also to define which is the success or what I'm looking for, because my goal is the live birth. And so every single strategist that can I use theoretically should be in terms of increase the primary outcome, and also the sample size. If I want to build a good algorithm, I need the data, and I need a huge amount of the data. And also I need to study to validate this data. So I would like to thank all of you for this opportunity. Thank you.
Thank you, Alberto. Please stay with us on the stage. And I will introduce you, my pleasure to introduce you Dr. Andrea Borini, Chief Medical Officer of 9.baby General Life, as your discussant. Please, Andrea.
Thank you, Lello. Good morning, everybody. I have a question for you. If you think like counseling with a doctor, infertility counseling, what do you expect? What is the information that are more important for the doctor for decide the therapy, the diagnosis pathway, or for the patient right to understand which is the prognosis? So if she can have a baby or not. Can you raise your hand for the first option? So it's more important for the doctor, the information that we can have in terms of history of the patient and everything. No, are more for the patient. So the patient has the right to understand which is the prognosis. I think that if we look and we see at the AI as a physician, what I would like to have in the future is to have help to, for example, to define the 15% of patient couples that they have still as a diagnosis idiopathic sterility, because idiopathic means that we are not able to understand which is the etiology of their infertility. So probably I think that the AI should help us in looking at the new things. For example, all the genome and putting data and information with the genome. Probably we will be able to understand which are the most of the idiopathic diagnosis sterility. So I think that it is very important to look more at what we have not now, instead of looking at how to predict the pregnancy with the data that we have already. So I think that is the most important thing for the AI.
So you are focusing on the knowledge that we can reach with the new tools about the patients, and also about personalization of treatment regarding the new knowledge.
Yeah, if we think that, for example, the 15% of the sterility are idiopathic, are those diagnoses just for genes problem? So can we enlarge the possibility to have a diagnosis and so to treat the patient in a different way? I hope that will be the help of the AI.
You mentioned also, you started with a good question, if it's important for patient or for gynecologists, for doctors. And from the patient perspective, and Alberto mentioned something that is interesting, the chatbot that can help to counsel patient when they are at home and they have doubts. Can you comment on this, the future of these kind of tools in IVF?
Yeah, I think that what we want to have now, so we dreams to have patients that stay at home, and we can do all the procedure except for the oocyte retrieval, having the patient at home. But I don't know if that is the only help that the AI can give us. So I think that I would like to have no any more couples without a diagnosis, a precise diagnosis, and I would like to have no patient
with just an IVF because we don't know which is their problem.
Questions from the audience? Okay, Alberto, want to add something to conclude?
Nothing special. So I personally believe that the artificial intelligence is the only way to put together the data, the evidence base, the experience of the doctors, and maybe we can create a new connection, because sometimes it's not easy. It can be very useful for the young generation also, when you don't have enough experience to take a decision. Can be, I think, a real support.
Thank you so much. Thank you. Well, it's my pleasure to introduce you the next speaker, Professor Francesco Pallotti. He's a reproductive endocrinologist and an andrologist, and a professor at the University of Enna in Sicily, and a researcher at the University of Rome La Sapienza. So, Francesco will speak about artificial intelligence in the management of male factor infertility.
Okay, thank you. Thank you for the introduction. I will just steal a couple of seconds just to thank the whole organizing committee for inviting me or speaking on this peculiar argument. And I'd say it's extremely peculiar because you will see from this presentation that while in embryology and in gynecology, the use of artificial intelligence is beginning to be reasonably widespread, in andrology and in the study of male factor infertility, well, maybe we are a little back, and let's see why. A few generic things. I think we talked a lot about this. Okay, artificial intelligence is a very, very long concept because it definitely precedes my experience as an andrologist, and the main goal was, and it should still be, the way to reduce error in diagnosis, treatment, and in general to assist us, both us and the patients, and as we talked about in the previous discussion, in prediction of our health risks in general, and in the study of male factor infertility in particular this way. This picture was already shown you by Alberto, and starting from this, you can see that most of the features where artificial intelligence in reproductive medicine was used are mostly based on surgery, artificial reproduction outcome, cost-effective assessment of artificial reproduction, embryo and oocyte selection. After all, for our spermatozoa, a kind of cell which is very loved by us andrologists, well, we just only one small picture here. Well, it has a widespread use now, but if you see from this table, well, studies and algorithms that are mostly focused on andrology are relatively few. As you see, we just have one way with support vector machines to classify sperm cells. Well, maybe we can do something better. And it is strange because back in the 80s and the 90s, we andrologists, those who worked with spermatozoa, were riding the wave of innovation, because one of the first use of algorithms was the computer-aided sperm analysis. Well, it is useful. WHO manual, the 6th edition, the last edition, which was published in 2021, puts the computer-aided semen analysis in the extended analysis. So someone who is trained, so those centers who can use those technologies, who has money to buy those devices, well, can use this to assist in the kinetic analysis of spermatozoa. I mean, sometimes it's difficult to use this data in clinical practice, because if the seminologist is not sufficiently trained, estimates of motility may not be sufficiently reliable. And there are many things that may affect reliability of these of this analysis, starting from sperm preparation to the statistical power, the computing power of the software, and so on. So in the end, in 1998, a national group suggested that maybe if we want to use a CASA system, maybe we should not definitely use for determination of sperm concentration as a primary objective, or at least not to detect simply a proportion of motile spermatozoa, because I mean, these data are extremely useful, but maybe they, using the technology of the time, maybe they were more useful in specific applications of this one, just like the analysis of hyperactivation or specific studies in reproductive toxicology. Well, nonetheless, those algorithms that were in a certain way the precursors of modern artificial intelligence in andrology had a remarkable success. Today, you surely know there are a lot of devices that assist in computer analysis of semen. And well, however, if the technology is not sufficient and if the algorithm is not powerful enough, but limitations today for these devices are not really different from those of 1998. And there is a reason for that, because oocytes or semen from other species rather than humans are relatively easier to analyze, because the ejaculates are clearer, the spermatozoa are more monomorphic. Human semen has, rather than having the winning the cup of the worst fecundity in the species in the planet, but ejaculates are dirt. There is a great deal of heterogeneity. So if the algorithms are not well trained, those analyses are not particularly easy. But if we can do that in a sufficiently good way, we can acquire a lot of data about spermatozoa, which comes from the linearity, the straight path, the velocity in where they move towards space, the displacement of the head, and so on. There are a lot of direct and indirect patterns that we can detect from a moving spermatozoa. And a lot of algorithms try to improve this analysis by adding the movement of the inside viscous fluid, the analysis of multiple tracks, and so on. In the end, to be very brief, very brief, computer-aided semen analysis can be used to report kinematic analysis and identify specific subpopulation of sperm cells. But I mean, sometimes they still need to be integrated by the manual light microscope semen analysis. So in the end, we andrologists still sometimes prefer, just like what WHO says, the light microscope semen analysis as a first level analysis. However, we can dig a lot of information if we apply those artificial intelligence algorithms to a computer-aided semen analysis. For example, if we feed to the machine, this is what this group made in, I believe, 2013 or 2015, I believe. If we feed the machine with a lot of kinetic information, we might try to, simply by stratifying those kind of movements, we can detect different movement characteristics. We can give a classification to reflect specific kinetic parameters in semen with, I'd say, sufficiently adequate precision, let's say about 95%, depending on what we are looking for. But this is just one way to see it, because another thing we can do is to use this data to predict what our patient has or has not. For example, this paper, using those lovely artificial intelligence methods, specifically a neural network, feed the machine with a lot of, what we say, medical history data, which range from age, season, the presence of fevers, smoking habits, and so on. We'll see them in the next slide. But the objective, which is the objective? Simply, we we may try to find a way to input data and predict the likelihood of having normal or altered semen analysis even before a laboratoristic approach. Well, you may argue, okay, what's the purpose for this? Well, we may, for example, use it as a screening method. The author suggested that this can be an alternative, but I see it more to be a screening method for patients to assist in early diagnosis or to direct the patient directly to a specific level of a center of expertise in andrology, for example. What makes me believe a little against this method is that I do not have a clear idea of what those variables are, how those variables are stacked. Because if I see which variables have been used in the parameters, in the analysis, you can see that these two columns showed the two models that the researchers have used. Okay, I agree that childhood diseases, mumps, polio may impact on adult semen analysis. Fevers, recent fevers, okay, I agree. Pathologies, allergies, and so on, okay, I agree. But there are a lot of variables that were considered non-relevant to the prediction. Exposure to radiation, chemotherapy, birth defects, alcohol, coffee, drug consumption. Well, they may be not relevant for the algorithm, but in my clinical practice, they are rather relevant elements. So one way to see it, that the feeding a machine with a lot of data can give us other, let's say, non-straightforward data that can be used to predict certain parameters. Also, we have difficulty because these data are valid only inside those caseloads. We do not really know if this can be really generalized to the whole population. And in the end, if you see the results from these two models, this is not the best curve I've ever seen, but it has high sensitivity and low specificities. So, okay, it's good to screen, but maybe you still need a human eye to have the full control of the clinical situation. And there are still other papers that try to investigate semen prediction of semen quality using these algorithms. It's not really important, the methods, because I'm really not an expert in artificial intelligence. So all those methods that have been proposed, I would be a very poor speaker if I even try to explain those. But what is important is the conclusion of the authors, because those data mining methods effectively can be used to predict something from our patients. The way to see it is how we clinicians can use these data to improve our effectiveness. This is the key point, in my opinion, because we still need to remember that we work with patients. We work in a clinical environment. So we need to follow our guidelines. We need to follow those analysis, first level analysis, semen analysis among them, but also microbiological, endocrine assessment, imaging, and so on. These data that we generally acquire from our patient are fundamental. But if you use those algorithms to predict a disease, we still are back because we miss the second part of the game, because we also need to diagnose, yes, but we need also to treat. So maybe the other part of the game would be to use these algorithms to identify those patients that will benefit from a specific treatment, or for example, those where a specific treatment should be not performed because they're likely not to respond. I believe directly to FSH treatment, for example, in the male infertility. Finally, I will just tell you another minute. Nonetheless, I'm quite happy about these predictions, because some way they can be used to assist the clinician, especially in the diagnostic part. For example, I will bring you the experience of colleagues from Münster that try to make a sort of proof of concept. They acquired a database of azoospermic patients, non-obstructive azoospermia to be specific, and try to find a way to predict which of these patients were Klinefelter patients and which were not. Okay, to perform this experiment, they trained an algorithm to identify a specific pattern that would be representative of Klinefelter syndrome. And as a benchmarking, they picked up 2 control groups. So essentially, those models were compared with an expert group. To be honest, PhD students from the time, or PhD that were just clinical, made the examination of clinical andrologists for the European Academy of Andrology, and other PhD students which were considered as non-experts doctors, which means they were people who were trained in andrology but were not specific for this specific environment. And well, let's say, well, if we see the overall accuracy, well, the AI, the models performed relatively better than both the expert group and the non-experts. However, if we see the values of sensitivity and specificity, well, sensitivity, we were definitely overwhelmed by the computed models. But if we see the specificity of our analysis, well, overall, we performed sufficiently comparably with AI, which means once again, maybe those methods are extremely useful in selecting patients, in identifying those patients which require a more careful approach from the andrologist, from the endocrinologist, from the gynecologist, and so on. So this is extremely promising. This is not clinical practice, of course, but in a way, we can think that those machine learning models could definitely assist in the diagnosis of specific condition, especially for less experienced physicians, which may use these algorithms to send the patient to a more specific clinic. I don't wish to steal more time because I see the time is short and lunch is coming. Okay, but I simply wish to remark that, okay, these methods are extremely promising, and probably they will be our future. I say that we andrologists are a bit back, so I don't think we should be scared in using these methods, but we still have to be careful because some way of critical evaluation and more extensive validation of those methods still have to be made before being introduced in clinical practice. Just a thank to my colleagues in Rome, which these are pictures from our lovely team in Sapienza, and bring you also the salutation from Professor Lombardo and Professor Paoli.
Thank you, Francesco. Thank you very much. Please stay with us. And now I'm glad to introduce you your discussant, Professor Andrea Garolla from University of Padua. Welcome. And on behalf of Italian Society of Andrology and Sexual Medicine. Thank you, Andrea.
Thank you. I'm here today on behalf of the Italian Society of Andrology and Sexual Medicine. Professor Isidori, greetings to all of you. I'm very happy to collaborate with your society that is so young, and in a young context is important to talk about new things. This is a really new thing, and the new things scare the less young people, as I unfortunately am. But I'm so relaxed when I saw that AI started from 1956, 10 years before I was born. So I think that we have just an experience. And when I searched this morning in ChatGPT, how to manage transsexual people, I was yesterday in a congress about it. I observed some things that touched me, and I observed also some empathy that lack also to all of my colleagues. So I was very happy, and I was very happy also of your reassurance about the security of this approach. I'm not afraid, I see Laura, about young people. I have a children, and I was afraid about the smartphone. I was telling him how to manage it, but he is teaching to me how to use it. And I think that young people will teach us how to use AI. So it is important as all the new things. This is a new thing, and I am enthusiastic to use it with you and to perform studies about it. The last thing I want to say is that we have a lot of biases, sure. We have to learn more, but I think that we will learn by our mistakes, as for everything. I want to say thank you to Francesco, because I learned a lot from it about AI. I think one thing about your presentation that was really brilliant. We have no problem, no big problem is important, but we have no big problem with the diagnosis in this moment, with the treatments. We can improve, but this is not a big problem. We have a big problem with the sperm selection. We have about 30 parameters to consider, and about 15 at least 15 ways to select the sperm. It's not possible for a biologist. So I think that this technology is mandatory for us. We have to give to this technology not only big data, but well-obtained data. This is mandatory. So I want to ask to Francesco his think about this proposal to develop the sperm selection by this technology, and I beg the pardon of translator for my Anglo-Veneto English.
Okay, no, it was rather clear, don't worry. And no, I agree this is a critical part because, okay, I decided to focus mostly on the clinical part because that was most suitable to my essence as a clinical andrologist. But yes, that's critical because you've seen that you said 30, but if we want, we can acquire even other indirect parameters. So we have a lot of way of acquiring data. And in this, let's say in Latin, mare magnum of data, we need definitely to find our way, and the time is ticking. And
okay, thank you. And any question from the stage, from the floor? No, I would like to close only with a question for you. Data that you are highlighting, we can collect in a lot of ways about motility. That is the best thing that we can do with sperm and AI. There is something that I can't understand about the way spermatozoa are swimming in a two-dimensional slide under the microscope, when instead when they swim, we are not acquiring knowledge about the three-dimensional way. Do you think that we are feeding machine learning with the wrong data, acquiring images from B-dimensional stage?
That's a big deal. In fact, we are feeding those data under the hypothesis that they are representative of our three-dimensional mean. That's likely not the case. And probably we'll need to acquire experience even in that, because we talked in the last discussion about the fact that at least 15% of couples of male are idiopathic. But are those really idiopathic because we do not know how to make diagnosis, or we are feeding the wrong data in this diagnosis?
Thank you. So we can go forward. Thank you so much to the speaker. Now, my pleasure to introduce you last speaker of this session, Dr. Luca Pagliardini. Luca Pagliardini is a researcher from University of the San Raffaele Center from Milan in Italy, and is the coordinator of scientific activity in this center. So thank you, Luca. Please, the title of is the point of embryologist, no? The point of the laboratory. So AI in the laboratory. Why?
Thank you. Thank you very much to Sierr for this invitation to this magnificent Congress. And let's start with this question. So why should we use artificial intelligence in our laboratories? Well, this answer could be quite simple, because every day we work extensively with microscopes. And so we deal with a huge amount of images, and images are the favorite kind of data for convolutional neural networks, as we've seen. And so if we take as example this small image, it's big, but actually it's composed by 500 pixel per 500 pixel, so a small resolution that contains 250,000 data points. So we already have in our PCs millions of data that we can analyze using artificial intelligence. And we can ask this AI to identify complex patterns, extracting meaningful features, and possibly making prediction. And so the first problem, the first issue that we can solve in our laboratories is the inconsistency in embryo evaluation. In this case, blastocyst evaluation. We all know that the evaluation of blastocyst is subjective and incomplete. Incomplete and also time consuming. And so this is a huge deal for us, and often different laboratories use different grading system for the evaluation. So in that was the first paper, the first study where actually deep learning was used in the assisted reproduction field. And the authors asked a group of embryologists to classify thousands of embryos using the Vick and Zaninovich score system. Then only the two extreme categories were chosen to train a neural network called STORK, and that showed a really good accuracy in classifying embryos, blastocysts, in a separate set of images. And then this model was tested against embryologists. So a set of 5 embryologists classified more than 200 images of blastocysts using a different grading system this time, the Gardner grading system. But due to the low agreement among them, a majority vote was calculated, and when the neural network was compared to the majority votes, it was better than the results of every other embryologist in the study. So this is really important since if we install this application, if we use this application in every laboratory in the world, we can just obtain a consistent evaluation of blastocysts that doesn't exist actually now in this moment. But moreover, the researchers asked the neural network to classify also the intermediate quality blastocysts that were firstly removed from the training. And the surprising part is that the STORK neural network was able to classify as good quality embryos the ones that had the higher percentage of pregnancy. So we can pose a new question. Can AI extract information from the images? So can be helpful in predicting pregnancy rates? And the answer is probably yes, but we have to make some consideration, since we have previously learned we need clear and accurate outcomes for the training of deep learning models. And this is challenging in our field, since we have a lot of variables to consider, but in particular because we have the uncertainty of failed pregnancy, where we don't know where the cause lies in the embryos or in the endometrium. And ideally, in a future, we may develop artificial intelligence that may take in consideration a lot of data, like the clinical history of the couple, the embryo culture conditions, that may take in consideration a lot of biochemical data and pictures from all the developmental stages of embryos, and also uterine receptivity. But at present, this is not possible. We can also, if we focus on the principal actors of implantation, the embryos and the endometrium, we will see that the researchers have focused only on embryos images to extract information, trying to predict pregnancy. And actually, two targets are chosen preferentially, like diploidy status of the embryos, like a surrogate for embryos with a good potential for implantation, and pregnancy itself. So I would like to show two recent examples of application of this kind. The first one is from the same group of the STORK model, and they try to develop a system, a neural network that can predict diploidy status of blastocyst using static images taken from the time-lapse incubator. And the system was also trained using some clinical information like patient age, a morphological assessment by an embryologist, and some morphokinetics data. And the results are pretty good. There is a good accuracy in the prediction. And the most important part is that if we test the same model outside of the first laboratory, so in other laboratories with different images, other system, the results are similar. And again, we can show in a new paper a similar approach for the prediction of pregnancy this time. And the difference was that they used the whole video from time-lapse this time, so an incredible amount of data to train the neural network. And also in this case, they integrated the model, the video model, with some other data from oocytes, so the age of the patients, MHA, and also the endometrial thickness. And the authors demonstrated that the inclusion of other data can increase the precision of the model. So the hybrid model had 0.73 accuracy in predicting live birth. And they also compared the hybrid model with an embryologist evaluation of the same blastocyst. And also in this time, the artificial intelligence was better than the human, but we need to say that the human embryologist can classify the blastocyst only in two ways, as good or bad. So this is not like the case that we use all day in our laboratories. But artificial neural network can be used also for other kind of application beside only the prediction of pregnancy. Like in this study from Hammer and colleagues, where they tried to develop the prototype of a witnessing system. So a system that tried to avoid error, avoid the mismatch of patients in the laboratory. And they taken cleavage stage embryos and blastocysts, and they take pictures at the first time and then after 5 hours. And so they asked the convolutional neural network to create a unique identification score, so like a fingerprint. And then they assessed if the system can correctly choose the right patient based only on the second image, and demonstrating a 100% accuracy actually in matching the patient. So you can give this algorithm a plate with some embryos without name, without any information, and actually can identify the correct patient. And the same group didn't stop there actually, because they proposed a new innovative application as a KPI, key performance indicator, in the laboratory. In this case, they used a neural network that was trained to predict the probability of high-quality blastocysts looking at cleavage stage embryos. And they compared this AI-generated KPI with other 4 KPI available in day 2 and day 3. And they demonstrated that this KPI generated from the AI was able to predict pregnancies. So at the higher correlation with pregnancies under different culture media conditions. So I was short, so we can go to lunch. And I would like to pose the final question. Can artificial intelligence teach us something new? Because we have seen that we have a lot of data that artificial intelligence can analyze this data, can reveal pattern, can analyze this pattern, but the information are hidden inside the neural network, the so-called black box problem. And if we can decode this information, we can probably obtain some new knowledge. So the artificial intelligence could not only be seen as a tool, but could possibly become a teacher in our laboratories. And so we can probably obtain in the next years a deeper scientific understanding of IVF. So thank you for your attention.
Thank you so much. Luca, please come on stage. Now I'm glad to introduce you your discussant, Dr. Professor Andrea Padoan, please, from University of Padova, and on behalf of CBOC Society. Thank you to be here.
Thank you to everybody, and thank you to invite CBOC to be here today. I'm in behalf of the society and on behalf of Dr. Tommaso Trenti, who bring his greetings to you and to Sierr Society. So thank you very much. So I look with very most attention the presentation of Dr. Pagliardini, and but I want to focus especially in 3 points that Luca said during the presentation. The first is about the competence and skills that people should have when they want to capture and work with this data, because as Luca said, data should be quality data, and in the last lecture it was already reported this important point. The second point regard the algorithm, the artificial intelligence algorithms that should be, in my opinion, which is also an important point that are widely discussed in literature. The algorithm should be tested because when they are generated, for example, by industries or by our colleagues, they could be very well fitted to a particular situation in a particular lab. Instead, we want to generalize the applicability of the algorithm to other labs because they use other microscope, other techniques. And the last point is like a provocative point that I want to focus you, is the fact that for example, the algorithm may be not stable during time. because some variables change during time, maybe the quality of the microscope, the quality of the analysis, or change also the personnel that work with the analysis. And someone in literature are saying that we should control the quality during time of algorithm, for example, by using quality controls. So just for now, because we have limited time, I have just one question for Luca that is about the skills. Do you think that is the importance, in your opinion, to have a good skills for this implementation, for collecting data, for standardizing data?
Yes, surely it is important. But for the application that I've shown, actually, the most important thing is the outcome. And we have other kind of problem in that way, because we actually don't know why we fail pregnancy, why the embryo doesn't implant. And on the second observation, I think that the scientific society has a big role in this. They should hurry up, because we are already late. This field is really fast. So 1 year is like 10 years in the real world, and the scientific society should provide maybe the controls for this application. So to test the actual effectivity, the actual usability in different conditions, because we can see a paper, we can say, okay, this works, I will use this in my lab, but maybe I have few data I cannot control. So scientific society, Italians and European like Sierr, should provide big data set on which we can test actually the efficiency.
So thank you. That's important, because many scientific society by now are establishing new working groups on artificial intelligence. Also inter-society group work very well. So thank you. That's a good point. Thank you.
Thank you. We have also... Okay. I was saying that we're also time for another question from the floor, but I think we are... Okay. So speaking about feeding, we can go feeding also our neurons. And okay, thank you so much to the speakers, and thank you all for this wonderful session. We see you after lunch at 14:30. Thank you. Grazie.
So please take a seat. We are going to start the next session. I'm very lucky. I'm with 2 human beings. And we're going to talk about artificial intelligence. The whole yeah, just to change topic. So please take a seat. I'm like a teacher at school. So we're going to start with session number 3, artificial intelligence players in IVF. So we are going to go deep in the IVF sector with 2 great experts. And I'm very happy to have Cristiano Ottolini and Federico Faber here next to me to start the conversation after the presentation. Federico, do you want to start presenting the first speaker? Thank you.
It's my pleasure to introduce Christina Hickman from Fertility with a talk called From AI to Better Clinical Outcomes. Christina.
Okay, thank you so much, Sierr. Thank you, Danilo, for putting this together. So on behalf of the AI Fertility Society, it's great to see the interest on AI growing, and it's great to see so many people genuinely enthusiastic about how AI is going to come in to improve our practice, improve our standard of care. So my talk today is going to be on From AI to Better Clinical Outcomes. And my conflicts of interest, I'm involved On the academic side, I'm involved on clinical practice. I own a couple of clinics in London, one of which, Avenues.life, we believe it's the first clinic that's been built with AI end-to-end. And I'm also the chair of the AI Fertility Society. And from that position, I very much would like to invite you all to engage, to participate here locally in Italy. And if you want to join, if you're coming to Esri, you're welcome to join us for the executive committee meeting, which will be an open meeting this year. And all of you are welcome to attend. AI has been around a lot longer than IVF. So we've heard this already. The first paper that I could find on AI and fertility was actually from 1979. That's only a year after the birth of Louise Brown. And you can see from this PubMed graph that the publications have stayed pretty stagnant, with only 1 or 2 papers ever so often across a couple of decades. And it wasn't really until 2018 that we've seen this boom in AI in fertility. I believe that this is partly because that's the point in time that following time-lapse, following PGTA, following the increase of blastocyst culture, we finally were in a position where we had organized data, which is a basic ingredient for AI to be able to prosper. So what is AI? So I've seen lots of attempts to define it, but in very simple terms, it's a tool. It's a tool that we use to take the chaos of raw data and turn it into useful information that we can make decisions with. Some reason my timer is going ahead, maybe AI is jumping in. Think about, I landed in Fiumicino and I had to find my way here. I have no idea where I am on the map, but then on I go with AI, and AI tells me you are here, you're going there, just follow that line. So I go from the chaos of where the hell am I to the simplicity of this is where you need to go. We then transfer this into embryology. You take time-lapse. Time-lapse video is computing about 2.5 billion data points. We can process all of that. So what we do is we pick our favorite data points. Depending on, do I want to look at the last image and make an assessment? Do I prefer to look at inner cell mass? Do I prefer to look at the expansion? No. I prefer to look at the cell divisions as it's going through. Are there any anomalies? I like the qualitative terms. So now you have the same embryo being assessed potentially by different embryologists across the world, each person looking at it from a different perspective and making a different decision as to whether to discard, transfer, or freeze. We shouldn't have that subjectivity on something as important as making a decision of the fate of an embryo. So what AI does is it processes all the information, not just our favorite ones. It processes the entire video across all focal planes and provides you this simple viability score. It highlights to you any anomalies that you might have missed or that you weren't aware of. So we transition from opinion-driven decisions all the way to data-driven decisions, bringing with it the consistency that's required for our work. We also need to consider what is the efficacy of prediction of these tools. Now, we have in the presence here of many different companies of AI, so I love the fact that we have choice of who to go with. I am going to be talking on behalf of fertility, so here's the example of the Chloe Blast score and Chloe EQ score. And what's been really interesting for me to say is that we're seeing similar efficacy of predictions across different clinics around the world. Okay, so whether you are in Turkey, UK, or Brazil, how the algorithm performs is the same, despite the differences in practice, despite the differences in the types of patients being treated. AI is also here to make our life easier. So I have always been a huge advocate of time-lapse. I'm a big believer that this is the foundation to allow us to introduce data-driven decisions in the area of embryology. And I didn't enjoy so much doing the manual annotations. So I love the fact that AI is well suited to do that manual work for me. And we have done a lot of work looking at how well or how comparable is the annotations of the AI, in this case, Chloe, with the annotations of a human embryologist. And you can see here that in all cases that we've assessed, it's at least strong. In some cases, very strong. Those 4 clinics in Brazil, we did a little bit differently. With the others, we asked them, we just took their retrospective data previously annotated, and we saw we had a strong level overall of agreement. But when we did it in Brazil, what we did was we provided them with Chloe, and then we asked them to supervise it and determine whether they agreed with it or not. What this tells me is that potentially some of the disagreements that we saw before were really associated with human error. So now you have 2 independent assessments of the morphokinetics. And this will obviously bring a more robust data set, which is these are ingredients that are going to be used for your clinical decision making. Next comes morphology. So if we think of morphology in terms of how we grade the embryo, so let's just take the inner cell mass of the blastocyst as an example. We have always been using the Gardner grading system, and it has these definitions of most cells tightly packed is an A, or maybe several cells would be a B, and very few cells. But how many cells is very few? How many cells is many? And this is where and why I believe there is so much differentiation between different embryologists grading the same embryo. And we have published quite a few papers on this, quantifying the level of differentiation. But the reason it is like that is because it's fast, it is simple, and we need that for the volume of work that we're processing inside an IVF lab. Sierr tried to solve this problem of the subjectivity by providing cutoffs, saying if your inner cell mass surface area is between 1900 and 3800 micrometers squared, that's an A. But do we have the time to do this manually? You do, and you can if you're using AI. So AI allows you, so we've done some work with Chloe where we use AI to do the Sierr grading, and the agreement with the human embryologist was around 87%. We did some independent work with Cornell, where we looked at their data set, and we were able to demonstrate that Sierr is right. There is an element of the surface area, and I always call it the Goldilocks. If it's just the right size, you're going to maximize your live birth rate, which is going to be twice as much compared to if it's too large or if it's too small. But you can go beyond just looking at the parameters that we've always used to date. And we can look at things like the roundness of the inner cell mass. So we can look at how spherical or how elliptical or the different shapes that we can get. We can also look at and ask the AI to tell us how many pronucleates do we have. And in fact, it's pretty good at differentiating between a vacuole and a pronucleate. In terms of counting the number of PNs, it gets it right about 19 out of 20 times. And we see that fairly consistently across the different clinics. But what is interesting is the fact that we shouldn't expect AI always to be perfect. We need to understand its imperfections. We need to mitigate for those. And this gives you an idea. Look, if in 19 out of 20 times I get AI to process the information and I verify it, my role is no longer to process the information. My role is to verify. And this is what I think we're doing as an evolution over time. We can look at other things. So this is Danilo Simadomo's paper, where he looked at the duration of the collapse, the shrinkage, the ratio of the embryo to the zona pellucida. I mean, we don't have time to capture these things manually, but these things have relevance. They have relevance in a fresh cycle. They have relevance in a frozen cycle as well. We can also detect anomalies such as direct and even cleavage. We can detect anomalies such as severe fragmentation. All of this automatically. So if you happen to have missed that information, it highlights it for you. So let's face it, there's many more. I didn't have time to go through the entire list, but there's many aspects that we know from publications are relevant, but we haven't been including in our decision-making. And the fact that AI can provide you these insights and highlight to you what would have missed is incredibly useful, not just for us to do our embryo selection, but also to have the communication with the patient, that personalization of what, of the reason why she did or didn't get pregnant, which helps us build trust with our patient as well. This one's an interesting graph. You have the AUC on the y-axis, which gives you the efficacy of prediction, and you have the number of the time in hours post-insemination on the x-axis. And for me, this is one of the things that proves that we should be culturing to the blastocyst stage, because you can see that the efficacy of prediction increases with the first algorithm, which is looking at the morphological aspects of the image. that's the blue line, or in the green line, the morphokinetic aspects of the embryo development. So the morphokinetic being the pace of embryo development. What Chloe does is it takes both of those algorithms and uses them as inputs and creates a whole new algorithm to determine whether this embryo will implant or not. And this graph shows you how the synergistic capabilities of doing it in this manner really works. It also allows you to reverse engineer when you're getting a score to understanding why. Is it because there's an issue? So it's a way to resolve the black box situation where we can understand it in biological terms. If you get a low score, it will tell you, well, this was what came from the input of the morphology. This is what came from the input of the morphokinetics. And we can start identifying specific anomalies associated with that low score. AI is not here to compete with the other tools that we have at our availability to make embryo assessment. It's here to complete them. So by bringing together each of these tools that we have at the moment, all of them have disadvantages in terms of invasiveness, consistency, and the timeliness. And AI is able to bring these benefits to make those individual tools better. In fact, I believe that we should always have as much information as possible on the embryo to make the most educated decision of what's going to happen to it or what should be happening to it. And the biology of what comes from PGTA result, the morphological aspects or the morphokinetics are very different. And it's really in the intersection of all three that we get the benefit of identifying and be able to fully quantify viability. And we believe that this can be put together in simple terms. Remember, AI is about bringing simplicity. We can now bring time-lapse genetics and your morphological aspects together in simple reports, scoring, taking all of it into account as one. But here's the big question. Can AI improve clinical outcomes? So PGTA is associated with reduced cumulative live birth rates. This was a really interesting paper that came out last year, where you can see in red are the PGTA cycles, in blue are the non-PGTA cycles. And we can see that there's a reduction in, I'm going to be fighting with my slides all day. So you're going to stay. You can see that there's this reduction in live birth rates. Yeah, not just live birth rates, but cumulative live birth rates. Okay, so the question is why? And there are 4 ways that AI can help resolve this challenge that we're seeing within the PGTA. So firstly, which euploid should we be transferring first? We know that 30 to 40% of euploids don't implant. So this is what work that we've been doing with Kathy Miller in the US. And we've looked at each of the morphokinetics, which is the x-axis, against the hours post-insemination. Now, these are euploids of very good quality. These are all A and B in terms of the quality of the blastocyst. They're all fully expanded. Okay, these are also euploid. Within these, we can identify ranges in the morphokinetics where no live births occur, despite the embryo passing every other element of quality. We can also look at creating 3 categories, one being your optimal implantation rates, one being your suboptimal, and the one which is 0, which is the red. So that green area, we split it into those 2 blue in the graphs. And when we're looking at the pace of embryo development, we start seeing differences between those that lead to live birth and those that don't. This is AI working together with PGTA, working together with time-lapse to create a solution. What about the mosaics and inconclusive and what I like to call the gray area embryos? How do we know which one to transfer or not? If we have another element of assessment of this embryo, we can make a better educated decision. That doesn't necessarily mean we need to rebiopsy an embryo. Warm, rebiopsy, refreeze, it's a lot of work. So we also have to look at avoiding biopsying fragile embryos. There's a whole question of, are we harming some embryos? And here's is where AI can help us identify going, look, for these particular embryos, there's a possibility it's euploid, but biopsy might not be the best thing for this particular embryo. So I believe that there's a lot of opportunity there for AI to support us. And this is the biggest one for me. Everybody focuses on how I'm going to use AI to select the best embryo for transfer. I am personally more interested on what is the embryo I should not be discarding. I believe that we are discarding a lot of embryos that should have been used in treatment. because we've set a criteria where we only do A's and B's. I can tell you now that a lot of C-grade embryos lead to beautiful babies. I think it was you who coined ugly embryos make beautiful babies. So great phrase. Ugly embryos, yeah, make beautiful babies. And Charles Borman covered this quite nicely, as well as Daniela Gilboa. So we have this is well documented, that the inconsistency in how we're classifying our embryos is potentially discarding, leading to discarding of viable embryos and impacting on the cumulative live birth rates for our patients. We also have the several publications from Sima Domo. We have, it's great that I can mention the names of the people who are here as well in the room, you know, Dean Moorbeck, who are really telling us, look, yes, these poor quality embryos have a reduced chance of viability, but discarding them reduces the cumulative chance in a significant manner, especially for your poor prognosis patients. So how should we report outcomes in reproductive medicine? So this is a really nice paper that I'm just going to summarize very briefly. If you have this example patient where she goes through 3 egg collection cycles, and she has 7 embryo transfers as a consequence of that, and she has 9 embryos transferred across those 7 embryo transfers. When we look at how we define it, the Americans use SARTs, the British use the HFEA. We have very different definitions of what constitutes success. And my concern is that most of these are looking on a single cycle basis, when we should be looking at a patient on their entirety of their journey. So I'm just going to give you an example of how AI, or any other embryo selection tool for that matter, can help improve the journey of the patient without necessarily improving your live birth rates per cycle started. So here's an example where embryo assessment can identify severe anomalies, and you can start telling the patient, you know what, let's just go straight to donation, skipping the need for the second cycle. Or maybe we can avoid transfers of embryos that we know have a futile or 0 chance of implantation. Or we can improve the embryo selection to go straight to that transfer that she needs. Instead of having 3 egg collections, she has 2. Instead of having 7 embryo transfers, she has 1. Instead of going through 9 embryos, she has a single embryo transferred. And this is a much better journey for this patient to go through. Now, if we're going to look at how live birth rates are improved, this is only going to happen with any embryo selection tool if you have a viable embryo in that cohort. And secondly, if the proportion of viable embryos is lower than random selection. Okay, so this is a mathematical concept, but this is something to take into account, that the way that we're running our clinical trials is not conducive to getting the answer of the benefit of how these technologies work. And this goes for all embryo selection tool trials at the moment. And what we need to look at is beyond. Let's say that patient who has no viable embryos in her cohort, she can still benefit from having an understanding of the prognostic factor. What is the chance of this particular embryo? So almost done. I got the message. Last point I want to make is the fact that the patient having access to the information. I'm a big advocate for that. I do believe that we should have the transparency, and I have run enough focus groups speaking to patients that this is in fact what the patients want. Come to Esri, to the talk from MB. So we worked on this together, where we have shown that an empowered patient does have an increased chance of having a live birth at the end and a reduced chance of having a cancelled cycle. So we compared patients who used a patient application that empowered them against those that didn't. And that was a very interesting outcome. And we're starting now to see, these are pilot studies, but starting to see improvements in number of cycles leading to until you get to your first baby. These are coming from the US, and we'll be presenting this at ASRM. Last but not least is the possibility of using these automatic KPIs coming from your AI assessment, and it can tell you when you have a problem before that problem impacts on your success rate. So there's also indirect ways of how your clinical outcome can be improved. So just to finish off in conclusion, AI's ability to process large data sets and simplify into useful insights, its ability to do accuracy and consistency, detect operational anomalies through live continuous KPIs, and its ability to engage and empower the patient. All of these are going to help us improve clinical outcomes through those 4 manners below. Thank you very much.
Thank you. Can you stay here with us? And we are going to move to the second presentation, make the question at the end of the session. Christian?
It's my great pleasure, actually, to introduce a friend and sparring partner of mine, Dr. David Grimes. Had many occasions where we've been on the telephone to each other talking about the topic that he's actually presenting today. So he's going to share insights into AI in PGT. Take it away, David.
Thanks, Christian. It's lovely to be here in Rome. Shame I can't stay longer. Beautiful city, and it's good just to be here. So Chris Hickman's just given a great talk on how we can integrate lots of data points. The ultimate outcome of AI, I'm going to narrow it back down to one very specific application of PGT. We at Cooper believe that there's a lot we can do to change fertility care for future generations to come. That's the whole point of IVF, is to generate future generations. So really, I just want to remind everyone what PGT is, how we got to PGT AI to remove the subjectivity, and then we'll get into some clinical benefits. But just to remind everybody, really what I'm talking about here with PGT AI is the PGT-A and the PGT-SR. These are copy number PGT embryo testing. PGT-M is looking for your monogenetic disease, things like cystic fibrosis, looking for affected children, where you may run PGT-A over the top, but primarily the patient is fertile. They just need, they're trying to avoid an inherited disease. So we developed PGT-AI for the PGT-A and the more accurate PGT-SR. So we all hope that all of the embryos are these nice, beautiful euploids with a nice normal chromosome copy. And the whole reason PGT-A was invented was that we know from natural fertility, one of the leading drivers of miscarriage and failure to implant is actually chromosomal abnormalities. So we've known this for years and years and years, but here I've highlighted a trisomy 10. If you have a trisomy 10, there's been no reported live births of a child with a trisomy 10. So if you have that in your embryo, it's never going to make a live birth. This was the whole point of PGT-A. Again, as Chris has just said, let's avoid those avoidable transfers. Don't transfer an embryo with a 0 chance of success. So when I got into PGT and embryo testing back in 2008, it was a very different world. It was a single cell taken from a day 3, 8 cell or a polar body. Everything was black and white, euploid, aneuploid. Who needs AI to make a nice decision on something that is that straightforward? But what we have now we do day 5, day 6 biopsies with 5 or more cells, is this mosaicism, which is a talk in and of itself, and a debate that's still raging 5-6 years after it started. But we wanted to really be able to delineate a lot more between the euploids, the mosaics, and the aneuploids. So when I started, and I used to call PGT-A samples, it was subjective. Like, again, we've seen in multiple talks today, you show the same data to 3 different people, depending on what they've seen before, how much training they've got, how cautious they are. They're going to make changes in how they see that data. So that's your kind of typical subjective. And in our world, we used to get 2 or 3 people to call that profile and come to an average. So we wanted to get away from that. So typically, you set your own thresholds. End users required a lot of training. We work in an ISO environment. They have to go through a lot of training, the same as embryologists. Standardization as close as you can. But then we used to do a lot of manual reporting, and you will all know every time you transfer information from one piece of paper to another piece of paper, you make mistakes. We're human, we make mistakes. AI makes mistakes. It's not allowed to make mistakes. Computers are held to a higher judgment than people, but we were trying to remove as many mistakes as possible. So this was an old typical PGT-A sample. that we used to have to manually call, and you get these blips in the data. All you've got to go on is a theoretical normal and some data moving away from it. And some poor soul had to decide if that movement was clinically relevant and could affect the patient's chances of an outcome. And we used to sweat over this. And ultimately, a friend and colleague, Tony Gordon, who's the clinical director at the time, had to sign off on the report. Now, if you're the person who's deciding that patient outcome, you want to avoid a negative outcome. And so the person signing the report tended to be more conservative because they didn't want to be held to be the person that has ultimately decided it was a good embryo and the patient has a negative outcome. So you get this subjective. Now, some things, this is a male embryo, X and Y, and I'm showing this for a very good reason. Stuff like that, very good, easy to call, no issue at all. But you can use some of these others and just see the things that we were forced. Is this a mosaic chromosome 20 or not? There's no statistics. It was a manual visual interpretation based on knowledge. Now, we are a large firm. We're a global firm. We have, we process about 140, 150,000 embryos a year now. And we're fortunate that we get live birth outcome data from some of our collaborators, and that's how we were able to build AI. But this is just a neural network showing how with training, at the beginning, you can train it to the truth. Turner syndrome, monosomy X, normal female, 3 copies of X, XXY, full triploid, but with a Y component, normal male, XYY. Just as an example, you train that set. We've had so many AI talks this morning. I'm not going to go over how you train data, but that's basically what we did multiple times. But we, as I just said, we have live birth outcomes. So AI is supposed to be built off the ultimate that you can, and we had this discussed this morning, the ultimate end result of IVF is hopefully a live birth. So we were fortunate, we were able to go back and get live birth outcomes from embryos that we had reported as euploid, track them back. Did they have a sustained pregnancy or a live birth? Sustained pregnancy is more than 20 weeks at this case. And then we validated that against 10,000 embryos. Now, that took a lot of work, but what we really wanted to do is get the most accurate data we could. And what we did as well is automate the whole pipeline so that when the analysis, when the embryo biopsies come to us, by the time they enter the sequencer to the time that they end up being reported, there is no human intervention. We've taken out all human intervention and rely exclusively on high-power statistics to do all the calling of the embryos. Now, this was the first time this had been done for PGTA. We used to do it when we had a non-invasive prenatal testing service, NIPT. That's all done on automated algorithms as well. Nobody looks at that data. This was a massive leap of faith for both us and the recipients of this data to think, I'm making a decision on that embryo with no human ever looking at that data. We're going to rely exclusively on the statistics, and that is it. This wasn't a tool. This wasn't an assistant with a human then validating it. This is completely automated AI, no human intervention. Then we get our reports. We do double check the report. You'll be glad to know. Check that the patient record has come through properly. It's the right patients, the right data. But other than that, that's the only time the data gets looked at. Again, we've heard a lot today how AI needs data. So we've been innovating and iterating. So sequencing, we use NGS, Illumina-based NGS sequencing. And we're now on the big beast of an NovaSeq. But when we launched PGT-AI in 2018, we did 1 million reads, 36 million base pairs. We now do 800 million base pairs. That's a huge amount of data for an algorithm to sift through, sort, and get better data. And this is all we're trying to do. We're not just trying to sequence more because we can. We're trying to get improvements in outcomes. So we are a global company with multiple service labs. We wanted to bring consistency. So it doesn't matter where your samples go. It doesn't matter who's on duty. They're not tired. They're not in a rush. It's all going to follow the same process, and you're going to get the same report at the end of the day. So we were really looking to standardize care for these patients, remove the human element. So the other thing that we were able to do is incorporate single nucleotide polymorphisms, which gives us 2 markers for detection, both normal copy number, but also your inheritance patterns, and that allows us to see the origin of the aneuploidy. So if your embryo has, say, a monosomy 18, we can see whether it's come from mum or dad. It does require the parental DNAs to confirm that. But really, this is the whole point of it. Science is wonderful, AI is wonderful. What we need to get to is improved outcomes for patients. So we were delighted that we could start to see, we were actually, by more robust methods, reporting more euploids. Now, you can report anything as euploid, it doesn't make it euploid. But we were reporting more euploids, we had fewer mosaics, and fewer aneuploidy, which comes back to a point Chris was just making about not over discarding embryos. You don't want a technology which is potentially causing embryos to be discarded that were a potentially viable child. So we're still collecting outcome data. This was published first at ASRM in 2022. There's just been a follow-up paper that's been brought out in February 2023. But this is really what we want to see, and this is where we want to see AI playing out. This is a single center study, let's hold our hands up to that. But, and it's an all-comers in the US. I'm sure many of you are aware there's a very high PGTA utilization. This is an all-comer center. You have to opt out of PGTA rather than opting in. So what we saw here was for an implantation rate of embryo scored euploid. These are all scored euploid, by the way. There's no embryos labeled mosaic. This is pure euploids. That with a subjective, our old technology, they were getting about an 80% implantation rate. And that hasn't changed much between our old methods and the new methods. But what we are starting to see is actually that implantation being carried through. We have a much lower rate of early pregnancy loss and miscarriage. So when we're calling it euploid, it truly is, it seems with this extra data we find able to discriminate a true euploid and a true highest chance birth from some of the other noise and some of the other artifacts. So here we can see a real big reduction in this early biochemical loss, and that's the biggest driver then for your statistically significant increase in live birth rate. So the patient journey, fantastic. They've got embryos, they have a transfer full of hope, they get a positive pregnancy test. One of the most discouraging things for anybody, and it doesn't have to be an IVF patient, is miscarriage. It's a real emotional barrier to future treatment. So by being able to reduce that miscarriage, reduce the pregnancy loss, for us, and for me personally, I think that is one of the biggest benefits, and one of the things that we should really be striving to improve in IVF is reducing miscarriage, because it is such a massive emotional and cost burden to the health service. In real numbers, we saw an increase in a decrease in biochemical loss rate, massive decrease, and this relative increase, relative decrease in spontaneous abortion rates, which was great to see. And I mean, this is a phenomenal live birth rate of 70% per embryo transfer. Again, single center, but we are seeing that kind of number replicated across other clinics. So where can we go with this? Well, we continue to innovate. As we're doing more and more sequencing as the cost of NGS comes down, and we think that that will just continue to improve. But what we do need for all of these, not just us, all of us need to work as a community to gather, and I was talking to Christian about this over lunch, but we need outcome data for all of this work. All of us as a community have a duty to help future patients by providing outcome data for what we're doing today, because that's the only way that we will improve. What we can also do as technology improves is get down to some of the more clinically significant changes that we're not yet able to detect. So we know that, and this is what non-invasive prenatal testing has tried to do, is there are certain clinical conditions which are de novo, they're called microdeletions, microduplications. They happen maybe in 1 in 200 pregnancies, 1 in 500 pregnancies. We're getting closer to be able to detect those. We had an interesting case very recently where a patient had a pregnancy from an embryo that was called euploid. It turned out to have DeGeorge, which is a microdeletion. They weren't sure if all the embryos were affected or not. There was no way of testing for that. So they then went into the next transfer, unable to know, and just have to take the hope that it was a really unlucky event. We're getting much closer to be able to test for that and remove another area of patient abnormality, patient concern. I think where we're going to end up, and this will only again come through large data, is do we start to sequence embryos at the whole genome level, or at least the whole exome level, and almost remove the need for PGTM, which is where you have apparent inheritance patterns. What if we could screen embryos directly without the need for parents for these genetic conditions? Again, as we get better at PGT and better at AI, we will be able to do a lot of these things. So with that, I've hit the time. Thank you very much for your attention. I'm happy to take questions.
Thank you, Christina and David, for a very nice presentation. I think we have a little bit of discussion here. I will start with 2 questions. I'm sorry, but it's like, I don't know how much time, but I want to ask this question to experts. We heard this morning, and we heard also during your presentation, especially Christina, but we have some algorithms that are predictive, but are accurate in selecting embryo or in guessing which is the best embryo or the embryo that is not going to make it. But when we see the AUC in the different papers, they go from 0.57, this morning was 67, 0.71, the best I heard. And the claim was this is accurate way because it's statistically significant compared to an embryologist. But can we say that something is accurate when it's 0.7 AUC? Where female age alone is more powerful than the algorithm per se? Can we make a decision on discarding that embryo, transferring that embryo first on 0.7? And then the second question, that I don't make any other question, is when people are claiming about algorithm that works in their lab and don't work in other lab, but they are not, but you cannot replicate, so they are not standard. And for me, if something is not standard, we are not going in the right direction. And there is a lot of suggestion in the literature, you should test your algorithm on your own data, on your own labs. So for me, this is the opposite of what we are talking today. If an algorithm is not working in every single lab, is not taking into consideration of the differences between labs, is not the direction of standardization and harmonization that we are looking for. Sorry for the 2 comments, and I would like you to.
Sure. So on the first one on the age, we've done a project recently. It's under review at the moment, where we looked at if you're trying to choose embryos that are sibling embryos. Most of the algorithms in the market add age as one of their inputs. The issue is that all the sibling embryos have the same age. And because age is such a strong predictor, it masks what is the individual embryo assessment. AI will take shortcuts. It will look and say, age is a good predictor, I'm going to use that, okay? When in fact, we found that we are better overall in the prediction within those sibling cohort if age is not included. And we focus only on the image, and we force the AI to look at only the image. Okay, so this is something that we need to understand how, especially when you have a particular weighted factor. So age is an example, the inner cell mass is another. There's many aspects that are heavily weighted. We need to train the algorithm in a way that we're taking that into account. Okay, so this is something to answer the first question. The second one was on the valid. Do you want to respond?
On this point, I think the randomized control trials that have failed to find any significant difference in using an algorithm is because they could not differentiate embryo within the same cohort. It's exactly what you're saying, no? Because when you use a randomized control trial and you try to select within the same cohort, if you have trained your algorithm on the age, it's going to mask. So very interesting observation.
And version 1 of Chloe was based on age, and then it was removed later on when we were doing the ranking. So it's something that we learned over time. And it was surprising because when I was told as an embryologist, of course, age needs to be put in there, you know, and I had to have a mathematician explain that to me. And this is where the multidisciplinarity of AI, I love that part. The second question you had was on validation, okay? Or at least the answer to your question is validation. Yes, we have done these studies, and those are results of validations that we've done in each individual clinic around the world. But the biggest risk that comes from AI is bias of the data it's been trained on. Okay, and for that reason, I do believe that you do need to test it with your specific data before you start using. I think that's very important because it might be that you have a particular type of demographic. It might be that you have a particular type of clinical practice. That means that that algorithm might not work as well in your clinic as it does elsewhere. And the only way for us to mitigate that risk is by testing in each individual clinic before they introduce it in clinical practice. And I believe all the AI companies that we have here do that validation. So there's a very responsible approach to AI that we have in the moment compared to how previous technologies were introduced in the past, where we've been disappointed, promises that weren't fulfilled.
Being commercialized, maybe you have to make this kind of validation yourself and not ask the clinic to do it. I'm not sure that clinic are able to do it.
Yes, so I showed you all the work that we're doing. I mean, we've done 90 different projects in the last 18 months with different clinics from around the world. It's an extensive amount of project. I don't believe that the traditional RCT that we use for efficacy of drugs is the same model we should be using for AI. I don't think it's the same one for PGTA either. So I think, and what I described before, where we were looking at a single cycle in the patient when we should be looking at our whole journey, RCTs can't take that into account because that's just not easy. It's not practical. And this is where we're drawing, in my opinion, incorrect conclusions on some of the embryo selection tools in the market. But I appreciate that this is a hot topic and we all have lots of opinions on it. So I'd love to hear yours.
Well, yeah, I think this whole thing is based on individual versus group. So I've just spoken about PGTA. That will give you an indication in terms of its genetic status. Age, obviously, when you come to the transfer, is going to have an effect, as Chris has just pointed out. Morphology on top of that. They all add together. We know that euploids don't work as well, even if we can't see the difference. As maternal age increases, what looks like an identical embryo doesn't work as well in an older patient. There must be some female component, not beyond the level that we can see today, affecting that outcome. So we need a way of pulling all of this data from all the different tests together. And there was a talk this morning about running different AI algorithms and merging the output to get that predictive outcome. And that's where we need to be. I think the biggest issue that we face, both from what Chris has said and various others, data entry today, both in the individual clinic databases and also in the public databases like SART and the HFEA, are not organized in a way which allows us as a community, both commercial and as clinics, to pull that data in a way which makes it clear which treatments, be it PGTA, be it different stim cycles, it's not organized or in a publicly accessible way that we can then mine it to find out the truth. Data is only as good as the people putting the data in. And we weren't thinking, rightly enough, 20 years ago, oh my, but wouldn't this data be fantastic in 20 years' time if we stored it in this way? So we're now having to try and generate a lot of prospective data to try and validate our assumptions. And it would be fantastic if we could agree how this data should be stored and what should be stored, and try and think into the future what data might be useful to help patients, rather than us now trying to think, oh God, I wish I'd recorded that. That would have been fantastic, because we just haven't done it.
I have a question for Christina. And I mean, your presentation was really dense because, I mean, we're all, the majority of us here are embryologists, and I am one. And so when I think about actually coming here, thinking about AI, I was thinking about how can we use it in the lab, and honestly, strictly in the lab. But then you can actually use AI to organize large sets of data, not just in the lab, but also for, as you were saying, informing patients or using the data you have in the lab to make clinical decisions, and also informing patients. And so you have these different levels of use of AI in the clinic. And I have a feeling that right now, the use that we can do in the lab to improve our pregnancy rates, I mean, are yet to be proven. Like, there's still a lot of work to do. So my question is, right now, you said you own 2 clinics in London. The first question that comes to mind is how right now a lab that is not using AI, or a clinic that is not using AI, can benefit the most from using AI, in which kind of setting? Is it the lab, or informing patients, let's say organizing KPIs? If you have to pick one, which area would you say right now would be the most valuable where to invest?
You're not going to like my answer. I do believe that we shouldn't be picking one. And I think this is the problem with our current AI direction. We need to get the complete picture. And this is why we're building avenues where we're using AI on the uterus, using AI on the endometrium, we're using AI on the embryo, we're using AI on the patient demographic data they're bringing in. Our next project is to build the overarching AI across that, and that doesn't exist at the moment. And that is what we should be striving towards. I don't think the solution is to pick one. I think the solution is we should be going for AI-driven decisions all the way through, because I believe that is the true evidence base, is true data-driven decisions, not based on opinion. So I wouldn't pick one. I think I would strategically make sure that we don't have siloed AI. So just to add, that's why you have the AUCs of 0.7, because if somebody's presenting to me AUCs higher and you're only giving me the embryo side, I'm partially not going to believe it, because the embryo is only part of the story.
I did have a question. I'm going to perhaps just pose a thought, because we've run out of time. It's very much in line with what you've both said, is that there is really a missing link. And I think that that's really evident. We have to understand what is the limitation, what are the limitations of AI in the lab at the moment. And I think the fact is that we're only analyzing one aspect. We're only looking at one aspect. And I take the analogy that I had a discussion with before. When we're looking at the embryo, simply looking at the phenotype. Phenotype is genetics and environment. We need to understand the genetics and the environment to understand what the phenotype means. So when we can put those 3 things together, then we really will have a solid AI platform for decision making in the laboratory. Till then, it really is just a standardization. I think a good standardization, something that we should embrace. But I think certainly from my perspective, and perhaps just concluding comments, because we've run out of time, is that I think that's where we stand at this point in time, if you agree.
Yeah, I'd agree.
Last question from the audience.
Okay, now we will stay with artificial intelligence, of course, but finally we will try to see the situation from another point of view, from a clinical point of view, instead of more biology point of view. So welcome, and a big thank you for Sierr, because the organization is really fantastic.
So, good afternoon. It's a pleasure for me to introduce the first speaker, Michelle Perugini, and she will talk about how can clinics evaluate, use, and communicate artificial intelligence.
Hello, everyone, and thank you so much for having me present today. Despite my surname, you might think I'm Italian, but I have a very Australian accent, and I'm hoping that the AI auto prompter can understand me. Today, I want to talk a little bit about not just, the science behind using AI in the embryology clinic or in the lab or in the clinic, but how do we evaluate and use and then communicate those results to patients? Because I think that's really important. These are the disclosures. We're working with Fujifilm as our distributor in global regions currently. And my background, just for those of you who don't know me, I'm a stem cell biologist and geneticist by trade. But I have spent 16 years as an AI practitioner. So I've got a bit of a blended background, which is quite interesting for this kind of combined clinical and AI space. So what I want to talk about today is kind of the revolution of AI and IVF. How are we using this? How are we evolving our current methods in the lab and clinic? How do we evaluate and test the AI effectively? And how do we use those results effectively within the clinical environment and interpretation of those AI? So there's a whole range of different use cases. I'm sure we're all familiar with many of these, but just as a bit of an overview, I should have worn my glasses. I can't even read the prompter down there. But being able to predict the outcomes of IVF patients, or the likelihood of an IVF patient achieving success in 1, 2, or 3 cycles, there's some applications there. Looking at stimulation protocols, optimization of the hormone treatments for our patients. Looking at oocyte assessments and other automation of just routine operational areas within the laboratory is a big area. As a company, Life Whisperer, we're working on the last 4 at the moment. So we're looking at embryo quality assessment. Actually, it was a really nice segue from Christina's talk and David's talk. We're looking at both the viability of embryos, but also the non-invasive genetic assessment of embryos, because we think they're both core components of embryo quality. And then oocyte quality assessment, and finally endometrial receptivity using AI and imaging. So it wouldn't be a current relevant talk if you don't use a ChatGPT analogy. So I asked ChatGPT to come up with an analogy of AI and IVF, and I ended up with a cake, which is interesting. But what it said was AI and IVF is like having a baking assistant who can analyze all of the ingredients and variables to suggest the best combination for the perfect cake. Similarly, AI can analyze the complex interactions between different embryo characteristics to suggest the best embryos for a successful pregnancy. And I thought it was quite interesting because, whilst we know a cake has sugar and flour and all the other kind of ingredients, it's a real art of how they all come together to make the perfect cake. And it's kind of the same with embryos. We can look at the macro level features of an embryo and we can assess whether it's expanded and whether it has an inner cell mass and the general quality measurements, but it's really the complexities of the patterns that we're not able to really assimilate as a human. And that's what the AI can do very well. But when we look at kind of applying these types of technologies within the laboratory or the clinical environment, I think we've got to kind of consider all of the actors that are involved. On the one side, we've got the clinicians and the embryologists who their ultimate duty is to the patients. They're working in a time poor environment. They're wanting to get the best possible outcomes for their patients. And, it's a difficult environment for them. They need to increase their operational efficiencies to be able to service their patients efficiently. On the patient side, they want access, they want the treatments to be affordable, they want the best possible success rates. And I think increasingly they're wanting more transparency. They don't want someone to give them hope through an IVF treatment. They want someone to manage their expectations and help them understand the likelihood of achieving success through that process. And I view AI very much as a tool set that sits between those two different stakeholders. It's not replacing the clinician, it's augmenting the clinician, or the embryologist in this case, ability to better service patients and improve outcomes for patients. So when we're talking about evaluating AI, what do we need to consider? I think the first thing to consider within a lab or clinical environment is, does a function actually suit what I need? You know, is this going to help me in everyday life? If it's not, then you probably shouldn't move any further through these metrics. You know, has it been built with sufficiently diverse data? So we've talked a lot about in the talks this morning about the quality of the data, the sufficiency of data sizes, and this just cannot be understated. If you do not build AI on sufficiently diverse data that represents different clinical environments, different patient demographics, it will not generalize and scale to different clinical environments. Simple as that, there's no shortcuts. It needs to be built on the right data. Has it been validated and blind tested? Are the studies published? Are they on sufficiently large data sets? Have they been tested in different clinical environments? So it's very easy information, or a very easy way for clinics to assess the AIs that they're interacting with. Does it meet the regulatory and data privacy requirements? You know, of course, GDPR, HIPAA, you know, all of the regulatory requirements for these tools are fine. But I think it's important to ask the questions around, where does my data go? You know, who gets access to that data? Who owns that data? Because I think those questions are really important for clinics to decide. And then, of course, is it easy to implement? Is it going to take a lot of time? And is it cost effective? So with Life Whisperer, our view is very much a platform approach to AI across the whole process. We have started with embryo viability and embryo genetics as our first two assessment types. They're commercially available in 48 countries now. We've got clinics all around the world using the technology, which is very exciting. But we're also looking now upstream at oocyte assessment and some other sort of more clinical areas, and also downstream at endometrial receptivity. And we, you know, there was a question on the previous panel around why the AUCs aren't high enough. It's because the embryo is only one component of whether a patient achieves a pregnancy. So we think that we've reached the theoretical maximum accuracy you can get for AI embryo selection without taking into account the endometrium. So this is where combination of these things is going to be really important. So just a little bit about what Life Whisperer does now. We are available in Europe, we're CE marked. Essentially, this is a static image assessment. This is an endpoint analysis. So this is very different from the time-lapse. You do not need time-lapse to use this AI, but you can use time-lapse images if you prefer. And essentially, you drag and drop images of day 5 embryos, and within 10 seconds, you get 2 assessments. One is the Life Whisperer viability assessment, that is the likelihood of an embryo achieving pregnancy. And the second assessment is Life Whisperer genetics, which gives the likelihood of an embryo being euploid from the physical morphology of the embryo. So this is kind of what it looks like. If you try and interpret what those scores mean, it's basically a sliding scale between 0 and 10. So the viability score, the higher the score, the increased likelihood of achieving pregnancy from that embryo. Simple as that. You use it as a ranking tool. If you've got 5 embryos, you pick the one with the highest score. Very simple. And we've shown in many, many studies, and I'll show you some of them, how the scores correlate with pregnancy outcomes. Same with genetics. Higher the score, the higher the likelihood of an embryo being euploid. All of the, as we've heard in the previous talks, all of the segmentation and annotations are all done automatically in the system. You don't need to do any pre-processing of any of the images. Our AI is actually a combination of a whole range of neural networks that look at honing in on different parts of the embryo that we know to be important developmentally. So the zone of pellucida, for example, we look at central components, the ICM and the TE, and those scores that you get are basically an aggregation of all of the neural networks coming together. We know that Life Whisperer detects known features, so it correlates very strongly with Gardner grading and all of the factors that you know and love, but it's also identifying other things. And where the AI disagrees with Gardner grading, the AI is about 3 times more accurate at predicting that outcome. This is just an interesting little study that looked at surveying of 158 embryologists across 20 embryos. And you can see the scores of how many they correctly predicted would lead to a pregnancy on the right-hand side there. And aside from one embryologist who actually got a score of 15 out of the 20, Life Whisperer achieved 14, and you can see there's kind of great variability. So subjectivity is a huge issue. What's interesting is Life Whisperer AI, it's not looking at those few individual factors of embryo grading that we normally look at. It's predictive even within those subgroups of different quality embryos. And if you look at Life Whisperer viability, the sensitivity for viable embryos is between 70 to 90% within each of these subgroups, and for genetics around 60 to 95, depending on the data set. So there's many studies, I've picked a few here that just show the key kind of scientific studies that we've done. This is our original paper in Human Reproduction from 2020. Around 9,000 individual cases, single embryo transfer cycles, 11 different clinics across 3 countries. And basically we showed a 25% increased accuracy for pregnancy prediction, comparable to using standard Gardner grading. We've also done some really sophisticated ranking studies, which are really interesting, and I would urge you to read this paper if you haven't already. It's really rich paper looking at many correlations with morphological characteristics, but also time to pregnancy calculations. Using this as a ranking tool, can we reduce the time to pregnancy by virtue of selecting the healthiest embryo first time in simulated cohort studies? So this was around 9,000 images, 18 clinics across 6 countries on a different timescale, more recent. And it did correlate with a 12% reduction in pregnancy outcomes and time to pregnancy comparable to kind of a random ranking analysis, which is really exciting. Life Whisperer genetics. So we've shown around 82% probability of selecting a genetically normal embryo. You can see on that graph there. And again, the paper's got a lot of rich data, but I don't want to kill you with data today. But you can see a really nice correlation between the scores. So the higher the score, the higher rate of embryo euploidy. Life Whisperer genetics is also predictive of live births. So we're tracking out our outcomes all the way through to live birth. We think that's really important. Although there's always a natural drop off, there is a really nice prediction with Life Whisperer genetics and live birth. This is my favourite study. This is a new study. It hasn't been fully published yet. This was an ASRM abstract that was presented last year. And what this shows is that Life Whisperer viability in genetics, we always know, well, I've always known that there's a genetic component and a morphological component to embryo quality. A euploid embryo can not implant, and an aneuploid embryo sometimes implants. They're 2 different kind of equations and 2 different sides of the embryo quality coin. So what this study showed is that the use of Life Whisperer viability and genetics AI together can actually double the reduction in the time to pregnancy, because you're getting a better picture across both genetic and morphological viability assessments. So now I'm going to switch gears. That's all the science. I guess one of the important things, and it was raised in the last panel, is, you know, does this work for me? So as a clinic or a lab, I think it's really important, as Christina mentioned, that you're able to actually test these things in your own hands, right? The scientific studies show that they're generalizable, and you can use those studies to get general comfort around the technology, but I think you need a way to be able to test it yourself. So what we've done over time is kind of develop this validation study outline. We work with every clinic that wants to do this to be able to implement their own kind of mini validation, if you like, of the technology. It's very quick and easy. It takes us about 5 minutes to set you up on Life Whisperer. There's no time-lapse imaging equipment or no extra things that you need in the lab. Or if you've already got time-lapse, you can use those images. So it's super easy, and I think this is a really nice way to guide you through that validation process. Now, this is a bit of a busy slide, but I think it's important. So if you're trying to aggregate multiple AIs, you need to know how to use them together effectively, because otherwise you get the situation of, well, what if it's got a high viability score and a low genetic score, a low genetic score and a high viability score? Which one do I weight more heavily? And of course, you can set up your own kind of standard operating procedures about this, but, you know, these are ranking tools. So the way that we normally talk to clinics around this is, you know, obviously the top embryo is one that's got a high score on both metrics. The second one, we always prioritize the genetic score more highly because, you know, you want a genetically normal embryo, and then you obviously want to achieve a pregnancy with that genetically normal embryo. And then the third down the rank would be, you know, a high viability score with a low genetic score. And then I think it's an important point that you need to counsel patients around whether they might do PGTA testing as a confirmatory measure for definitive genetic assessment. And then, of course, the lowest is low viability score and low genetic score. And what's important here is even if a patient gets a low viability or a low genetic score, there's still a proportion of embryos within those categories that become pregnant and are genetically normal. This is not meant to be a binary yes or no. This is meant to be a ranking assistant. So, you know, it's important to be able to explain the results like I think all of the other AI companies have recognised. You know, we all have these patient reports. I think they're very important. They've got a little explainer of what it means, what the scores mean, how many embryos within each scoring category, you know, what your expectation of outcome is with each of those assessments. And I think that's really critical. Patients want that transparency. So just overall, that's a very abrupt timing prompt. It's kind of like, so basically, you know, the benefits are obviously objectivity. So standardization, really important. The fact that it's patient friendly and you can explain those results to the patient, really important. Easy to use and cost effective. And I'll just finish on this slide. We work very collaboratively with clinics all around the world. We're a very scientific team. On our Allsite project, we've got 200 clinics collaborating and contributing data in various ways, shapes or form and helping to test these algorithms and be part of building the algorithms. Same with endometrial receptivity. So if anyone's interested in collaborative projects, please reach out and let us know. We're always open to that. And of course, if you want to try Life Whisper, it's open to anyone to have a free commercial pilot period where you can run your own validation. Thanks so much.
So we can continue with the second speakers and we will do the question.
Yes, good morning. The second speech, the second presentation is from Justina Cho, iLife, and the title is Artificial Intelligence for Optimizing Ovarian Stimulation and Embryo Ranking, please.
Hello. Oh. Hi, thank you for having me. I'm Justina and I'm a data scientist at iLife Health. I'll be giving this talk on artificial intelligence for optimizing ovarian stimulation and embryo ranking. So we at iLife Health build artificial intelligence software for clinical decision support during IVF. We're a very data-driven company, so we place a lot of importance on innovation through rigorous research. Our process is to identify the clinical need and to use our data to best inform how we can meet that need. And part of our goal on the data science team and at iLife is to understand how we can incorporate AI at every decision point of the IVF journey. I've shown here many of our various research efforts, but for this talk, I'll focus on 3 topics: the starting dose of FSH, the timing of trigger injections, and embryo ranking. So Before I get into some of our research, I'd like to briefly introduce the platform. So A-Life Assist is our platform, and there's 3 components: STEM Assist, Insights, and Embryo Predict. First, we have STEM Assist, which is an application that's currently designed to help with 2 of the critical decisions made when managing a patient's stimulation cycle. The first being determining the optimal dose of FSH, and the second, the timing of trigger injections. Next is Insights, which is a tool to help managers manage and visualize their clinic's KPIs in real time. Finally, we have Embryo Predict, which is a digital embryo grading workflow tool with microscope integrated technology. We utilize an automatic blastocyst ranking algorithm, and we generate automatic reports. And really the goal is to make the lives of embryologists easier. A-Life Assist integrates seamlessly with a clinic's EMR and workflow, and our platform is a centralized tool that connects the entire team, from managers to embryologists to clinicians. Now that I've introduced the platform, I'd like to get into some of the research that makes up the core of our products. A-Life has built one of the largest and most diverse proprietary IVF data sets. So here's a brief glance of our partners who make up 35% of the US volume for IVF cycles. While we work primarily with US data, we are also currently working on a retrospective clinical study comparing US and European data. So if anyone is interested in collaborating, please find us afterwards. I'll start off by diving into our work on the starting dose of FSH, which is one of the first decisions made during ovarian stimulation. And this is the first part of our STEM Assist tool, which is currently launched at several clinics in the US. In order to understand how clinicians dose and how to optimize dosing, we analyzed a private clinic data set of about 22,000 retrieval cycles from across 4 US clinics. And one of the first things that we found was that the starting and total FSH can vary significantly between clinics, despite similar patient characteristics. So there's up to 1,000 IUs difference in the mean total FSH. This diversity ends up actually being key for our analysis, because we're able to see the effects of different doses on outcomes across similar patients. We take advantage of this diversity when building the optimal dose model. And the goal is to maximize the number of M2s retrieved while reducing the amount of drug that's used. In order to do this, we utilize a k-nearest neighbors algorithm, and we create an individualized dose response curve by plotting the total starting FSH and the number of M2s retrieved. And this is done for a patient's 100 nearest neighbors or 100 similar patients. We then created, in order to evaluate the model, we then classified all the patients based on their individualized dose response curves based on the curve shape. So generally, patients fell into 2 categories: dose responsive or flat responsive. And then we compared the outcomes from optimal versus non-optimal doses, and also the outcomes from low versus high doses. For the dose responsive patients, what we found was that patients given an optimal dose generally had higher M2s, 2 PNs, and usable blastocysts than those patients from the given non-optimal dose. So in other words, patients given an optimal dose did better than matched patients given non-optimal doses. For the flat responsive group, what we found was that patients given a low dose, when compared to matched patients given a high dose, actually had similar numbers of M2s, 2PNs, and usable blastocysts. So patients given a low dose did comparably to match patients that were given a high dose. And this finding is particularly interesting because it's widely known that in the US, clinicians dose much higher than in Europe. And here we see through our research that high doses are not always necessary, especially in the majority of patients. So these flat responsive patients make up 64% of the cycles in our US data. I'd like to take you through an example of how clinicians use the dose tool in StimAssist. So this is a snapshot of what a physician would see when using the dose tool. So we have here a 40-year-old patient with an AMH of 1.71, BMI of 20, and an AFC of 15. And the tool displays an individualized dose response curve, which shows the predicted number of M2s on the y-axis and the total starting FSH on the x-axis. We also show the cost estimate for the amount of drug used. And based on this curve, the clinician would be able to potentially maximize the number of M2s while also reducing the starting dose of FSH. And what actually happened was when the dose tool was used on this patient, the clinician lowered the dose from 450 to 375 IU. And in the end, he was able to retrieve 10 M2s, which is around what we had predicted in our dose response curve. Next, I want to talk about the timing of trigger injections. So for this work, we developed a model to optimize the day of trigger. And the way that we did this was we used 30,000 retrieval cycles from across multiple clinics. And we trained multiple linear regression models on bin follicles and E2 levels to predict the number of M2s if triggering today or if triggering tomorrow. And with these two models, we wanted to evaluate the benefit of the trigger timing system. And so for the purposes of this study, we used historical data and had our system recommend whether to continue on to the next day or to trigger. So if the trigger today model predicted less M2s today, and the trigger tomorrow model predicted more, then the recommendation was to continue. And if the trigger today model predicted more M2s than the trigger tomorrow model, the recommendation was to trigger. So we did that for all the patients in our data set, and we sort the patients into early, on time, and late groups. So if the actual trigger day was before the recommended day, the day recommended by the model, the patient was triggered early. If the trigger day was the same as the recommended day, then the patient was triggered on time. And if the actual trigger day was after the recommended day, the patient was triggered late. So they were categorized into these three groups. And then we compared the outcomes. What we found was that patients triggered early when compared to on-time triggers had less M2s, 2PNs, and usable blastocysts. And when comparing late triggers to on-time triggers, patients in the late group also had less M2s, 2PNs, and usable blastocysts. So in other words, patients with on-time triggers did better than matched patients with early or late triggers. And this is important because this means that our model is recommending a more optimal time to trigger than what had actually occurred. So we're using historical data. We're trying to evaluate our model. So here's another case example of what a clinician would see using our trigger tool in StimAssist. So here we have a patient of age 31, about 31, an AMH of 0.87, BMI of 18 and an AFC of 8. And he can see what is the trigger today model predicting for the number of M2s and what is the trigger tomorrow model predicting. And what he sees is that the predicted number of M2s today is about 5.8. Tomorrow it goes down slightly to 5.5. We also give a prediction for E2. So he sees that tomorrow the E2 level is starting to go up. The trigger tool was used to decide, do I trigger today or do I trigger tomorrow? And he decided that he would trigger on day 8 when originally he wanted to continue. And what ended up happening was that he was able to retrieve 5 M2s, which is close to what we had predicted for day 8. This tool, along with the optimal FSH tool, are used together in StimAssist and can help patients with optimizing and improving a patient's stimulation cycle. Finally, I'd like to talk about embryo ranking and our embryo ranking algorithm. So our embryo ranking algorithm makes up the foundation of our embryo predict product. So in order to build our ranking algorithm, we used images from 6,000 single blastocyst transfers and 2,600 non-transferred aneuploid blastocysts. This is from across 11 clinics in the US, and all the clinics have different microscopes and cameras, and we also include PGT and non-PGT cycles. We use this data to train a set of convolutional neural networks and incorporated metadata to rank embryos based on the likelihood of leading to pregnancy. The work I'd like to highlight in this talk uses this model, and it's our retrospective embryo AI assessment study. This is a double-blinded multi-reader study with images collected from 10 new labs. So we've never seen the images, the model has never seen the images. So 438 embryos were collected and were used to create about 1,200 virtual patient panels. There were 5 readers or embryologists, all with varying levels of experience. And the goal was that the readers would select top embryos for transfer, and so would our AI model. What we found is that our model successfully passed the primary endpoint of the study, which was to show non-inferiority. And another key finding is that in this case, A-Life's AI was able to outperform the embryologists by 8.5% when the embryologists had agreed and our AI had disagreed with them. This algorithm is used in our embryo predict tool, and in general, the goal of the tool is to bring standardization to embryo selection and to help make the embryo selection workflow more efficient. Hopefully by now I've managed to demonstrate that AI has the potential to improve clinical decision-making in several areas within IVF. A-Life has demonstrated clinical value through retrospective clinical studies and will continue to do so with future retrospective studies. We also have prospective studies currently both in ovarian stimulation and embryo assessment in the US and in Europe, and we hope to further demonstrate clinical value to both clinicians and patients. So if you're interested in being involved in this study or future retrospective and prospective studies, please find us afterwards. Thank you.
Thank you so much. Excellent presentation. Because of we are late, first of all, I would like to know if there are some questions from the audience. Any question from the audience? No question. Do you have some question for?
So thank you very much. Yes, very quickly question. Do you think that the question is for both? And do you think that this type of platform can help us to reduce the cost of the IVF treatment in a public system?
I can talk from our perspective. Ours is a low-cost solution. The reason that we've tried to create something that doesn't need equipment like time-lapse imaging is so that we can deliver that solution at low cost. I do think we've done some financial modelling around the efficiency gains within the laboratory side. And not only does the AI pay for itself in terms of the efficiency gains that you can have, but it actually makes money, because if you're getting patients pregnant quicker through fewer cycles, you're doing fewer repeat transfers, you're servicing more first cycle customers who pay a premium. So it's kind of a double benefit. You're getting more patients pregnant quicker, which is good for them, but you're creating efficiencies and a better business model on the clinic side. So yes, I really genuinely believe that AI can be a low cost solution that improves success.
I agree as well. I think in one of the case examples that I showed for the dose tool, in our dose tool, we actually provide cost estimates. And what we found when clinicians are using this tool is that in our prospective studies, that they are lowering the dose of FSH. So by lowering the dose of FSH, they are reducing the cost. And I guess to add to that, with our embryo grading tool, I think that one of the goals with that, beyond ranking embryos, is to make the workflow a lot more efficient. So if embryologists are able to get through more embryos quicker, they're reducing the time that's involved in embryo grading and working on embryos. So that will also reduce the cost as well.
I'm a clinician, sorry. So the utility of AI in embryology, in particular connected with PZT and time-lapse, etc., is quite well documented. But for example, in endometrial receptivity, do you have any data about the possible utility of AI in this field? Because endometrial receptivity depends from many factors. And so it would be very interesting for me to understand something more.
Yeah, we're so excited about this. The answer is we don't know. We don't know, right? Everything's exploratory until you prove it. So what I can tell you is we've got access to around 35,000 transvaginal ultrasound images, as well as follow-up data from the US and Europe. So we're starting that pilot study now. We've just put that through ethics approval. Super interesting study. So I think what's happened in the industry is everyone recognises that the endometrium is kind of half of the equation of getting a patient pregnant, but it's very hard to assess it. And doing an ERA test has not really shown to prove benefit. And I think the reason is because we're trying to optimize across a very small implantation window, right? Which is not particularly helpful in my opinion. I could be completely wrong. But I think what we need to do is determine whether or not at that time the endometrium is receptive. And if it's not, then we hold out and we wait. We're freezing all our embryos anyway. They're too precious to put back until it's ready. So we'll be doing a whole range of different endpoints and assessing those images and seeing what factors we can identify from the endometrium to measure its receptivity. And my view is, even if it's, initially only 60 to 70% accurate, I think that will have a massive impact on pregnancy outcomes.
Okay, thank you so much. Any question? The stage? Oh, Laura.
So I'm fascinated about, all the progress what we are doing in different steps of the IVF, but something is missing. It's how to produce a better embryo. Nobody is working. Selecting means that you have the embryos, but are we planning to have some tools to try to improve the environment in the lab to produce more and better quality embryos?
My view is they're all little bits of the same puzzle, right? So if you start looking at oocyte competence, then you can potentially produce better embryos because you can optimize, the stimulation of patients using AI and then produce better oocytes, which you can then grade, which you can then predict and produce better, embryos. by the same token, it can change clinical decisions, because you might choose, if there's a poor kind of trajectory of the cycle, you might choose to do another oocyte pickup and save the patient kind of going through that whole process and waiting. So I think it's about having a collective of information that you can then assimilate across the whole process. The challenge is, at the moment, they're all kind of point solutions that are doing bits of that process, but that'll change over time. It's just where we are at the moment.
So I'd like to add to that a bit. I think there's maybe the direct solutions. So for example, with our stimulation cycle tool and our embryo grading tool, that's very direct at that decision point. But I also want to point out, like, our third tool, Insights, that is helping to monitor and visualize KPIs in real time. I think that can help in general to improve conditions within the lab. So we're able to monitor embryologists, how they're performing, and hopefully the goal is, by looking at this or using this tool, we can improve embryologist performance across labs.
Thank you so much for your excellent presentation, and we leave the place to the third section.
Good afternoon. So welcome to this third section of the session 3. So the next speaker is Dr. Milin Yao. So Dr. Milin Yao is the co-founder and CEO that has led Unifi from technology invention and platform development to commercialization. Dr. Yao's vision is to combine healthcare of AI and scientific validation to improve women's and couple access to the most effective and safest fertility treatment. And welcome, Dr. Yao.
Thank you very much. I'm so excited to be here, enjoying this beautiful city, and really it's a great pleasure to have a chance to tell you about some of the work that we've been doing at Unifi. Disclosures. Just a quick intro. It's probably the first time that I meet many of you, that you hear about this talk. I started my career as a clinical OBGYN, did my subspecialty training in clinical infertility, grew up in Toronto, Canada, completed my medical school at University of Toronto, and went on to do fellowship in clinical infertility at Brigham and Women's Hospital at Harvard in the US. And fast forward, what we have, what I'm going to share with you is the result of academic research from the time when I was faculty at Stanford University, where I collaborated with clinicians, experts in machine learning and statistics. So it's been over a decade that I've been working on this AI as applied to IVF. And I will tell you a little bit about the full circle from academic invention to commercialization, and now to getting some clinical proof points, which are the most important. So this is a quick overview of the statistics that you're all very much aware of, probably, and also put in there, every country has, you know, their own challenges, and also the utilization of IVF is different. And from, you know, US, where I'm from, you know, access is a big problem, a lot of barriers. Probably some of those challenges are similar here. And also we have different challenges as well. So, but overall, you know, there's a really vast, IVF is vastly underutilized. Only about, in the US, only about less than 3% of people who can benefit from it are using it. And from the statistics that we could find on the internet in Italy, it's less than 5%. But I'm very interested afterwards to learn from your perspective. So what this talk is about is really how to use AI to help more people use this very successful and very effective treatment. So a little bit switching gears from embryology. And also we, you know, did some reading and learned about some special considerations that Italy is facing, such as declining fertility rates. I understand there was a big conference in town yesterday by some very famous people like the Pope talking about this issue. And so I thought, wow, if I learned about it sooner, I would have liked to go and listen to that. But I mentioned this because there is a way to use AI, and actually we're doing some of that work at Unify to really help countries that have declining fertility rates figure out strategy with public funding and public-private collaborations, how to best utilize resources if they want to maximize the number of live births, singleton live births. And we've already begun talks with some countries, and very interesting, very exciting to be able to apply AI and machine learning this way. So I just mention it here. If any of you are involved in projects like this, would love to support you in that. And these are numbers that you all know better than me. I just put it here for my own self-education. And but the challenges that we face are very similar. We basically have IVF, which is a very effective treatment, tried and true from several decades, very safe, but most people need to pay out of pocket, pay cash for this. And so for the patients, what they experience is, what they perceive is a lot of uncertainty. They may spend money and not have a baby, even if the clinic does a fantastic job. And there's no other consumer purchase like this where somebody pays money and may not get what they want. The patient wants to have a baby, and you're providing excellent treatment, which may or may not result in a baby. So how do we resolve this? And so how do we help people to feel more confident to move ahead with treatment? Yeah, so let me see, I slipped here. So what we have done is using AI and machine learning to build prediction model for predicting personalized probability of live birth. And this is a very nice, intuitive patient report that explains to the patient with a lot of transparency based on her and her partner's healthcare data, what can they expect to be the probability of live birth, not only in just one cycle, including the use of IVTs, but also cumulatively, if she and her partner could use 2 cycles or 3 cycles. And here, when I talk about a cycle, I'm referring to 1 stimulation cycle, including the use of 1 or more embryo transfers as needed. And so that is really important and is a more patient-centric way to think about it. And I think other speakers have brought that up as well. So what we find is that before, we have now many centers in the US using our system. They've used it for consecutive 4 to 6 years, and we have some long-term data, including clinical live birth data. And we also, some clinics also started using in Canada, UK, and also Europe. And so this is what we notice in general to be the problem. A lot of patients still kind of focus on IUI because it's less expensive, but you know, they might be getting more ovarian aging as they kind of delay IVF. And as you all know, IUI success rates can be quite poor. And so why does it matter? So the breakthrough is by giving patients personalized probability of success, whether it's higher or lower than they had thought, it actually increases the confidence. But the important thing that we have found is that it needs to be validated in that center. So when the doctor is counseling the patient, the doctor can say, this is from results from our own center. And so we have developed a whole framework of using AI and machine learning that does not require massive amounts of data sets from multiple centers, a need for harmonizing across and needing time to build. We really focus on working with 1 clinic at a time and using our AI and machine learning system. We do not need a very large data set and can really validate for each center. And now we have long-term data showing that we're going to be reporting at ESHRE as well. Here's example, and really thank you, Dr. Barini, Are you still here? Thank you so much for letting us use this graph as an example. So what we have done is built a customized prediction model for live birth success for 9-dot baby in Bologna. And what you can see here, maybe conceptually, you wouldn't be surprised. For every age group, there's the blue, let me see if I can show this. There's a blue line, and that's the age-based success. So if you didn't have machine learning, then that would be the age-based success that you would be telling each patient. And that's how things are done right now in most centers. However, when you use an AI machine learning model that has been specifically built using that center's own data and validated according to that center's own data, you will see that there's such a range of probabilities for the patients depending on their health profiles. So even for people under 35, the range could be as low as 20% or lower, or higher than 60%. And for each age group, that's the case as well. And not only do we, is that really helpful to patients, and you can see actually just visualizing in a two-dimensional slide is never really accurate, but we try to show the concept of it. So the blue dots are the cycles that resulted in the live birth, and the orange dots are the cycles that did not. And you will see that proportionally, there are more blue dots at the top and more orange dots at the bottom. And that's all our eyes can discern. So don't try to read more than that. And we also, when talking about validation, there's not really enough time to go into all the depth here. We've published on the way we built prediction models in a series of papers, and also the validation, but happy to discuss that afterwards. But I want to point out, because there was a lot of discussion earlier today about AUC, a few things very important. You cannot actually take one AUC from one research paper to another because the circumstances are completely different. You cannot compare that way. And and the problem also is we're used to reading scientific literature of AUC of diagnostic tests. These are prediction tests. Prognostic tests are very different from diagnostic tests. Diagnostic test means you're diagnosing a clinical condition that's already in the person's body today. Well, the pregnancy and the live birth does not exist yet. So a prognostic test is predicting something that will happen in the future. And the standard of AUC is completely different. And so you cannot judge the AUC of a prediction model using what you've read from diagnostic papers. And so, what we did in order to have a comparison is we take that particular clinic's age model. So, and the age model AUC can vary depending on the heterogeneity of the patient's local situation and so on. And so we have some stats on the side there. But the important thing is AUC is not the only parameter. When we built these prediction models, there's at least 10 parameters that we look at. Now, of course, we want to get the model with the best AUC, but we also want to make sure that the other parameters are also favorable and showing that model to be actually clinically relevant and useful. So I won't go into all of them, but for us, for this particular purpose, Plura is actually the most important parameter that we look at. And we've, happy to discuss more of that later. But I will quickly go through some of the other slides, just as a background. The reason we kind of, started doing this was because we noticed that I've worked at many different cities with different socioeconomic situations. Some places, a lot of people are covered by insurance, like in Massachusetts and Boston, and some places, most people are paying out of pocket. But it doesn't matter where you are in the world. What patients want to know is, what is the chance that this is going to work for me? And I think we all want to give that answer, but we need a tool to give it so we know it's accurate, locally relevant to your clinic, and also validated and personalized. So very simply, currently, our prediction model is just using variables of health data that is already in your clinic's data. in the electronic medical record. And this is intentional because we want immediately that this is something that could be applicable to everybody without doing more expensive testing. And what we have found from analyzing data from all over the world is that age only accounts for about 50% of the prediction. So that means if you only use an age-based model, you're missing a lot of information. And this is just a simple example to show you what the first page of the patient report looks like. Very easy to understand, very intuitive. And it saves the doctor a lot of time to counsel the patient in a very streamlined fashion. And I put this here because what we learned is that after you have a very accurate prediction model, you can actually use this to do to make your business operation more efficient within the center, because you can now start doing business analytics by placing patients into prognostic group. So you can see the utilization of FETs, utilization of ICSI, or utilization of PGTA or other things, not just based on a whole patient population or based on age, but based on prognosis. And that helps you to structure and maybe even staff your center in a more efficient way. And definitely many centers have now used the system to help them with pricing as well. So that we can make IVF more affordable and encourage more patients to do multiple cycles without really the clinic really losing out as well. And there's a way to optimize that for patients and for clinic. And the important thing is to make this really easy to use. So I'm going to be running out of time, so I'm going to go very quickly. So this is the result of what we've learned is when the clinics were using the Unified Report to counsel patients, they're seeing 2 to 5-fold increase in IVF conversion from new patient visit to IVF utilization. And of course, we're very data driven, so we've tracked that for our centers, and this is all so going to be presented at ESHRE. And we're also, we just submitted a manuscript reporting these results as well. So this is graphically what it means by IVF conversion. You literally break down the numbers. If 100 patients come in, what happens to them? And you track them over time. And we've built really a sophisticated software to automatically do this for the centers that are participating in these analyses. So their business analysis can be a lot more efficient. So if you're going to be at ESHRE, please come to our talk. And we've published many papers. A note here is that we've also done the same kind of patient report and modeling for different types of treatments. So for egg donor treatment, for third-party reproduction, for egg freezing, to how to counsel patients about how many oocytes to expect and how many rounds of egg freezing might they need. So these are all addressing important questions that people have. This is a summary of what our company is doing. And I want to touch on a couple, if I could take a couple minutes, just to touch on a few things that people mentioned earlier. GDPR compliance, cybersecurity, these are top priorities for us that are really well figured out. And we also have very tight data use security. We don't use your data for other purposes other than to serve your center. And maybe just to show this slide, because I think it mentions a few things that we talked about. And cost, I'll just mention this, cost is very important. As we do AI, we care a lot about making this equitable. So AI should not be expensive, should not be out of reach. And so we have figured out a really good way to work with clinics to keep the cost down so that you can also use it for as many patients as you want. And definitely come and talk to us more about that if you're interested to learn. And we believe in transparency. We've published our methods and results in different scenarios. And yep, that's all for now, and happy to discuss more afterwards. Thank you.
Thank you for your presentation. I'm sorry because we are in late. If there are some questions from the audience, it's okay. If not, we will move fast to the next speaker. Some questions? No? Okay. Thank you. Thank you.
Okay, so we can now move to the next speaker, Dr. Jürgen Bernstein. He was part of the Fertitech team, which developed the first embryoscope time-lapse system. And today we will talk about IDA score, embryo evaluation for both cleavage and blastocyst stages using IA. Please.
Yeah, thank you so much for inviting me and giving me the opportunity to talking to you today. So I would like to bring you back to the embryo lab. I would like to bring you back to time-lapse systems. As mentioned, I was part of the team that developed the first embryoscope system, the first time-lapse system. But now we have moved on. The time-lapse has shown a lot of benefits like improved culture conditions and improved blastocyst rates and so on. So there's a lot of good things to say about time-lapse systems. But now it is the focus on which embryos should we select. And we have worked on that for many years. We have started out with the KIT score models. So we both day 3 and day 5, but now it's all about AI, and happy to be here to tell you about what we have been doing. So first I would like to disclose that of course I'm a Vitrolife employee and a shareholder as well. So the talk of or the topic of my talk today is IDA score, and first of all I would like to tell you a bit about the basics of IDA score, the IDA score version 1. I'll talk about how we validate, because numerous talks has been about the data, and especially how do we ensure that the model is working. So validation is extremely important. And then I'll talk about the new version of IDA score that is actually released tomorrow. So IDA score, what is IDA score? It is a decision support tool. It's meant to help you decide which embryos to transfer. It's not like a replacement of you. It's not like taking over and making it completely autonomous. It is which embryos to choose from. And as an input, it takes only time-lapse images. Also, some of the previous speakers has mentioned about age. And this is for surely intended to be ranking within a treatment where the age is the same. So we deliberately don't use age, and I think as Chris mentioned, we have also seen that including age is actually decreasing the performance on embryo selection within a treatment cycle. And as output, the IDA score model is giving you the likelihood of a fetal heartbeat. It is based on an original model from Australia called the IV model, made by the Burgess Clinic chain. But in contrast to that, we have increased the size of the data by a factor of 10. So that is the basic for the IDA score version 1. But what is really important is how you validate your model. I think nearly every university can make a embryo selection model, but what is really important is all the things that is going on afterwards that you have made your model. And here it's very important to discriminate between internal validation and external validation. I think internal validation is where you test on a certain part of your training data. And this is what we do internally. Every time that we release a new version of IDA score, we do a lot of tests to see biases in our data set. So we are sure that it works on different ways of insemination or fresh or frozen cycles, lengths of incubation, and so on. That is something that we're doing under the hood before we release each cycle. We also do a lot of tests to ensure that the model is working on new clinics that the model has not seen before. But even more important, this is just what we do inside before we release a model. But then after a model has been released, we have collaborated a lot with clinics to ensure that it is working on data that has not been seen during training. And this is what we call external validation. And here we have done a lot of publications on different validation. We have correlate IDA score with morphology, ploidy, fetal heartbeat, ongoing pregnancy, live birth rate, and also miscarriage rate. And we strongly believe in being very transparent about these things. So we publish a lot. We publish a lot of both the internal validation, but also, as I said, even more importantly, the external validation. So this is just a glimpse of some of the publications that has been done, and I strongly encourage you to read these. So I'll highlight a few of the publications. First of all, in a quite large study from Japan, they analyzed 1,500 blastocysts. This is not transfers, but this is blastocyst grading. And what they looked at was 5 different morphokinetic timings going from start of compaction and all the way to expanded blastocyst. And what they found was that the embryos in dark blue, which is the low scoring embryos, is slower for all these morphokinetic timings. So you see that they develop slower with regards to the timing. And the high scoring embryos, those are the one that is a fast embryo. Similar, this group looked on morphology quality and on cleavage state. And what they found was that the low scoring embryos here, there was around 15–16% that has poor morphology, and the high scoring embryos, there was only around 1% that had low morphological quality. And the same goes for day 3 morphology, where they found that around 25% of the low scoring embryos had a poor morphology quality on day 3, and less than 5% had a poor morphology if they were high scoring. And what is really interesting about this study is that this is not something that we train the model on. This is something that it has learned. The only thing that we train the model on is the ongoing pregnancy. So by itself, it has learned that morphology is important, speed of development is important, and Gardner, there's also studies showing that Gardner scale is important. So this is, I think it's a bit similar to how embryology involved, that people the more and more they was looking on time-lapse and Gardner grading, they learned that certain features, certain speed of development was important. And I think the AI has learned similar things. So one thing is, of course, morphology. That's not the really important thing here. The important thing is, as highlighted by several others, is live birth. And here is a study done by Danielo on Genera Life. And what they found was that if they evaluated the euploid transfers and the blastocysts that didn't result in a live birth, then the IDA score was 6.5. When they then looked on the embryos that resulted in a positive live birth, the IDA score had an average of 7.6, which was, as you can see, highly significant. If they then looked on the ability to sort or the rank, then they get this AUC curves, and as explained just now, AUC is extremely difficult to compare between studies. You should never do that. The only way that you can use AUCs is to compare to some kind of baseline. So in this baseline, the baseline was the embryologist evaluation by manual annotations. And here they found that the AUC was 0.64 and the IDA score had a AUC of 0.66. So in conclusion, you can say that IDA score was better, or at least comparable to the manual annotations by the embryologist. in an even larger study, and also from Japan, on non-tested embryo transfers, the K2 clinic found that overall there was a very good correlation with IDA score. The low scoring embryos on average had a live birth rate of 10%. And if it had a high score, then the live birth rate was about 40%. And when you then divide it into different age subgroups, you get an even better performance, where the very good embryos ended up in having a live birth rate above 70%, which is quite impressive. They also looked on the miscarriage rate and found also here a nice correlation, where the low scoring embryos, of course, had a higher miscarriage rate compared to the high scoring embryos to the right. So in conclusion, about IDA score version 1, then it's validated on very, very many studies, and that goes around the whole world. And it correlates with many endpoints, and especially we see very nice correlation with live birth rate. And another important point to make here is that the performance is at least as good as manual and evaluations. So if you then turn to IDA score version 2, that is, as I said, it's just released now. So it's the same model architecture. It now includes predictions on cleavage days as well. In the previous version, we would only predict the chance of an ongoing pregnancy on day 5 or day 6. And then we just also published an article showing how the model was developed and all the different validation, internal level validation that we have done. So this is just an overview of the different, over here there's the old version where we have 14,000 transferred embryos with a known outcome. And that has increased from 14,000 to above 30,000, 33,000 transferred embryos. And that includes both day 2, day 3, and day 5 embryos. So another thing that we changed is that at least our users found that the scores was a bit strange. There was all clumping around the high scoring range of the interval, and then there was a lot of middle range scores. So we decided to stretch out the scores so that we will get a better distribution of the scores. And then we wanted to have, one important thing is that we wanted to have the scores to be comparable between days. So in example, if you have a score of 6 on day 3 or day 5 or day 6, then it should be the same likelihood of an ongoing pregnancy. And this is exactly what you see in this figure, where you have the different transfer days in the different colors, and then you see a correlation where they are located around this line. And one important thing is also that due to we don't have as much knowledge on day 2, then the scores is only going from 2 to 6, and then when you have more and more information, the score range widens out. And as pointed out by several other speakers, then the AUC you can only compare it to a baseline. So here we have compared to both manual annotations and the KIT-score model and the previous version. And what we find is that the AUC of IDA score version 2 is better on day 5. It's comparable on day 3. And unfortunately, there do not exist any like commercial day 2 model. So here it's only possible to calculate the AUC. And here it's 0.67. And I think that actually brings me back to the points of not being able to compare AUC values across dataset, because it's a bit counterintuitive that day 2 is actually higher than day 5. But this is due to that it's different data sets, it's different clinics, it's different patient population. So again, never compare across data sets, only compare within data sets. So in conclusion, we have made a new version of IDAScore. It's based on more than 33,000 kid embryos or transferred embryos with known outcome. It is also now possible to do predictions on day 2 and day 3. It includes a new way of making the scores available, and it has performance comparable to manual annotations done either by a KIT score, and of course also if you're only using Gartner score. It is intended to be used as a decision tool. It's like you can ask it for a second opinion, so you can see that, and then you can kind of validate if you agree with the prediction. And of course, there's a lot of benefit. You have a much more fast workflow compared to doing a lot of manual annotations, and we are happy to have this model or IDAScore in general installed in a lot of clinics worldwide, and as I guess that most other speakers have mentioned, if you're interested in collaborating or need help to validate or something like that, then please contact us afterwards. Thank you.
Are there any questions from the audience? Because we are a little bit late. So we had to know if some of you have some questions. Okay. So we have to close this session. Thank you very much to both speakers. Thank you very much.
Okay, so we are going to go on with the next session, and the next speaker, actually, there is a slight change in the schedule. So the next speaker is Dr. Dan Nayot with the online presentation. Dr. Nayot is the co-founder and chief medical officer at Future Fertility, as well as a practicing reproductive endocrinologist and infertility specialist and medical director of the Fertility Partners Network of IVF clinics in Canada. He has a bachelor in mathematics and an MD at the Western University. And so in his presentation, he will actually show how to bring together these two different knowledges in order to improve the experience of patients in terms of IVF experience. I don't know what happened. Yes, I don't know if he is online. Yes.
Can you hear me?
Yes, we can. And Dr. Nayot, welcome, and you can start with your presentation.
Okay, it's a pleasure. Thank you so much for having me. I think I took over everybody's coffee break, but it's a real honor. I'm sorry I couldn't be there in person, but if there was one conference I did want to join was this. So thanks for having me virtually. So I'm Dan Nayot. I'm the co-founder and chief medical officer of Future Fertility, and I'm the medical director of a network of clinics called the Fertility Partners. And you guys have heard a lot about AI and different applications. Today, as a clinician, I'm going to focus on how we can use AI on the oocytes and how that can help us clinically, whether it's from the physician, embryologist, or patient perspective. It's about a 15-minute talk, so I'll have to go really fast. I think we all know ChatGPT. This is my attempt to be a little bit funny, but really what I want to do is highlight an important point. You know, when we started Future Fertility about 5 or 6 years ago, I was at the first AI conference in Lisbon in 2019. I think Kevin Loki was there with me, maybe 24 people. And back then it was sort of a fun research project for everybody. And I think in 2023, we can see that AI is inevitable. And now we're just trying to figure out how the best way to use AI. Me personally, I use ChatGPT for bedtime stories with my kids. I find it much more creative than me. But I think we're all talking about today is how can we use AI in reproductive medicine? And my lecture specifically will be about the eggs. AI has become so powerful that there are now specific jobs called prompt engineers. It's not how good is the AI, but how creative is the human? How can we use the AI as a tool to help us in the clinic? So let's dig a little bit deeper. So I've always focused on the egg because I thought it was just crazy that there was no egg scoring system. All the journal articles you'll read, all the embryologists around the world, all the clinicians, we know that there's no validated visual egg oocyte scoring. This is different from embryo grading. Sure, there are better ways to grade embryos, but at least we have some constant baseline. But for the eggs, this doesn't exist. And we know that eggs is the key part to IVF. We know that egg donation can almost overcome all age-related declines. The problem is we have no ability to measure eggs. Of course, we can check nuclear maturity, but we have no insights into cytoplasmic maturity. Of course, we can comment on oocyte dysmorphisms, but we don't know what those actually mean and how they help us. We know that embryologists are very skilled and have seen hundreds of thousands of eggs, but they can't remember the micro details, and there's many things they can't discern together. So using AI to analyze these mature eggs is the key to finally create an egg evaluation system. So let's just talk about egg quality. We define egg quality as the reproductive potential of the egg to become a baby. I think this is similar to embryo grading. So, embryo grading describes the embryo, but it correlates with clinical outcomes. If a 5AA and a 2BB had the same live birth rates, then you can argue an embryo grading is not too helpful for us, but it doesn't. The same idea with the eggs. So a better egg should lead to better outcomes. Of course, the ultimate goal will be, can you predict if an egg will become a healthy 18-year-old? That's the ultimate goal, but we got to move backwards to live birth and implantation and euploids and blasts and fertilization and so forth. We decided to focus inside the lab because inside the lab is as controlled as you can get. We know that you can have a perfectly normal embryo and it may not implant, not related to the embryo itself. So we focused on the lab. I won't repeat what all other speakers have said, but having a large, diverse data set with good AI practices is critical. We originally built our programs on 70,000 images with 8 countries and 3 continents, and this is growing month by month. I'm happy to report that we're over 120,000 images now in 12 countries, over 4 continents. The key is diversity and good AI practices. Okay, so let's look. So if you could predict if an egg will become a blastocyst, you've got to validate that in real world time. Here we can see retrospective data on almost 8,000 eggs, and we can see that the higher the score that the AI machine gives the egg, it correlates very strongly in a stepwise manner that the higher the score, the higher the chance that that egg will become a blastocyst. And again, that correlates with egg quality. So a higher score should give you a higher reproductive potential. We've done this prospectively as well, as all the speakers will tell you. That's the next step of validation. We did this in different clinics in different countries in real time. And we did this with ICSI cases, but non-male factor, because we didn't want that to contribute to the outcomes of those eggs. And we saw once again that the higher the score in real time, that the more likely this egg was going to become a blastocyst. So this is great. We can finally say that AI can have a correlation between egg and blastocyst. And we know over many studies that this is not an ability for an embryologist to do. Okay, so let's start. We're going to focus on at least 5 clinical applications of how to use an AI score for eggs. Let's take an example. So here's a QR scan code. If you guys want to use your iPhones, you can look at what sort of a report looks like. But let's start with a similar concept. Let's start with the embryo. We know that visually embryos are graded, and we have some form of the Gardner Schoolcraft grading system. Every embryo in the world is graded, whether you're discarding that embryo, and I know it's a 2cc that's been discarded, whether you have one embryo, I mean, the outcome's going to be binary, success or not, but you need to tell that patient what kind of embryo you're putting in there, or whether you're biopsying those embryos. So every embryo in the world is evaluated. Analogously, for the eggs, if there was an egg scoring system, which now we've enabled through AI, every egg in the world should be evaluated because those insights are valuable. Let's go into some case uses. Well, the first case use is IVF. Mylene and the Unify IVF team have already highlighted that many patients have a low prognosis, and using a personalized report and counseling, you can prepare them for multiple cycles. So as she has highlighted, this can help with retention and multiple cycles. We see the same issue from the clinician point of view. We know that a majority of patients would be considered low prognosis. So we know they may not get too many eggs, or we suspect their egg quality is going to be low just based on their age. And we anticipate that we're going to be sitting in front of them more likely than not and talk about their failed IVF cycle. So the ability to highlight the impact of the egg on their failed IVF cycle is critical. It's critical for transparency, and it's very helpful to personalize what to do next. Whether you're talking about egg donation, whether you're talking about managing expectation and trying multiple cycles, or I'll leave it up to you if you have a favorite way to adjust your protocol to try to make better eggs. Next. If we could evaluate eggs, then essentially we can rank eggs. There are some countries around the world where there's a limited number of eggs that we can select to fertilize for legal reasons. Well, in these jurisdictions, it is critical to pick your top eggs so that you can maximize the number of fertilized eggs and embryos to transfer. So having an evaluation system will allow you to evaluate the top eggs. You know, you have already thought of this probably yourself. Well, if I could do that, I could probably use this with the egg banks, because in the egg banks, they not only have to choose the top eggs, they also have to distribute. All the egg banks around the world have told us they would much prefer, if they had 18 eggs, to have one live birth divided by 3 intended parents versus 300. So even evenly distributing the eggs is a key part for the egg banks. Next, although this has not yet been proven, this is a concept we're working on, we believe that embryo selection could be helped with the use of the AI of the egg. There are many clinics around the world that just use the final data point, which is the embryo grading. But I think most labs around the world use other data points, like what day the embryo was, what about the morphokinetics. So adding the starting point of the egg will be another data point you can use for embryo selection. I'm going to move it along for time-wise. This is a study we're quite excited about. We did this with a network in Europe, but another case use is group culture. I can appreciate that not all labs use group culture. Some do single culture, but many do, and many believe that the group culture has cumulative improved rates. Now, eggs are randomly distributed into group culture based on the number of eggs they have, because there's no evaluation system. And what we did in a prospective real-time scenario is we took pictures of these eggs, we gave them a magenta score, and we grouped them based on the score. And once again, we saw that grouping the score correlated with the number of blastocysts that are happening. We were quite excited because maybe group culturing by better quality eggs will improve the cumulative blast rate. And we're excited to now launch this multi-clinic study in a network in North America. And hopefully I'll have some data for you with our next presentation. Okay, let's move on. So we talked about fresh eggs. Now let's talk about frozen eggs. I think that's what future fertility is probably already known for, the Violet report. You can QR scan it here. But the first case we ever applied AI to are the egg freezers. To me, as a clinician, seeing thousands of patients over many years, the same question came over and over again. All egg freezing patients wanted to know was, what is the chance of success? And over again, I can only tell them that we use their age and their number of eggs. And I think that's better than telling them nothing, but I think that's very general. As we all know, not every 34-year-old has the same quality eggs. And what's even more for sure, not every egg in that cohort is the same. So using a personalized tool like AI to predict eggs to blastocyst and then model blastocyst to live birth, we can give a more personalized report to the patient. Now, beyond the statistics and the data, this has a lot of other benefits to the patient. First of all, these are the only patients who've ever seen their eggs. They have put a lot of effort and a lot of finances towards it. So having some sort of keepsake is quite important to them, is what we found out. It also shows transparency. You said you had 11 mature eggs frozen in your lab, and here are pictures of 11 independent eggs. And the clinicians have told us over and over again the same thing. When they get to see their report and they have a more realistic expectations of the chance of live birth, it helps manage expectation, and for sure it leads to multiple egg freezing cycles, which is only going to increase the cumulative success rates for these patients and increase their chance of overall success. Okay. Beyond the egg scoring, there are other ways we're using AI on the eggs. As you can see, we're obsessed with the egg. We've been doing it for many years, and we think it is the key part for the IVF lab. So, you know, some of these are pretty intuitive and logical. Just the ability to identify a nuclear mature egg is a task that we're underway now. Of course, all embryologists could probably do this with high ability, but having it as a safety check for the one in a few eggs or for your junior embryologist adds a great value. The other learning point we learned along the way, speaking to hundreds of embryologists over the years, is that many embryologists comment on dysmorphisms, whether it's smooth endoplasmic reticulum or granularity or so on, but very few of them act on these dysmorphisms. And when you ask them, then why are you commenting on it if you're not using it, is that they may use it in the future. And I agree with them. The more data you have, the more you can probably unlock. But one way to save embryologists time, which is critical, as we've all heard today, is to just take a picture of that egg and automatically identify the dysmorphism, because then you can quantify it and you can always go back and look at it. So today I've focused on the clinical applications of using AI on the eggs. Of course, there's a few more. I wish we had a little bit more time to talk, but that's the main things I wanted to highlight for everyone today. Thank you so much, and enjoy the rest of the presentations.
Thank you, Dr. Nayot. Unfortunately, we are running out of time, so we have to move on to the next speaker right away. Thank you very much for your participation. And
thank you so much.
Thank you, Dr. Nayot. It is my pleasure now to introduce Dr. Daniela Gilboa. She's an embryologist. She is co-founder and CEO at AIVF, a medtech startup which applies artificial intelligence in the field of IVF. Dr. Daniela Gilboa, thank you.
Hi, everyone. Hi, Michelle and Christina. Good to see you guys again. And I'm very happy to be here in beautiful Rome. And thank you, the organizing committee, for inviting me. I'll be talking today about, I think, a new era of IVF, the era of bioconvergence and computational biology, embryology. And just to disclose, I'm the co-founder and CEO of IVF. Okay, so we all know what's happening with AI today, and this is just recently the AI, the godfather of AI lives, Google, and warns about the ethical considerations of AI. And there's a new concept now that mathematicians are talking about. It's called artificial general intelligence. It's AGI. But let's go back to 1950. Where it's all started. A young, brilliant computer scientist, Alan Turing, published in Mind magazine a mind-blowing concept of computing machinery and intelligence. And he said, you could read it here, we may hope that machines will eventually compete with men in all purely intellectual fields. This is mind-blowing. And if you want to read this entire paper, you could ping me afterwards. So again, 70 years later, we have this guy talking about AGI, artificial general intelligence. But why are we dealing, or why are we talking about Alan Turing now? Because of the imitation game. As part of the argument that Turing put out was the idea of the imitation game or the Turing test, and we'll come back to this later. This is a slide that I always show because it's a perfect distinction or comparison between the human learning concept and machine learning. And this is important for us to grasp because it's part of what we believe in the next generation of AI, and I'll explain. So human learning is basically learning by rules. If we want to teach the computer, for example, here, what's the difference between a circle and a square, we have to actually realize what the rule is. So the rule that we would tell the computer is count corners. So if it turns 0, it's circle. If it turns 4, it's square. As by machine learning, this is learning by examples. So we don't provide the rule, we provide examples or data sets. So a data set of circles and a data set of squares, and this is where the machine will learn by itself the rule according to the example. So this is human versus machine learning. This is something I'll go back later. Remember this. Now going back to IVF and how we can all apply this into IVF. So we all know this was taken, an image taken at Stanford University a few years ago. Day 3 embryos, about 10, 12 embryos kind of look the same. And we all use subjective human analysis, subjective morphology evaluation. And so I think it's safe to say now that most failures in IVF are due to the fact that we don't really know how to select embryos. And so wherever there is judgment, there is noise, and there's a lot more of it. This was said by Daniel Kahneman. He won a Nobel Prize for economics in 2002. We wanted, for the sake of time, we wanted to actually understand and model the bias and the noise that we have in embryo selection, in human embryo selection. So we conducted a very interesting study, which I'll present here. And we wanted to understand whether we as humans, as embryologists, actually look for the best embryo in the dish, or whether we just choose the first acceptable one, whether it's the first acceptable one versus the best one. So we had, so this was the hypothesis, and spoiler, yes, the selection bias can impact implantation outcomes, and we're very, very biased as humans. And what we did is a retrospective study. We had 3 fertility clinics, 1 in the US, 2 in Europe, more than about 4,200 fresh IVF cycles. And we actually, the question was whether we select the best one or the first acceptable one. And the answer is, and this is across all 3 clinics, is by us choosing, an embryo is twice as likely to be selected from the first 4 wells rather than the last 4. Meaning, what we do is the minute we see a good embryo, an acceptable embryo, even if we go on and compare and look for what we think is the best one, we go back to the first acceptable one. This was modeled, calculated across all clinics. We have new data coming in that shows the same ORs. So this is, I think, demonstrates that there is an inherent human bias. So the fact that we have to use an AI system and to become augmented embryologists is something that I think all companies and all research teams have managed to convey. So now what do we do? And I talk to clinics, and most of them say, yes, we know there is human bias, so this is why we turn into PGT, and PGT is probably the solution. I say no, but it's not for this talk. So now let's see if we can create an AI that will take the human learning and the machine learning and provide us with something that is exactly what we need. It's just exactly like we are looking at embryos, but better. So we've tried to show this on a genetic testing model. We developed a non-invasive approach to actually understand if the question that we are asking is not if the embryo is euploid, but rather is the embryo aneuploid. And I tried to collect a few of the publications recently, and all of them show an accuracy or different metrics, which is kind of the same, 70, 72, 78, and it's great. But the question that I'm asking is, what does it mean for us clinicians? What does it really mean that we are using an accuracy, a model with an accuracy of 78.5%? As clinicians, what do we deliver the patient? So I don't know how to answer this. So what I'm trying to do here is propose a new way, which we call symbolic AI. And symbolic AI is basically combining the human learning and the machine learning, the knowledge-based system with the outcome-based system. And let me show you how it works. So this was tested on our PGT model, the model that detects novel features in the embryo that are associated with ploidy. So we had a one-center retrospective study, of course. We had 2,500 blastocysts with PGTA outcomes. And for the sake of time, I'm not going through all of these features, but we were actually able to identify, recognize, and model 5 different features. Each one of them is correlated with ploidy, with aneuploidy. Each one of them has somewhat of a contribution, but they cannot be a standalone. So we all know that morphokinetics has some contribution, and morphology has some contribution, and even cell division activity. We were able to understand and to model the mitochondrial activity of the embryo on day 4, which is very, very correlated. But what happens if we take these 5 features and integrate them into machine learning model that was trained on PGT outcomes? So the combined accuracy, or the combined model, gets us to above 90% accuracy. Why? Because when you look at these features and you ask the right question of not which embryo is euploid, but rather which embryo is aneuploid, you're really able to come up with a model that's pretty accurate and it could be used in a clinical setting. We understand what we get. And more than that, it's explainable. Because when the model says this specific embryo is aneuploid and it shows mitochondrial activity or abnormal mitochondrial activity, I understand because it has biological sense. So this is where symbolic AI comes in, and it's basically embedding human knowledge and behavioral rules into computer programs. And we as embryologists, and we have 45 years of clinical embryology and deep understanding of embryonic development, this knowledge needs to be incorporated to any AI model. And I'll finish with this video. I'll show you how it works. This is, of course, just an example of some of the features the AI is able to detect. And again, features we understand. Some of them cannot be seen by the human eye. Some of them we know, but were never modeled. But I think it's a bridge between the AI and the human to be able to work with such amazing technology. And going back to Turing, I think now it's the era again of bioconvergence. It's not the machine versus the human, as Turing suggested, but it's more than the human plus the machine versus the human alone. And I think this is really the era where we are with augmented medicine, augmented embryology, augmented IVF. And there's an amazing research activity going on here, more of a behavioral aspect of human with the machine versus human without the machine, who performs better. And I could tell you that together we do a great job than just alone. So I'll just finish again with Daniel Kahneman. As long as algorithms are not nearly perfect, human judgment will not be replaced, and this is why it must be improved. Thank you very much.
So thank you so much for your excellent presentation. This is, I mean, as embryologists, we aim to have support from the application of AI in improving our knowledge. This is something that, I mean, we would like really to have at the moment. So we are running late, so we have just time for one question. If there is any question, yeah. Also for the first speaker, any question from the audience? Okay, just a brief comment that I would like to, I mean, if you, Dr. Nair, can comment their presentation, his presentation, since I understand the application of this kind of algorithm in, for instance, in the optimization of the oocyte donation program, no, where you need to optimize the allocation of the oocyte to the recipients. But what about the infertility patients? I mean, the risk is that we may reduce the efficacy of the treatment by deselecting oocyte, even those oocytes that have that reach a very low score. Or I don't know if you had the chance to identify with the use by the use of this algorithm any particular feature, morphological feature that can predict with accuracy the viability then of the oocyte. So, for instance, if in case with unexpected outcomes such as total fertilization failure or total blastulation failure, was the algorithm able to identify any particular feature that can predict this kind of outcome?
Yeah, can you hear me okay? Okay, thanks for the question. I think there's a few questions in there. So the first one, just to clarify, when we talk about egg selection, the only case use, like you highlighted, would be in jurisdictions where we have to select because there's a limited numbers, but we would never deselect eggs in IVF cycles, like you mentioned, because every egg probably has the potential. I think probably the most controversial example of that in our field is SERs. So, you know, there were papers originally suggesting SER, smooth endoplasmic reticulums, not only do worse in the lab, but have really bad neonatal outcomes. And many embryologists started in their lab to discard them. They would never use it. It's, I can't believe that. And then some papers came out and suggested they're actually probably no different. So I'm not sure we know the true answer, but you can see there are 3 labs out there now. There's ones who will discard SERs, those that ignore it because they don't really know the clinical application, and those who will use it but deselect it and pick their embryo with a SER egg last. So again, I would not advocate to deselect eggs even with the most predictive AI tool because you don't truly know that 100%. I think your next question was about, did we learn anything interesting in specific cases like failed fertilization and no blast and things like that? And the answer is yes. I think the complicated part is how do we explain it to clinicians who have a certain mind, or embryologists or patients, because, you know, we as humans, we need to simplify it. You know, it is much easier if I highlight granularity and tell you that the granularity is bad because that makes sense. You can see it with your eyes. It is less intuitive if I show you in a heat map and you know, and show you that this region. So I think we're working on that, how to take what we're learning, but simplify it in key messaging for the audience, because if the audience doesn't understand it, then it's not really that explainable.
Yeah, we can make it, we have to make it then translate in something that we can apply then in clinical practice, of course. So thank you so much. If there are another questions from the audience, we move to the question.
Thank you. Daniela, sorry. I was interested in the conclusion that you put with your study about the integration of many information and the way by which we can also make the right question. No? Do you think that the introduction of these tools and the integration of information can learn us how to do the right question? Maybe that we can add more to change our mind about the question that we are performing.
Definitely, and I think it's embryologists and physicians ask different questions than computer scientists. So if you take a data set and this amazing question of how to select embryos and you give it to computer scientists, they will look at it differently. And I think we have to lead it from the patient side, from the clinical side. So there's one thing having the computer scientist understand it and build something, but then it needs to be handled by physicians and delivered to the patient. And this is where I think we have to realize that we have to ask the relevant clinical questions to answer this.
Thank you. So thank you so much for your very excellent presentation. So we will move to the last session.
Good afternoon. Welcome to the part 5 of this event. It's a great pleasure for me to chair this session with my co-chair, Giovanna Tomasi and Laura Sosa. And I would like to introduce the first speaker, Davide Gaudesi. He's a clinical data manager, data passionate, database programmer, and digital solution explorer. And he worked at the Advice Pharma Group, and he shared his vision about clinical data management with all his community. The title of his presentation is Opera Project, Leveraging Digital Technologies for an Innovative Large-Scale Multinational Collection of ART Real Data World. Thank you.
It's a great pleasure to be here with you all, and I'm happy that today we greatly discuss about 3 key topics for the project that are data quality, data volume, and ethics that are very pivotal for my and our project. But disclaimer, I'm not talking about AI or at least I'm talking about something before AI. It means data that is the feeding material for all the AI tools and platform. So I am the head of data innovation management in Advice Pharma, that is full service CRO based in Milan. And my unit is mainly involved in real world data and real world evidence project and data integration project. So today I would like to talk about the project, the process, the data, and the challenges related to that process. So OPERA stands for Observational Retrospective Project for a Research Database for RT Procedure. That is a project that was sponsored by the Fondazione per la Ricerca dell'Ospedale di Bergamo, and the scientific supervision is by Professor Francesco Maria Fusi and Professor George Griesinger. The starting point of the project was that statement of Professor Griesinger in 2020 that all innovation to IVF treatment have to be judged from one perspective, the possibility to provide to couples a new way to have a baby with less effort, less burden, less financial cost, and less parental and fetal risk. So the data that we collect as a community tell us that we do not have enough evidences to guide and help clinicians in order to select one treatment with respect to another. Why? Because no RCTs and only 2% of meta-analysis achieved 80% power to detect an improvement of 5 percentage points. That could be what the clinician need to take a data-driven decision. So what? To fill this gap, the idea was to build a standardized European database with a high number of IRT cycles, from which one it's possible to obtain comparable subgroups and obtain real-world evidence. But what are real-world data and real-world evidence? According to the European Medical Agency, real-world data are the data routinely collected to a patient health status or the delivery of healthcare for a variety of sources other than traditional clinical trials. These sources are something like electronic health records, claim records, and so far and so forth. So the analysis of this data lead us to obtain real-world evidence. But the question is, what are the requirement of this data? That first of all, they must be digital, so electronic. We need a high volume of IRT cycles. The data must be anonymous and of a high quality of data. And from this data, it should be possible to extract informative aggregated reports. So where the data came from? Now we collect data from 18 European ART clinics, 9 in Italy and 9 in Germany. And why we selected these clinics? Simply because they have a Meditex installation on place. They are used to handle more than 500 whole site cycles per year, and the clinics collect the data of interest for the project. So now that we paved the way of the project, we can speak about the process. And these are some general numbers. As we said, 2 countries involved, 18 clinics, for a total of more than 106,000 ART cycles. The process was designed in order that every time the 5 clinics obtained the approval from the ethical committee, the data were extracted from Meditex, locally anonymized, securely transferred to Advice Pharma repository, and with a quality control step, the data were securely in terms of quality and then transferred to the final repository. So anonymous was pivotal for all of this, and how we achieve this goal. We decided to use no direct identifier, and instead of the birth of data, we use the year of the birth to calculate the age of the subject, and the data are locally anonymized. After this step, the data are transferred from the clinics to a national data center. We check that the transfer was successful, and so we go back to the first previously set of anonymized data, deleting that in order to keep only the transfer one. So a second data transfer was implemented from a national to a remote repository. Again, a data check was performed in order to be sure that the transfer was successful, and the first copy was destroyed, and so we keep only the last one. And finally, the data was transferred from the remote to the advised pharma repository. A working copy was generated, data coding and standardization performed, and finally an automatic opera transfer from the repository to the our proprietary electronic data capture platform called ICE. So, what were the data involved in the project? 5 kinds of data. Basal data, mainly demographic and something about the hormone and infertility factor, stimulation and ovulation data. Laboratory data that are mainly involved in the evolution of the embryo status, and the pregnancy and outcome data. So at this point, we face a group of challenges relating to this data. And I divided these challenges in 3 categories: the freedom to capture data provided by the electronic health record system, the opportunity to get and to obtain real-world evidences, and the challenges related to languages and jargons. So the text, the field in Meditext are most of them as a free text that provide to the clinician the possibility to write all the possible information, but from a data perspective point of view, it's not a good thing, simply because when I say everything, I really speaking about everything, and later on I will show why. And so a predefined reply option for sure speed up data capture, but also go in the direction of increase the data quality. Then open text cannot be counted, obviously, but this is obvious for us, for human, not for a computer. So it means that you have to process properly. It means to define what is a text, what is a number. And so after the process, you can make some statistic and calculation. Notes, there are a tremendous amount of notes within the data points. So that is something that you have to have clear in mind, and so to find a way to process them properly before to extract and to obtain data in order to perform your statistic. Then the date formats, there are no specific date format in place. So it means that I have to start from the fact that one date could be recorded in an American format and one in a European format, just for an example. And no normal ranges were set in the system. So it means that no warning could be suggested to the clinician, and also no information tell me that that specific data should be or not should be used. And so for this reason, a great work was done with the principal investigator in order to understand what was the good and the bad data. So when I say about, okay. As you can see, in the duration of sterility, I found a negative data, that it means a loss of information because it's useless. Or for the hormones, together with the level of the hormone, are also find this kind of information that has completely had no sensor or no utility to, or for example, for the female infertility factor, this kind of notation, I don't know if the clinician are used to this kind of information or can add something, but for sure for the project is totally useless. Or the date, you can see they are recorded in both way, and so, but the system is a computer and need to be used this kind of date format, or as well for laboratory data. Both this kind of annotation were found, and in this case this is very challenging because it forced me to modify the data, because this cannot be used. So it means that I have to process the data to the closest one, and obviously this is quite close, but it's not the closest. So I have to take a decision, and this is could impact the quality of the data. The chances to obtain real-world evidence, it means to perfectly understand the standard clinical practice, because from the point of view of the clinician, and information could mean something, but from my point of view could be another thing. So it was very fundamental to stabilize the process of communication with the principal investigator in order to be aligned about what the data are telling us. Or missing data, some data processing tend to derive data if they are not, but this is not good at all. If you are missing data, it means that you are missing evidences, and it could be a big problem. And so if you think to design a project like that, keep in mind that missing data are a big problem. And coding is another challenge that it's better to show you. For example, we found more than 500 combination of gonadotropin used in the data set that must be coded to 8 categories. Or for the adjuvant before and during stimulation, we found more than 300 or more than 700 combinations that must be categorized to a much lower groups. It means that clinician must decide what are the coding to be applied, and the data manager have to implement a process to traduce this algorithm in order to obtain the category of the gonadotropins. And finally, languages. Multi-language database, it means a translation process that must be taken care from the beginning, because the translation is not something simple. If you make an error in translation, it makes an error in the final evidence. So it's very important to take care about. And the jargon and the acronyms are something that must be taken care directly from clinician, because only the clinician know what is really talking about in that jargons or that acronyms. So the OPERA project shows us that the real world have the potential to explore the unmet reproductive medicine needs, and this database paves the way to explore those needs. But for sure, privacy by design was a key element, as well as quality control that allows us to produce the high quality data that lead to real world evidence. And for sure, this is a continuous learning process that allows us to better handle data and to better proceed in the process and maybe in the next projects. I conclude. Thank you all, and it will be a pleasure to answer to your question.
Thank you, Davide, for your nice presentation. Now we can open the discussion. Are there any questions from the audience?
If there are no questions. Thank you, Dr. Gadesi, for your interesting talk. and fascinating information you gave us. And as you shown, collecting data of fertility treatment are maybe one of the better way to improve patient care and support research. In your opinion, how far are we from having interesting data registry, which could allow industry experts or researchers to access data and improving, obviously, upon request of patient without compromising patient, offsprings, and donors' privacy?
Okay, thank you for the question. One of the main goal of Opera project is to provide this kind of database and tool. As a projection, our foreseen is to reach at least 5 times the number of cycles that we collect today in 18 clinics, obviously expand the project to other countries and other clinics. And the privacy for this specific project is not compromised at all, because I did not go in detail, but every single cycle is defined as the year in which were recorded, the age, the year of birth of the women, and the specific code of the clinics. And in order to protect the privacy, we transfer data every 5 clinics that reach the approval of the ethical committee. So practically, as a database administrator, I cannot know what are exactly the origin. Obviously, I received the data before the processing in Italian or in Deutsch. So I can obviously understand the nation, but that's it. So the privacy is totally protected. So in this regard, if a project like that are designed with this mindset, we can take care of the privacy and to provide enough power to clinicians. Obviously, if they ask the right question, they can get to real world evidence that can help us in the clinician and in the day-by-day activities.
Thank you so much. Only a really brief question. All of us use generally in our laboratory some database. And what do you think about the data that we already collect and we don't know if in a proper way or not? Can we use it for a new tool in AI, or we have to trash it all and start it from new data in a correct way?
The honest answer is I don't know, simply because you have to make an analysis of all the database that you want to use it, test the quality in terms of completeness and precision of the data, and only at that point you have to consider if it's possible to integrate that database in order to build a bigger one or not. So everything is related to the starting point, the data quality, and the question that you want to obtain an answer.
Yeah, but the problem is how we can check the data quality of our database.
The data quality can be checked in terms of completeness. It means how records are full of data. Okay. In terms of if they span all the ranges, for example, for a numerical variable, because if a specific database is populated with data that are particularly enriched with some values, and maybe that values are not enough or not feasible to reply to your question, it's not the right data source. So all this kind of approach can be put in place, and obviously the scientific question is the most important thing to think about. Starting from that, all the process can be drawn easily.
Thank you.
Thank you, Dr. De Catesi. Let's move to the other talk. And I'm delighted to introduce you Dr. Irene Cuevas. She's a lot of things.
Funny,
but she's a clinical embryologist. She's the director of the embryology laboratory of Hospital General of Valencia. And also she's the president of the special interest group in embryology in ASEBIR, that is the National Society of Embryology in Spanish, that we can define our sister society. Yeah. So please, she will talk on improvement of IVF treatments beyond efficiency in embryos or gamete selection. Please.
Thank you very much for your introduction. And thank you, Danilo and Valerio, for the organization of this interesting meeting, and the rest of the society, of course, this sister society. So I will talk about the improvement of IVF. As you said before, I'm a clinical embryologist, and when I started to work in a research project regarding AI, I was really interested in embryo selection, of course, of the rest of the embryologists around the world. But we started to work in a tool for better selection of the embryos that I have in my time-lapse systems. But we realized that that was not the answer for all the IVF treatment. At the end, if we use an AI solution, and we want to introduce one AI solution in our clinic, has to take profit for everyone involved in the treatment, for all the staff involved in the treatment, and for our patients, of course. So as a clinical embryologist, when I transfer one embryo to my patient, I think that if I will transfer the same embryo with the same quality, with the same score to a different patient, the result will be the same. And we still don't know the answer. What is the correct answer? Where is the answer? In the age of the patient, in the amount of gonadotropins or the type of gonadotropins that the doctors use for the stimulation protocol, or the volatile organic compounds that there are today inside my laboratory, or maybe there are changes in the thyroid of my patient. So there are a lot of variables that can influence the final result. And I have a very good embryo that has not implanted with a very high score. So when we already had a tool for scoring embryos and for selecting the best embryo for transferring to my patient, we decided to stop and to make a review on all those other parameters that can influence what embryos I'm transferring to my patients. And the talk of Dr. Davide was perfect for me as an introduction, because all you know, and Valerio had a very good question, we have a lot of information that most embryologists, we record a lot of information, we type everything, we record everything, but we use everything? No. When we have a congress, we make beautiful abstracts for the congresses, and the databases are really useful at that moment, but not for the day-a-day or for improvements in the day-a-day. So one difficulty with the data that we have is that we have data from several resources. We have Excel files, we have electronic medical records, we have PDFs that the patient brought when he came from another clinic, we have pictures, we have hysterosalpingographies, we have everything, even handwritten documents. All we write still things in the history of the patients, and we have data there. So to process everything, as the doctor said before, is really, really, really difficult. And the thing is that at the end, almost all the data that we generate remains stored, and that means unused forever and ever and ever. And maybe there we have the question for why some embryos, beautiful embryos, high scored embryos, don't implant. So at Circle AI, I'm the scientific advisor of this company that I'm really glad to be here because it's the first time that we introduce the company in public. So at Circle AI, we thought that the ideal process to start using an AI tool was to transform low quality data, the data that we have in all the clinics, all the laboratories and everything, into high quality data to be used to try to find the right answers. So what our engineers do, I don't know a thing about that. I try to understand everything, but I'm not able to understand. What they do is that they transform all the data. Davide has said before, there is a lot of problematic because we use a lot of alias for the same thing. For example, anti-Mullerian hormone, AMH, and everything is exactly the same. So our engineers has to translate all that information and allocate all that information in the correct place. So we generate different nodes that are attributed to one patient. And those nodes have all the information regarding one specific topic. For example, we will have one patient is the central blue point, and that patient will have a lot of nodes, for example, one with all the information that we have about the sperm analysis or from the male, and all that information will have their own nodes because we can have parameters regarding the health of the male and parameters regarding the semen sample of the man. So at the end, it's a long list of nodes with several nodes from every single patient or every single couple that we have in our clinic. And all that information is used to compare patients with others. So we have another part of the tool that is the patient information too. We have another module where the patient can introduce their own information and can be shared with the clinic. And we offer the possibility to connect with all the information that other providers are or can bring to you. For example, if you are doing the PGTA with a genetic testing like Genoma, for example, you can connect all the information of your embryos to be populated directly into the tool to be used, not only all you have inside your clinic, but information from the patient, information from providers, from laboratories, to make all the data the more complete possible to have all the information. So I think, or we think, that data is the key for having all that unorganized information in our databases, everything that is unknown for the prognosis of the patient. We put everything into the biomedical graph, of course, completely anonymized everything, and we put at your disposition all the information at any time that you need it. I will try to explain this because it's a bit complex. When I have a new patient that comes to my clinic, that patient will offer me some kind of information. For example, I will say, since the very beginning, I know the age of the couple, and maybe she brings me the anti-Mullerian hormone. So I have a small piece of information from this patient. So if I go to all the storage I have in my clinic, probably I will have 1,000 patients that are very similar to her. But if I do some tests to my patient, this amount of patients that are very similar to her will be closer. So what the system will offer to you will be the information of those specific patients that are really close to you, the patient that you are treating right now. So you won't the system will never tell you what you have to do with your patient, but will bring you the opportunity to go to all your stored information and to know what did you do with that kind of patient that is very, very similar to the one that you are treating, and what was the final fate of those patients that you have to treat. So this was the case for the very beginning. For example, to counsel your patients if they have to start doing IVF or IUI, or wait 6 months until becoming pregnant spontaneously or something like that. But we use that information at any stage of the process. So we work exactly the same with all that information, comparing patients or comparing embryos at any stage of the treatment. When we start the stimulation process, for example, you can have all the information of previous patients for better counseling your patients, which kind of hormones you have to use for optimizing, for example, the number of oocytes that you have to retrieve in a patient that will do a fertility preservation process. But probably the goal is completely different when you have a patient in 42 years old. That's what is really important for, or what our goal is, to become pregnant as far as possible. So all the information will be there for you, for helping you making better decisions. For embryos, it's exactly the same. We will have all the embryos, we will have a score that will be comparable. All those embryos will be comparable at any time with other embryos from other patients, other treatments, that have had a similar behavior along the development, but compared to patients with a great amount of similarities. So we think that that is the difference. And I don't have many time, but I wanted to show you the tool, or some parts of the tool that I think they are interesting. This is the part where we can see the patient profile and the medical history of the patient. We are used to have electronic medical records where we can find a lot of empty spaces, because we have all the information and we can have that information or not, but you have the possibility of fulfilling everything. At Circle, what we do is that we show the doctors or the technicians only the information that is available. Of course, at any time, if you have new information, you can upload directly. If the patient brings the PDF of hormonal test, for example, you can directly scan and upload, and the system will fulfill that specific thing. So you can see that in the history of the patient. And of course, you can type everything if you want to. This is another part that is really interesting for doctors, of course, regarding the stimulation protocols and the egg retrieval details. You can see here that you can, of course, fulfill everything regarding the stimulation process, but the system is always comparing your patient with the 40 closest patients that you have in all your database. So the system is offering you continuously all the information from those patients. And as I said before, you can optimize whatever you want. The number of blastocysts obtained from my patient, the number of oocytes retrieved, the number of mature oocytes, or I don't know, whatever you can imagine, the number of 2PN embryos. the system will tell you too what is the best option, the best treatment option, the type of gonadotropin and the dose of the doses of gonadotropins. But as you have several possibilities, you can choose, because imagine, for example, a patient which best match with other patients like her is the most expensive treatment. And you have a patient that don't have many money, so you can choose the next option. And in that step, the system will offer you different variants of doses of gonadotropins with that amount of money that the patient has to have the best option for your patients. But I think the good thing is that continuously, if you make any other decision than the best one, the system will offer you the best possibilities in that case. This is the part that we first developed, as I am a clinical embryologist, of course, and we have the part of time-lapse when we work with time-lapse incubators. I don't know why the system is not, the video is not playing. Okay. The previous one didn't work, but it was an overview of embryo development, really beautiful, with embryos in different places, in green, good embryos, in yellow, the regular ones, and the red ones in red. And here we can see all the information that we extract from the embryos, all the information, all the events that the system is detecting is automatically populated in the right side. So you can confirm that the system has really make a good decision in the number of pronuclei or in the division, etc. And if you make or you detect any kind of mistake, you can modify, and the system automatically will learn from those modifications that I make in the system, because as an embryologist, we do exactly the same. When everything is clear, is really easy, but when I have a really fragmented embryo, it's really difficult to say when I have 2 blastomeres, but the system exactly the same. But the difference between the system and me is that the system will learn from the mistakes. So we segmentate the blastocysts, so all the information is recorded, so we can use all that information for doing the comparisons with other embryos. So at the end, it's not only morphology or kinetics of the embryos, because all the hidden information is used for doing the comparisons. And at the bottom, we have the comparable embryos, and at any time, we can go to the comparable embryos or the comparable patients to check if the system really has all that, is as comparable as the system is telling me that it is. At the end, to summarize, because I'm out of time, to summarize, I think that what we want when we are thinking about having an AI tool inside our lab or our clinic is we want something useful for our day-to-day. So thank you very much. And I want to thank all the team of Circle, particularly my engineers that are so lovely, and our medical advisors too. Thank you very much. Sorry.
Yes. Okay, thank you for your very interesting presentation. The discussion is open. Are there any questions from the audience? A question from Carlotta.
Thank you, Irene, for your very interesting presentation. I have a question for you. Do you think that artificial intelligence could be a useful tool when used in association with non-invasive PGT?
Yeah, of course. I think that now that everything that we can use into the system will be informative for all the treatment, anything. So when I talk about everything, non-invasive PGT, of course, is giving us objective information regarding embryo development and the DNA of the embryo, of course, but not only that information that we know that has some kind of connection to embryo development. I think anything. So if we are collecting information, as Valerio says, for example, if you are measuring every day the temperature of your incubators, and we put all that information into the system, probably at the end, we will find any kind of relation, not only with embryo development, but with the rest of the treatment or with other. So I think that the importance is that we have the data to be integrated in systems like this one, to be used in the future and to discover what really matters. Thank you. We have been, just to finish, I wanted to say that we have been talking since early this morning that the accuracy of the majority of the systems that we have right now is about 70%, or 0.7, sorry. But the truth is that when we are reading papers regarding IVF or embryology, all the raw curves are about 0.7, because we don't know the accuracy in IVF is really low, because there are many components that we still don't know what is the real influence in the final fate. Or so, as we don't know a lot of things, what I think that we have to do is to have the possibility to introduce and analyze everything, to have maybe some answers. The more data we have, exactly. Mm-hmm. Thank you. Thank you.
Thank you once again to our speakers, and we hope that this technology will be easily useful in our lab. And now we can move to closing lecture. Closing lecture. So we invite Matteo Ferrante and Tommaso Boccato.
Okay. Thank you for the introduction. This is the last session, the last talk of today, and we will change the focus from artificial intelligence application to IVF in artificial intelligence in general. And in particular, we will present 3 outstanding models from the last years that are reshaping our way to describe creativity. So we will describe novel AI paradigm from chatting to painting in order to visualize human creativity. And basically, the outline of this presentation is subdivided into 3 main parts. And we will describe 3 main objectives, which are generate text, generate images, and segment images. The presentation will split it in 2 parts. In the first part, I will present just an idea of what is behind the scenes for these models, an idea of what is the procedure for the training and what are the objectives. And in the second part, Tommaso, my colleague, will present to you some examples which are very beautiful and very interesting. So let's start. We have talked a lot about artificial intelligence today, so I won't go over the basics. I will start talking about foundation models. Foundation models are basically giant neural networks trained over huge datasets. And we have already said today that the quality and the quantity of the data that we use is a fundamental part that impacts a lot over the performances of the model. In these foundation models, we train our neural networks over millions or billions of images or pieces of text. And these gives to the model the ability to generalize in a very wide range of application and conditions. So if you just have to keep in mind a couple of things to look for when you read a news about artificial intelligence, you can just look for two main parameters. The first one is the quality, and thus the quantity of the dataset, and the second one is the dimension of the neural network that was used. And in general, for both these two parameters, the bigger, the best, because these impact a lot on the performances, and in general, size matters for artificial intelligence. So let's start talking about large language models, because we want to interact with machines using natural language, because in the everyday life, we talk in natural language, and we also want that a machine is able to read, for example, a medical report or answer to our question. So the first step is, okay, realize that we want to interact with machines, not only with numerical data, but also with words, with sentences. So the second step is that we need that a machine is able to understand the statistics of the language. So the machine needs to be able to distinguish between words, verbs, and so on and so forth. And then, okay, we need to collect the data. For example, we can collect all the text that we find in the web, starting from Wikipedia, and putting together all the other websites. Is a lot of text, but we are able, not we, giant companies are able to train this kind of model on such datasets so large, so huge. So the last part is find the optimal algorithm to take care about this. And in general, these are called transformer, and they are based on this attention mechanism. Because if you need to answer to a question, you need to keep in mind the whole context of the question and what are you answering. So these are the main ingredients for a large language model. But what is the behind the idea of a large language model? Just predicting the next word. So we will give to the model a piece of sentence, which is, for example, our question, and the model will start to generate one word at a time the answer. So this is the neural network. I won't go over in detail, but basically it's called a transformer. And a transformer is something that is able to transform our input, the question that we are posing to the model, into our output, another sentence. And this is done word by word, one word at a time. And at each iteration, the whole context is kept into the model. I think that the widely most known large language model is ChatGPT. We have talked also in this day about ChatGPT. And ChatGPT is basically this huge transformer. And how huge is 175 billions of parameters. Just to have an idea, just to run inference, just to answer to our question, there is the need of 800 of gigas of memory. It's like 100 of normal computers, not for the training. For the training, you need much more. Just for inference, just to answer to your question. So it is a huge power consumption. And we need this big model to answer in a very good way to all our questions. But if we just collect information from the web and train this model, we will have a lot of human biases. We have human biases in our text. So if we take the text from the web, there will be racism, sexism, bullying, and so on and so forth. And we don't want the model to respond in the same way that we do on internet. So there is a second step in this model from OpenAI, and this is a step with humans in the loop. So human teach to the model how to avoid this bad answer. And in this way, you can go to the OpenAI website and ask for questions like someone has done today, and write down, ChatGPT write down for you the answer to your questions. And nowadays, we have also GPT-4, which is from 10 to 100 times bigger. And again, size matters. So if we increase the capacity of the model will be so much good than before. So we have this giant model, which are very interesting. But if we want to move from text to images, now we can do also this. For example, we can describe the content of the image to a model, and we can generate an image with exactly that content. And this is kind of frontier of the last 2 years in the artificial intelligence, and we are now able to generate, for example, this image that you can see here, and in the second part of the presentation you will see more examples. I just want to give you the underlying idea behind these so-called diffusion models. Diffusion is a concept taken from physics, and in general things evolves from ordered states to disordered states. Think for example, to a Rubik's Cube. If you do random moves, you will end up with a non-ordered state. It's much more easily because you have a lot of possible non-ordered states and you have just few ordered states. So it's difficult. You have to put effort to complete the Rubik's Cube, but not to just scramble it. And what we can do is just basically learn how to revert this diffusion process. So basically just fix one thing at a time. Think about your room, for example. If it's in a disordered state, or your library, you can just enter in the room and fix only one book. And then you repeat this procedure until you will order the entire library. And you can choose, for example, different criteria. You can order books, for example, by color or by author or by whatever criteria that you have in mind. Okay, we can do the same, aside from this metaphor, using images. We can start from pure noise, so completely random images, and we ask, for example, for a face, and this model is trained to extract relevant feature from this noise in an iterative way. So basically, we start from noise, we remove some noise, and then we generate something which is a little bit more like a face, and so on and so forth, until we generate a realistic face. And the last thing that I want to present, and in the next part, Tommaso will dip more in this, is image segmentation. Okay, we can generate text, we can generate images, but what about image segmentation? It is a very complex task, because if we have an image, it's easy for us to separate things which are related to different concepts, but it's a little bit difficult for a machine to identify all the objects, identify the mask, and do this in a very precise way. And this year, some months ago, researchers from Meta, Facebook, proposed this new method called SAM, segment anything model. And basically it's composed by 2 giant neural networks. Again, they are transformers. And the first part is called the encoder. Basically, it takes an image as input and it outputs a vector. This vector is basically a sequence of number, which is very informative about the characteristics of the image. And this vector, called embedding, is passed to the second neural network, and this second neural network will produce the mask that we will see, and we can overlay to the original image, as you can see in these examples. So basically, this is all for the high-level overview idea of these cutting-edge models, and I will let the floor for Tommaso.
Thank you so much, Matteo, for your... Oh, thank you, thank you. Matteo, thanks for your nice introduction on artificial intelligence and foundation models. Now we will take a look together to some very interesting example of generative artificial intelligence. And I'd like to stress out that these examples actually are real, and real in the sense that you can basically take my own inputs and try them for yourself, exploiting the graphical user interfaces of the mentioned models, obtaining very similar results. And specifically in this first group of examples, we will deal with text generation, which is a task in which you can ask something to your model, and the model will, after a few seconds of processing, try to answer you properly. So in this first example, I decided to write the following input prompt. Explain the plot of Cinderella in a sentence where each word has to begin with the next letter in the alphabet from A to Z without repeating any letters. And as you can see, this task is extremely difficult because actually you have to know the plot of Cinderella, first of all. Then you need also to exhibit some very important synthesis skills. And then a lot of creativity is required. Actually, I will take probably hours to perform this same task. And
The output of the model was the following: a beautiful Cinderella dwelling eagerly, finally gains happiness, inspiring jealous king, love magically nurtures opulent prince, and so on and so forth. So really impressive in my opinion. Oh, thank you. And then we have a second very interesting example. Here I just provided the model with a picture, and I decided to ask GPT-4 what follows. Please, GPT-4, tell me what can I make with these ingredients. And actually this task is even more difficult because the model has to recognize all the objects inside the image, and it has to basically reason about these ingredients. And this time the answer was, there are many options for what you can make with these ingredients. Some possibilities include pancakes or waffles, crepes, French toast. These are just a few examples, but the possibilities are endless. Here instead I decided to report to you a very interesting experiment by the scientists of OpenAI, which wanted to basically assess the reasoning capabilities of this model by testing it on a variety of academic exams. And for example, in the plot I reported, we can find on the x-axis the specific exam considered, while we can find on the y-axis the percentile in which the model score has been placed. And as you can see in this column on the left, MC12, which is something like our Italian esame di Stato for Australian medical doctors, the model scored better than half of the actual medical doctors which tried the exam. And if we consider, for example, the AP biology exam, results are even better. So moving on, now we will consider another very interesting task, which is text to image. And here basically we can prompt the model with a textual description of the image you want to generate. And again, after several seconds of processing, the model will return you that specific image. Here the models involved are Imagen by Google, Dolly by OpenAI, the company co-founded by Elon Musk, and finally Stable Diffusion. This is my first example. I wrote in the system, please generate me a photo of a raccoon wearing an astronaut helmet, looking out of the window at night. And as you can see, results are extremely impressive in this case. The quality is very high, and we are talking about images which are in high resolution. This is instead my second example, a robot couple fine dining with the Eiffel Tower in the background. And again, results are very impressive. And why is this example so important? Well, because I decided to basically ask for an image which is very likely not present in the training set of the model. And this means that basically we are looking at the generalization capabilities of these models, which are unbelievable. And recently, some of the models have been extended to perform even more difficult tasks. Here I'm showing you an outpainting task, which is a task that involves starting from an image which can be generated by text or uploaded to the system. And then you can basically move this bounding box in such a way as to extend the content of the image until you are basically satisfied. And you can move the box, you can repeatedly click on the square, and the content is changed. In this case, I started from a painting from Vermeer, girl with a pearl earring. But there are also other very interesting tasks. For example, in this case, this is an extension of Imagen by Google. And this model is basically capable of generating videos from textual descriptions. And in this case, the input was, okay, please model generate a giraffe underneath a microwave. And as you can see, again, the video generated is very creative, very funny. Okay, now we will take a look to our last task, which is segmentation, in which basically we can cut an image in such a way as to produce masks that cover the specific objects in which you are interested. And here I'll show you something about the segment anything model by Meta AI. So how can you prompt this model? Well, there are different modalities. You can just let the model automatically segment your image. You can also point the object on which you are interested in. You can click the object, or you can also draw a bounding box around the object, or even provide a textual description of the entity you are interested in. So some examples. In this case, we have a very complex scene with a lot of people. And as you can see, the segmentation map is very accurate. Here instead, we have 3 examples coming from very different domains. We have a real life picture of the ocean. We have a painting from Van Gogh, and we have a medical image. And talking about medical images, there is a surprise here for you now. You probably all know what this is. Actually, this is a frame taken from a time-lapse video of an embryo. And I personally asked the model to segment this frame. And this is actually the result after a few seconds of processing. So now it's extremely easy to perform a task like this. And to conclude, we have seen the power of these algorithms, but obviously there are also risks and problems linked to this kind of new technology. And I'm obviously thinking about ethics, which is defined in a discipline, a branch of philosophy, which is involved in defining in a systematic way what, well, the concepts of good and wrong. And specifically, when we refer to AI ethics, we are talking about a set of guidelines, a set of moral principles, which should be enforced in the design phase of your AI algorithm. So why is it so difficult to design such guidelines and to enforce such guidelines? Well, there are many concerns, and in random order, technological singularity. What happens if the model you're designing is capable of outperforming humans in every possible task? Well, that could be dangerous. And then we have responsibility. So you are inside your autonomous vehicle and there is a crash. Who is responsible for this event? Who is responsible from a legal perspective? And then we have also the impact on jobs. But I'm not very worried about this, because actually this is a problem. This is not an intrinsic problem, but this is a problem which is linked to every new emerging technology. And then we have also privacy. So you basically let the model use your data, and then probably the model is trained on your personal data. So when basically your personal information is encoded into the model weights, or in other words, your personal information is encoded into the learnable parameters of the model, what happens if you want to delete this kind of information? Well, we know that the model is a black box, and I'm an AI expert, and I don't know actually how to do this. So this is a really big problem. And finally, we have biases and discrimination. Again, this is a problem linked to our society, but we produce data which is biased. And this is a problem because actually our models can basically amplify such biases in such a way to produce dangerous outcomes. So we have a lot to discuss now. I really want to thank you for your attention, and have a nice evening.
There are questions from the audience. Any question from the audience? Oh, there's a question from the audience from Lello.
Congratulations. Thank you very much. Regarding the last thing about the black box, how can we manage the knowledge that can be deriving from the big amount of data that our machine learning tools are manipulating actually?
Actually, the truth is that I don't know, because probably this is an open challenge in this kind of research. So it's probably, yes, this is an open question. I guess that there are experts working on it, but honestly, I don't know how to solve these specific problems. I don't know if someone else can answer properly.
Maybe I can offer like a discussion, and I really enjoyed your lecture, learned a lot, thank you. I think because machine learning and AI really goes with association. So it doesn't necessarily tell us the cause and result. So, but once we learn a lot of associations, maybe we can use that information to generate new hypotheses for testing. So I think we still have to go back to scientific principle and generate hypotheses, but now we can generate much better hypotheses and spend our time testing much more relevant questions, yeah, and get to the truth sooner.
We all heard of ChatGPT during the past few weeks, maybe a few months, okay? But I think it was around a little before. But did you use it before, or did you know of ChatGPT before? Or you got to know the existence of this tool as we did in the past few months?
Thank you for the question. So language models are around in the research field from 2015, more or less. But ChatGPT that came out in November of 2022 was kind of a revolution because of the dimensions, because it was the biggest one by a very wide margin. And the abilities of ChatGPT that you probably have seen are so greater than the previous models that makes him able to reach the wide audience. This is because the news talks about ChatGPT. There are a lot of interest now around this ChatGPT. Language model. We have language models from 2015, 2017, more or less. So they are around for years, but never so powerful. So this is the first year that we have so powerful model.
ChatGPT was kept a secret before. I mean, nobody knew of it.
It was
before.
not a secret. ChatGPT is based on GPT-3. Now we have GPT-4. And before there was, of course, GPT-2 and GPT-1. It's not a secret. We knew that OpenAI was working on it. The surprise was the performances. Because every time they scale up this model, it's basically always the same thing, always a transformer, but every time they scale up by 10 or 100 times. And when they do this scaling up, the performances increase in a way we are not able to predict.
So in simple words, they invented some algorithm, new algorithm.
This is the point.
Something that nobody else has done it before.
No, this is not a new algorithm. The algorithm is always the same. It's always try to predict the next word in the sentence. It's always the same thing for years, but now it's so powerful because it's bigger. It's bigger than before. And before we added the computational power and the data to train this model.
Okay.
This is the main point, I think. And when you scale up, just the last thing, when you scale up this kind of model, the game is that you are trying to predict the next word, and you can do this in a very creative way. And the model has some emerging abilities, and these emerging abilities are not necessary, but they emerge. For example, there is the ability of translate between different languages. There is the ability to precisely answer a question, doing a specific task like the Cinderella one, and so on and so forth. If you don't scale up until a certain level, you don't reach these capabilities. Upper a certain threshold, you will see some of these emerging properties. And this is the things that is carrying, for example, Hinton. When he say, I left Google because I want to, is scared about emerging properties because we cannot predict these emerging properties. So thank you.
Thanks to you.
Yeah, just a quick comment. I think to your question about explainability, about black box, I think Tommaso was a little bit modest because I know he knows about there is actually a dedicated research field about so-called explainable or interpretable AI, which is at least to some extent what opens the black box side, which just means, okay, answer the question, which is a very natural question for a clinician. What did you use to make that prediction? Which areas of this image were the most predictive? Which subset of data was the most predictive? This is actually something that is done almost routinely, although he was obviously correct in saying that for these foundation models, you cannot do it anymore. But for regular models, you cannot do it. And I just had a second comment about the lack of causal relationship that our colleague was making here about associations. Actually, there is, just as a comment, there is a branch of machine learning which is called causal machine learning, which is just emerging now, which is trying to tackle exactly that, to actually make predictions in a causal way, not just in an associative manner. Just in case anybody wants to look it up or is interested, I just wanted to make that comment. Thank you.
Thank you. So much. So before the closing remarks, for people who don't know, I would like to underline that we are a scientific society that is ISO certified. And today we got the inspection for the maintenance of the certification. We are really proud to say that we confirmed our certification, and we have to thank for this the quality team, in particularly Maria Luisa Cinti, who works a lot about the certification of our society. So thank you so much for this. And thank you also Laura Sosa, that spent a lot of time again with this. And then please, Danilo, could you please close this event? I think you are the best person ever to do this.
Well, I mean, you tell me how it went. We can discuss about that later during the networking event. We just wanted to tell you that the whole meeting has been recorded, and we will make it available for you, also for the companies, to share it with their customers. And well, I think that we try to give an overview starting from the basics in a very educative way, and then dig into the more commercial aspects of how AI can help us. And I'm really happy that the guys now gave us this very nice talk about the perspectives that we can imagine, and that's definitely much more. It's very interesting to listen from Nicola when he says there is new emerging, this is emerging, everything is emerging. So, and I mean, this was just to give you and us the basics to be ready to all these things that are emerging. And now it's time to enjoy ourselves and have the possibility to keep talking about all the hints that we had from these talks.
Yeah, I think that the best way to make a brainstorming is with alcohol.
With alcohol, yes.
Yeah, for sure. Yeah. So let's make a brainstorming, but
machine don't get access to
alcohol. Absolutely. Absolutely. So let me thank again the scientific committee of the society who work in the organization of this event, also the executive committee that spent a lot of time about the organization of this event again.
And all the sponsors that made it possible.
All the sponsors,
supporting companies.
Absolutely.
Really, really important.
Yeah, because they make the success of today. And at the end, Danilo. No, sure. You're the man who spent for sure a lot of time in the organization of this event. So thank you so much for this. Let's drink something.